Feels like I am dreaming, letting go of these demons. I just wanna know what's on your mind. There's not enough reasons, it's not like I need them. I just wanna know what's on your mind. What's on your mind? It's like 3 a.m., you're still on my mind. Let's not waste no time, just tell me how you're feeling. You still have my heart, although we've been apart. Let's go back to the start, I think we're both too brief. See the tunnel light, it's never been so bright. I haven't lost the fight, you let me keep believing. You still give me chills, I do it for the thrill. Yeah, you still give me chills. Yeah, I feel like I can tell you anything. No white lies, compromise, just up your range of wings. Let's continue what we do and build the trust again. You can tell me what to do. Feels like I am dreaming, letting go of these demons. I just wanna know what's on your mind. There's not enough reasons, it's not like I need them. I just wanna know what's on your mind. What's on your mind? What's on your mind? What's on your mind? You make me love and hate you at the same time. I feel like loving you is like committing a crime. How can you make me come and act just at the same time and let you take the crown? You made me nervous and I pretend that I'm just fine. I don't know why you gotta keep messing with my mind. Let me open up my heart and let you inside. My heart is jumping around. Yeah, I feel like I can tell you anything. No white lies, compromise, just up your range of wings. Let's continue what we do and build the trust again. You can tell me what to do. Feels like I am dreaming, letting go of these demons. I just wanna know what's on your mind. There's not enough reasons, it's not like I need them. I just wanna know what's on your mind. What's on your mind? 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 Bet you can see me. Invisible. Feels like I'm drowning. Invisible. Hidden in the corner of this crowded room. Visible from your look, will you find me soon? Trapped in the darkness, lost in the night. So far away, out of sight. Discover and release my love somehow. My questions need your answer, give them to me now. Pain inside is way too much. Just want to hold you and feel your touch. Yeah, oh, oh. want all the lovey-dovey sex. You rent out with the lovey-dovey sex. With you, I want it all. Girl, you are a winner when I take you around the globe. From the summer to the winter, when I be around you, won't you give me a call? I wanna drive all night, wanna take your private jet to the sunny mountains. Wanna make you smile, with you, I want it all. You got it, got it, got it all. Your body to your smile, want you to my own. And I just had to let you know. Come and bring it here, 'cause I want it all. You got it, got it, got it all. And I just had to let you know. Got it, got it all. And I just had to let you know.
I was all alone before I met you. Heartbroken, all up in my chest. And had me thinking, damn, all I really needed was some glue. But then you came and caught my eye. One night stand to a 1 week ride. Oh my, now you got me thinking, damn, all I really need is you. Yeah, it's like we're jumping off a summertime thing to another one fling. Then we cozy up in winter, give a fuck about the spring. 'Cause I really want it all, took another diamond rings. Hey, whether the weather be the November, December, kill it together. Have you higher than ever, a second best, so contender. Spend it all on you, generous for the love and the tenderness. Swear to God, it's an effortless life.
Got it, got it, got it all. Your body to your smile, want you to my own. And I just had to let you know. Come and bring it here, 'cause I want it all. I want it. You got it, got it, got it all. And I just had to let you know. You got it, got it, got it all. And I just had to let you know.
Queen on the throne, call you royalty. Me and you together, that's loyalty. House in the hills and we out chasing thrills. So you living like the woman you were born to be. I'ma never let you fall, I'ma never let you down. I'ma never miss a call, I'ma always lift you up. I'ma always give it more, 'cause you got it, got it, got it.
You got it, got it, got it all. Your body to your smile, want you to let you know. You got it, got it, got it all. And I just had to let you know.
I remember when we were staring a photo. Don't forget the way you look me in the eyes. And I keep you in my heart, and my heart is where you are. I still think of you, I want you coming back. I remember when we were staring a photo. Don't forget the way you look me in the eyes. And I keep you in my heart, and my heart is where you are. I still think of you, I want you coming back. Call me when you want, baby, I can take it on my heart. Yeah, yeah, give me your love, yeah, yeah. Call me when you want, baby, I can take it on my heart. Yeah, yeah, give me your love, yeah, yeah, yeah. I remember when we were staring a photo. Don't forget the way you look me in the eyes. And I keep you in my heart, and my heart is where you are. I still think of you, I want you coming back. I remember when we were staring a photo. Don't forget the way you look me in the eyes. And I keep you in my heart, and my heart is where you are. I still think of you, I want you coming back. Call me when you want, baby, I can take it on my heart. Yeah, yeah, give me your love, yeah, yeah. Call me when you just push me out, try to push me out. And I wanna be patient with us, but it feels like you're giving up. I see a difference when I look in your eyes. Never a time I wasn't there, right by your side, no matter what. Whenever you call, I would come running, but it meant nothing, nothing, nothing to you. You and I have had better days.
face it tonight. Face it tonight. Oh, no way though. Maybe I can't let go. Maybe I thought you'd take my side, my side. No way though. You never think it through. One more round and not going down tonight. Baby, you're worth the fight. Why you playing? No rhyme or reason, oh, it's not fair. It's not fair, no. You said you were staying through the winter season, but you're not there. You're not there, no. No way, though. Maybe I can't let go. Maybe I thought you'd take my side, my side. No way, though. You never think it through. One more round, I'm not going down tonight. Baby, you're worth the fight.
I don't trust anyone since you just broke my heart. We were different minds. I was red and you were black. I had never felt so lost. I'm fine without your love, but I have to be strong. I try not to think about that. Where you leave in my place. I just want to forget you, but I'm not capable. Ooh yeah, ooh yeah, hey, hey. I don't want to fall again. Ooh yeah, ooh yeah, hey, hey. I don't want to fall again. Ooh yeah, ooh yeah, hey, hey. I don't want to fall again. Ooh yeah, ooh yeah, hey.
Okay. Good morning, guest speakers and participants. My name is Jung Ho Shin, one of the organizers of this event. And thank you for joining us today at KRICT R&D Forum on Materials Data, AI, and Autonomous Laboratory. We are thrilled to have experts from around the world gathered here to discuss about the future of material science and technology. To start, we will now have the opening remark from the Dr. Young-Gung Lee, who is the president of KRICT Research Institute of Chemical Technology. Please give a big hand.
예, 안녕하십니까. 한국화학연구원 원장 이영국입니다. Before starting my greetings to you, actually I didn't know that so many foreign participants are here. I'm sorry because I prepared greetings in Korean, so the rest of my greetings will be proceeding in Korean language. Sorry. 안녕하십니까. 다시 인사드리겠습니다. 한국화학연구원장 이영국입니다. 먼저 이 좋은 청명한 가을에 바쁘신 가운데서도 크릭트 R&D 포럼에 참석해 주신 모든 내외 기빈 여러분께 환영과 감사의 인사를 드립니다. 이번 크릭트 R&D 포럼의 주제는 머티리얼스 데이터, AI 그리고 오토노머스 레보러토리로 소재 데이터와 인공지능 자율 실험실을 통한 연구 자동화의 혁신입니다. 인공지능을 활용한 소재 연구 데이터의 수집, 관리 그리고 활용은 소재 연구의 패러다임을 변화시키고 있으며 이번 포럼을 통해서 관련 분야의 최신 연구 결과와 기술들을 공유하시고 또 협력할 수 있는 기회가 되기를 기대합니다. 특히 오늘은 고속 실험과 AI 기반 예측 모델 등 연구 현장에서 실질적인 성과로 이루어질 수 있는 기술들을 다룰 예정이고 또한 기계학습과 고속 실험 기술 그리고 과학적 예측을 위한 언어 모델 등의 연구 또한 여기 오신 연구자들에게 새로운 영감을 줄 수 있을 것으로 생각합니다. 오늘 이 포럼에 참석하신 모든 연구자와 관계자분들께 유익한 정보와 협력의 기회를 제공할 수 있기를 바라며 소재 연구의 새로운 가능성을 다 함께 열어가기를 기대합니다. 참석해 주신 모든 분들께 다시 한번 감사의 말씀을 드리며 오늘 뜻깊은 시간이 되시기를 바랍니다. 예, 감사합니다. Thank you.
Thank you. Now we'll begin our first session of this forum. And the chair of this session is the Professor Woo Sung-jang.
Morning, everyone. So, as the president of the KRICT mentioned, so we have a valuable research forum today, and we will be discussing over the materials data, artificial intelligence, and then autonomous laboratory. So, We have a first speaker from the Massachusetts Institute of the Technology, MIT, Dr. Junyoung Francis Chung. And while he's preparing his presentation material, so I would like to introduce his short CV. So he had his degree in chemistry, PhD degree in chemistry from the Korea University, and then he went MIT for a postdoctoral research associate under the division of the Professor Connor Colley. So today he will be talking about the curation of novel datasets for the machine learning applications in organic optoelectronics and then reaction mechanism prediction. Let's give him a round of applause.
Thank you for kind introduction. And is there any click? Oh. Good morning, everyone. And thank you for organizing this wonderful forum. I am Junyoung Chung, and I am postdoc of Colley Research Group at MIT. And today, I'd like to present my work during when I was in a postdoc in Korea University and MIT. So, yeah. So I got my PhD degree in experimental physical chemistry. I studied many time-resolved spectroscopic techniques, and this is okay, good. So I studied many molecular systems that interact with the light, and we call the molecules interacting with light as chromophores. And we can use these chromophores in many different ways, like thermochromic sensors, chemosensors, and we can stain the cells to visualize, like in this bioimaging techniques. And we can use this chromophore as emitter in OLEDs, or we can observe the lights to make an electricity in photovoltaics. And this photoacid is my thesis molecule, which is the aromatic acid that has a lower pK in the excited states. So we can control the release of proton by irradiating a light. And I had a lot of collaborations, and they give me a molecule. And when I got the molecule, then I measured these three spectra. First is UV visible absorption spectrum, and steady state emission, and time resolved emission spectrum. And these are kind of fundamental. It has fundamental informations that absorption maximum wavelength or emission wavelength. And these two properties are very typical properties, and we can calculate them using DFT calculations. And however, there are many other properties that are not calculated using DFT. For example, the bandwidth of the absorption spectrum is very important in photovoltaics, because once we have a very wide bandwidth in absorption spectrum, then we can observe a wide range of wavelength in the light. And however, for the bandwidth in emission spectrum, we want some very narrow emissions in the OLED, because narrow bandwidth has a very pure color. And the photoluminescence quantum field is also important, because it represents the brightness. And the fluorescence lifetime represents the lifetime in the excited state. And I measure those three properties. And those properties are not only determined by the molecule itself. These properties is affected by the surroundings, like solvents. And this Richards betaine 30 is a typical molecule that has many different colors in different solvents, from THF to hexafluoroisopropanol. And these means, like the solvents, the surroundings can affect the band gap of HOMO and LUMO energies. So, and this is also observable in cyclic voltammetry. The HOMO and LUMO energies are affected by the surroundings like this. And so this is my background, PhD backgrounds, and I I heard a seminar at 2019 from Professor Uyeon Kim at KRICT, and he introduces some graph neural networks to predict the molecular properties. And I was inspired by that seminar, and I tried to use the machine learning models to predict the optical properties. And I studied machine learning by my own, and I tried to find some good database, because we need a database to train or build a machine learning models. However, there was no data sets out there. So I decided to make the data set by myself. And I had no technology to automatically collect the data, so I collect this data set manually, and I search the paper and draw the molecular structure in ChemDraw and copy that structure to SMILES, and I also collect the optical properties with the solvents. And if I spent 12 hours per day, then I was able to collect 3 data points per day. And so when I leave the Korea University, and now I had 80,000 data points. It was painful, but I think it is valuable to do that. And now I had data sets, so I decided to make machine learning models. And as I inspired by the seminar from Professor Uyeon Kim, he introduced graph neural network. So I used very simple graph neural network to predict the molecular properties. And I passed the chromophore to graph neural networks and also solvent as well, because the optical properties are determined by these two. And after the graph neural network, I passed them to several multi-layer perceptrons, and I predict these properties. And this is the results. X-axis is the experimental value, and y-axis is the predicted value by the deep learning model. And the upper left corner is the absorption wavelength, and it has a very good accuracy, like 0.98 of R-square values. And this is quite impressive. And I like to emphasize 2 other properties, like photoluminescence quantum yield and fluorescence lifetime, because those 2 properties are not predictable by DFT calculations nor by human intuitions, because these 2 properties are characterized by interactions between the surroundings. However, using very simple deep learning neural network, we can predict them with a decent accuracies of 0.89 of R-squared values. So these 2 properties are predictable. And I compared the accuracies of deep learning model with DFT calculations. I select 131 chromosolvent pairs and calculate the absorption in emission wavelength. And DFT calculations, I use some very basic ones, but it has worse performance, worse accuracies than DFT, deep learning models. Because I think, so DFT calculations calculates only one conformation of the molecules, but in experiments, in liquid phase, in solution phase, the molecule can have a multiple conformation, and we are observing some ensemble averaged properties. So these are not reflected in DFT calculations. However, deep learning model can capture that. And I tested the deep learning model with the molecules I use in my researches, and this is the photoacids, which has a lower pK in the excited states. And the deep learning model was able to predict the acidic and base forms well, and the other molecules as well. And the deep learning model predicts the molecular properties within the 15% of error. And the more good thing is, once we know these optical properties, then we can simulate the spectrum. I assume that absorption and emission wavelengths with very simple Gaussian functions where the absorption is defined by extinction coefficients and absorption wavelength and its bandwidth. And from the, and I compared the experimental spectrum and the two spectrums from deep learning and DFTs, and deep learning is very close to experiments. And once we have the spectrum, then we can simulate its color. And the color under the daylight, the yellow color, all three DFT and deep learning methods has very similar color to the real one. However, DFT fails to predict the emission color. It predicts blue, but the green is the real one. And the machine learning model can also predict the solvent effects. So the Richards betaine 30 and the other solvate chromic dye, the model is very sensitive, and it knows the color changes. And the model also able to predict the color in the solid states. And now I have the machine learning model, and now I can simulate the colors. So what is a good thing? And when I was in Korea University, I had a collaboration with LG Display and Professor Dong-Hoon Choi. And the task was we want to develop a new deep blue emitter with decent quantum yields. However, and Professor Dong-Hoon Choi is an expert, and he knows which structure will have blue-ish color. But he doesn't know, or his group doesn't know, which one will have really deep blue colors. And in the purpose of OLEDs, we want deep blue color, not blue-ish color. And he designed several molecules, and I have deep learning model, so I can predict these optical properties, and we can choose the most promising ones. And these three are the examples, and their predicted ones, and the molecule 1 is predicted to be blue. So we synthesized this molecule, and I measured the properties. And as you can see, the color in the cuvette is matched with the predicted one. So we can, using deep learning model, we can accelerate the discovery of new chromophore. And this work was done when I was in Korea University as postdoc. And the second topic is my work at MIT. Professor Konakoli gave a mission to introduce Koli Research Group in this KRICT forum. So we are working on many things, many machine learning models in this diagram. So machine learning models can design promising molecules. And once we have a target molecule, then machine learning models can retrosynthesize this molecule and once we have like a target molecule and its precursor, we can predict the reaction conditions. And from a given reactants with reaction conditions, we can also predict what is the most likely outcomes of the reactions. And as machine learning model predicts the reagents, reactants, and the other reaction conditions, the autonomous laboratory will make that molecule in high throughput manner. So the robot is also measured mass spectrum, and we have another machine learning model to decipher the molecular structure from the mass spectrum signals. And this loop can be completed by the modeling, and we can connect the molecular structures with the properties. And I am working on the fourth synthesis part, which is this, the organic reactions. Okay, so the left part is the reactants and right part is the product. So as a chemist, we want to know will be formed from a given reactants. And this is a very important problem, so many machine learning scientists also work on that. And now we have many machine learning models that predicts the most likely outcomes from a given reactants. And these machine learning models achieve 93% of top 1 accuracies. Now, so I would say, oh, we have a very state-of-the-art models. And this was the current stage when I joined the group. And when I looked at model, oh, it seems like model understands the chemical reactions very well. And however, as a chemist, we don't think the product directly from the reactant. We think the reaction mechanisms. So in the reaction mechanisms, it consists of several sequences of elementary steps. And there are many roles of chemicals like reactants, intermediates, products, and some byproducts and spectators. And I wanted to develop a new machine learning models to predict these reaction mechanisms. And so the question is this. So the model has state-of-the-art performances to predict the products, but what if we predict the intermediates? And it was impossible because there was no data sets. And again, I faced these situations and I decided to make a new data set for this. And I don't think I can make the data set manually, so I have to think about some more clever way to do that. And so I tried to mimic how chemists think the reaction mechanisms. For example, let's say we have a reaction that carboxylic acids and amine react to form this amide bond. And as a chemist, when I look at these reactions and think the reaction mechanisms, I don't think the reaction mechanism with the entire structures. I think this kind of reaction mechanisms where the unreactive part is replaced with the R group. So we do think the reaction mechanisms in this kind of template. So I think, oh, maybe I can use this strategy to impute the intermediates. In other words, let's say we have the reactants and I made the reaction templates. And I can apply the templates sequentially to get the final product recorded in the data sets. And the template is written in very general form, so it can make many other possible products, artificially possible products. For example, 35 molecules has like magenta color. That is the product recorded in the data sets. But however, this strategy can make the other products, 38, and that is not recorded in the data set. So this is some kind of artificial ones. However, I know what is the true product and what are the reactants, so I can find a way and prune them to get this very clean reaction network. And by doing so, I can remove the artificial products, and the molecule 16 was a reactant, but now it is a spectator. So by doing so, I can impute all the intermediates in this way. So I made 175 reaction mechanisms and resulting in 5.8 million elementary steps. It took 3 months. And so now I have a data set, so I need to make a new machine learning models, but we need to think how should the model work. So we have several elementary steps, and the goal is from the reactants, we want to get the final products. So And I think the many machine learning models can work on each steps, like the direct model. And however, the model should know when the reaction is over. So I made an artificial reaction at the end where the product is repeated. So there is no changes at the end. And I used 3 different machine learning models, which is developed in recent. And the first one is graph-based model, Weisfeiler-Lehmann difference network, and the other 2 are sequence generation models. First is molecular transformer. So molecular transformer translate the reactant smiles to the product smiles. And the graph to smiles also generates the product smiles, but input is the molecular graph. And with these 3, I trained these models, and now I had to see its performances. And so we have many elementary reactions, so I do think some typical top K accuracy is enough to see its performances. And this is the result. Sequence generation model has better performances than graph-based models. And I think I need to mention there are some upper bounds of each top 1 accuracies. I think this is not good example, but once let's say we have an aromatic ring and nucleophile attacks the aromatic ring, then positive charge will be formed either 2 ortho positions. And in the smiles, those 2 molecules are different in smiles. So, and the machine learning model cannot predict these 2, as rank 1 simultaneously. So there are some upper bounds. And graph to smiles has a very good accuracies. But I don't think this is enough descriptions of the performances, because for this reaction sequence above, the top 1 accuracy of the sequence is 75%. However, one of the steps is 11, then the top 1 accuracy is still 75%. However, once we, let's say we start from the reactants and we are using beam search strategy. And previous one, in this scenario, if we set beam width of 2, then we can find the final products. However, in this scenario, it is impossible. So I think we need another metric to evaluate this kind of situations. So I define a sequence rank, which is the minimum bandwidth to get the final product. So the sequence rank of this is 2, and this is 11. And graph to smiles, again, has best accuracies among these 3. And so it can predict 91% of sequences with beam width of 1, so which is good. And many chemists ask me, oh, this model only predicts some very basic level reactions, and even undergrad can do that. So why should we use that? That was a question, and this is one of my answers. And this is the reaction of amine protection using CB0. And this reaction types is not covered in the training set. However, the model was able to predict the recorded products. So at first, amine attacks carbon-carbon, and then proton transfers, and then chloride leaves, and the carbon oxygen is deprotonated to form the final products. And the model predicts each steps as top rank 1, so this is very good. I was happy. And as you can see, at the reactants, we have a secondary amine. So, and model predicts the other way, like protecting the secondary amines. And I didn't teach the model like primary amine is more reactive than secondary one, but model was able to predict in a right order of them. And there is one more thing, like in fact, this CBC group can be deprotected under acidic conditions, and the how can I call that? Like so at the center, the carbon and oxygen is protonated, and there are 2 additional HCl molecules. So model started to predict deprotections. And so chloride attacks benzyl group, and it forms benzylic chloride, and CO2 evolves. And deprotect amine groups attacks benzyl chloride and form this kind of new byproduct. I knew that it couldn't happen depending on the reaction conditions, but the most important thing, it suggests this kind of possibilities. And this is a very important thing for pharmaceutical companies. So I'm working with Pfizer to elucidate some possible impurities. And this mechanistic model provides which step is crucial to form byproducts. And in this case, the acidic condition is a problem. So we can neutralize the acids in proper timing. So we can prevent this kind of situations. And yeah, the conclusion. Yeah. So I built 2 data sets for my researches, and the optical property data sets can help us to develop a new chromophores, and mechanistic data sets help us to identify some possible impurity formations. And I think the novel data set, so as machine learning scientists, we are relying on the data sets, and we can solve the problem where the data set defines. So I think a novel data set is always useful, and once we have a new data sets, then I think the data sets provides us a new challenge, like the optical properties data sets. The optical property is a result of interaction of 2 molecules, like chromophore and solvents. And my model doesn't handle this interaction very effectively, but this data set gives us a problem, like how can we model this kind of interactions in better way? And the mechanistic data sets, so the problem is we need to predict a sequence. And one of the steps is, if it is failed, then we never get the final products. So I think the question is, how can we make some fail-safe models to get the final products? So this is kind of my concluding remarks. And I'd like to thank my PhD advisor, Seongnam Park, and my current PI, wonderful PI, Connor Colley. And I'd like to thank AML PDS for funding. Thank you for your attention.
Thank you for your nice presentation, Dr. Jung. So any questions from audience? And also we do have our presentation live on YouTube, so if anyone in the online can ask a question through the chat as well. So anyone in the session room have any questions? Yes, please.
Yeah, literally, I did that in. 3 months is for the mechanistic data sets, and for the optical properties, it took 2 years. But like once I have like 10,000 data sets and I started to make a machine learning models and it works, and my old PI like make it better model, then I said like we need more data, then he said collect them. So okay, sir. Yes.
Oh, yeah, I mean, that was the question.
Okay, so, yeah, yes.
Although I was initially trained as a chemist, but I almost forgot most of the chemistry. So you mentioned that one of your reaction network model began to gave the right ranking between the primary and the secondary amines. Do you think that was, so I mean, like really it's not an offensive question, but is there any like physical meaning that therefore your machine learning model actually knew it, or do you think it was kind of a by chance, or is there like a construct such that, you know, yeah.
So I think the data set describes that fact. So the data set has many protection reactions, and I think there are more chance to predict primary amines than secondary amines. And so that is kind of biases in the data set, so model is also biased to that distribution. So that is my understanding for now.
Any other questions from audiences? If not, I do have a small question, maybe related to the Professor Sun's question. So you did actually eliminate some of the reactants or the byproducts during your collection of the database. So is it like, so do you have any strategy to screen out which are the non-necessary molecules or the byproducts? Or I think it is somewhat constraining your data set to human bias as well. So it may affect your final product. So how did you actually select it, which one to eliminate or which one to include during your pruning of the data set?
So the pruning procedure is kind of automatic. So so I use the data sets of like USPTO full and pistachio data set, which has many organic reactions where like, so I mean organic reaction means like reactant and product pairs. And most of them will have like only one product, major product, and all the other things are reactants, including the solvents. So, and these is our starting point. And when I make the reaction network, then I can identify which one is the product because it is recorded in the data sets. So I can find a route that connects from the reactants to product. So, and I pruned all the other pathways. So there is some chance to miss the real product, but they are not recorded in the data sets, like because they are maybe a minor product or maybe they are not desired products. So maybe there are some risk of that, but for now, I think the model is fine with that.
Also, one last question about the data set. So have you ever tried to augment your data set with other techniques, or have you tried to maybe collect your data automatically from the possible or the literatures available in these days?
Yeah. So I wanted to be grounded in like to experiments. So so there's many techniques to augment the data, but we want to make them to mimic real experiments. So no, we didn't.
So maybe one last question from the audience, if there is. Or else let's give a speaker once again the big hands. And then before we introducing the next speaker, we'll have a short break to rearrange our settings here for the live streaming. So yeah, we'll begin again maybe in 5 minutes. Thank you for waiting. So we will start the second presentation of the first session. So while preparing for the presentation material, I will also shortly introduce Dr. Ho Won-jin from KRICT. So he actually had his bachelor's and then PhD degree in the School of Chemical and then Biological Engineering at Seoul National University. And then after that on, he is now working in the KRICT Chemical Material Solution Center as a senior researcher. So today he will be talking about AI applications in diagnosing the modern transport phenomena in the complex fluid. So please give a speaker a big hand.
Thank you for introduction. Is mic working? Yeah, okay. And the pointer is here, yes. Yeah, I'm now working on the here, complex fluid modeling and simulation and artificial intelligence. I'm gonna introduce some examples of my researches involving AI. So this is the topic of my presentation, a complex fluid. Complex fluid is a fluid that containing macromolecules like polymer, particle, surfactant. And unlike the simple liquid or solid, this complex fluid shows very unique behavior due to several reasons. The first is summer motion. Their spontaneous summer motion, the speed of their spontaneous summer motion aligns with the time scale of human perception or human process. And this material have various interactions between the component, for example, the van der Waals attraction or charge repulsion. And they also interact with the suspending medium or the flow so that they form very complicated morphologies. And due to these things, this complex fluid shows very distinct behaviors. And this is the example. I think many of you are not familiar with this subject. These are the example of the behavior of the complex fluid in terms of transport phenomena. And there are mass transport phenomena like this. This is the aggregation of the particle or gelation in the particulate suspension. And this is the deposition of the particle or clogging during the microchannel flow of the particulate suspension. And this complex fluid sometimes shows yield stress behavior like solid. And this is a tubulous siphon phenomena due to the viscoelasticity of the polymeric solution. And that one is a load climbing effect due to the normal stress differences under the deformation. So traditionally, when we study this kind of transport phenomena, we consider the balance equation of the force or energy exerted on the component, the particle in the suspension or the fluid. This is for the explanation of the movement of the particles in the suspension. And sometimes we do the simplification. I'm lost, yeah. To the simplification of the interaction between the fluid and the component to obtain this kind of differential equation, the equation of the motion of the fluid. However, this kind of theoretical approaches are not always effective, especially when we try to develop a new material or new processes. So that's why we need the machine learning based, the data-driven approaches. So I'm going to talk about 3 topics today. The first one is early detection of pore clogging in microchannel flow. And the second one is the classification of battery slurry. And the last one is developing the data-driven constitutive equation. So this is the first example. We set up the system where the polystyrene particles flows through the T-shaped microchannel, and there is a single inlet and 2 outlet there, like this. And we took an image of the flow during the suspension flow through the T-shaped channel. And here you can see that the particle attached to the channel walls, and under certain condition, such as low flow rate and low viscosity, we can observe the clogging. So the narrow channel is completely blocked by the polystyrene particles. And this tendency can be explained by, it's broken. This tendency can be explained by the force balance equation. So the left one is the drag force exerted on the particle due to the flow, and the right one is the attractive force between particle and wall. And this theoretical analysis aligns very well with the experimental result. Here, this criterion is derived by this formula, and this criterion distinguishes the clogging samples and non-clogging samples very well. However, this kind of theory is not always available, and it is also important to predict the clogging before it happens, not observing it after it happens. So we introduced the machine learning techniques. Here we used a convolutional neural network, which is very famous for specialized for the image processing. And we used 3 different types of the structure, mathematical structure of the model. First one is just the simplest, the 2D CNN, which process the image through the neural network calculation and produce a single output. The output is the probability of the clogging in the future of this input image. And second one is the time-dependent CNN, which has the same structure with the previous one, but it additionally used the time value information as an input. So it means the elapsed time from the beginning of the flow. So time-dependent CNN utilize the direct information about the temporal change. And the last one is 3-dimensional CNN, and it does not use the direct information of the time, but it uses the continuous multiple images as an input. So it only uses the information of the change of the image as an input. So we train those models by using binary cross-entropy loss function, and here is an example of the output. P clogging is the probability of the clogging in the future of the input image, as I mentioned, as a function of time, given as a function of time. And you can see here that the value of the output of the clogging sample is higher than that of the non-clogging sample. So we can establish a threshold between these 2 curves to distinguish the clogging and non-clogging. And to consistently measure the performance of the models, we defined the cumulative AURC, which is the core value of the model, independent of the value of the threshold. And we also define the detection time, the time of the detection of the clogging, which is the time when the value of the score goes over the value of 0.8. And we conduct an experiment under those conditions, and we set up the test train split, trying to avoid the overlapping between the test and the training data set. So here is the result. The actual clogging occurs at approximately 1.5 hours after the beginning of the flow. So the clogging is there. But those 3 models predict the clogging way before it actually happens. And definitely the time-dependent CNN, which use the direct time information, is the best. However, sometimes it is not possible to measure the exact elapsed time from the beginning, and in that case, the 3D CNN can be an alternative choice. So in this problem, we found that convolutional neural network can effectively predict the future clocking, and the time information, the temporal information, is very important for the fast detection of the clogging. And this is the second example, the battery slurry classification. In this problem, the battery slurry is a particulate suspension consists of graphite particle in micrometer size and carbon black particles in nanometer size, and the CMC polymer. So it's very complicated. And in the suspension, the aggregation is very likely to happen, and controlling the aggregation is very important in the manufacturing of the battery. So, however, this kind of slurry is not transparent, unlike the previous one. So we have to find another way to find an information about the fluid, the structural information about the fluid during the flow. So the key concept of this study is that the structural information of the fluid is hidden in the flow signals. Actually, the chaotic fluctuation of these flow signals, and it might be able to find or extract the structural information from this chaotic fluctuation by using machine learning techniques. So we set up this circulation system. So we circulated the battery slurry in this closed loop for 7 days. And during the circulation, we measure the real-time signal of pressure and the flow rate with a frequency of 20 points per second, so for 7 days. And after the circulation, you can see that the viscosity of the slurry decreases from here to here, which implies that the structure had been changed. And to process these signals, we first normalized the signals to observe the fluctuation, the chaotic fluctuation. And we introduced the echo-state networks, but I'm not going to explain the details of ESN, but it is specialized for classifying the chaotic patterns and chaotic signals, time series data. And we train this ESN model to distinguish the data of day 1 and 7. So the endpoint data. And you can see here that by training a data during about 10 minutes and measuring the data for 5 minutes ensures the almost perfect classification. And if we calculate the data of the intermediate period, then which are not trained in the network, you can see that the output gradually increases from the value of the day 1 and to day 7. So it means that the network captures the gradual change of the structure inside the fluid. But so this kind of model can be used practically used in the industry, but this ESN model do not tell us anything about what fluctuating pattern is important, or and it does not give any information about the internal structure or the fluid property. So it leads us to the next example. This is constitutive equation. Constitutive equation is one of the most important topic in the field of rheology, which is maybe you're not familiar with this. And constitutive equation is a relation between deformation and stress of the complex fluid, and these are given as a function of time. So if we know the constitutification of the complex fluid, we can simulate or calculate every behavior of the complex fluid. So it is a DNA of the fluid. However, theoretical modeling of the constitutification is very challenging. Actually, not a single constitutification is known for describing a single complex fluid very well. And even though we know the constitutification, it is also not easy to find the equation parameters from the experiment. And if we develop a new material, it is also very challenging to formulate the new constitutification for the material. So that's why we introduced the data-driven approach. And when we design the data-driven model to describe the constitutification, we should consider following things. The model should be trainable from the experimental or synthetic data, and the model should be able to capture the important rheological properties, the relaxation time or viscoelasticity, and so on. And this is very important. The mathematical shape of the model should not be predefined for the generalization property. But the model should satisfy some important physical principles, such as frame invariance, Galilean invariance, or rotational invariance, because it is a physical model. So at first we tried recurrent neural network, which is a specialized method for the sequential data, time series data. And in RNN, every output as a function of time are given as a function of every previous input. So the mathematical structure of this RNN is very suitable for describing constitutification of the complex fluid. So there is a hidden state here, and it evolves as a function of time by depending on the input as a function of time. So this input can be the deformation as a function of time, the shear rate as a function of time, and the output should be a stress. So this is the structure of, I said, constitutive neural network. And to impose some important physical properties to the network, we should modify the structure, the mathematical structure of this hidden state, the recurrence relation. So here we added all the input, the gamma dot, to the hidden state to memorize every flow history. And here we have alpha, which is smaller than 1, which is multiplied to the hidden state every time. So the flow can forget the history of the deformation. And here we have hyperbolic tangent and constant h, which impose some nonlinearity to the model. And after memorizing this kind of flow history, we can calculate the stress from this hidden state by using neural network calculation. So we have a model architecture like this. First, we memorize the history, and I'm lost again. First, we memorize the flow history, and we calculate the stress by using multi-layer perceptron neural network calculation. And then we recombine the output values to the stress tensor. So as we have the model, we train the model by using two different types of the data, synthetic data from Gigekus model and TEVP model. Gigekus model is a famous nonlinear viscoelastic fluid model, and TEVP model is a fluid model with yield stress and thixotropy. So we train the stress data of the startup and cessation of the shear flow. And you can see that the training result is very good. So the loss, the error decreases very rapidly. So the training is there's no problem in the training. But here is some interesting result. We observe the trained value of the parameters of reconciliation. And you can see that the value of alpha, we found that the sum of the value of the alpha just coincide with the value predicted by the theoretically predicted prediction of the training data. And some, in case of the TVP model, it's again here. In case of TVP model, which has some yield stress, there is alpha whose value is 1, which means it does not forget the deformation history. So some part of the memory is solid-like in this case. So the running actually is done as we intended. And we also tested the untrained kind of data set, which is oscillatory shear flow, which is not a step shear flow. So we tested the small amplitude oscillatory shear modulus and loss modulus in both fluids. So you can see that the shear modulus shows very nice fitting. But in case of the Gijikus fluid model, the normal stress shows very weird kinks like this. So it is basically because this model structure is a one-dimensional structure. So to resolve this kind of problem, we modify again we modify the structure of the hidden state again. But you don't have to understand all this mathematics, but the hidden state is now not a scalar, it is a tensorial format. And we introduce the concept of matrix function and eigenvalue decomposition in the calculation before the calculation of the neural network. So actually this three-dimensional model has the same structure with the previous one. First we memorize the deformation in tensorial form, and we compute the eigenvalue of this memory tensor, and we compute the neural network calculations, and then we recombine the final stress output. But the eigenvalue calculation is slightly difficult, but it still works. It is still trainable. And if we retrain the three-dimensional model by using the same shear flow data, then you can see that both shear modulus and the normal stress differences are fitted very well. So it tells us that imposing the physical constraint to the mathematical structure of the model is very important to improve the performance of the model. So now we have the framework of the data-driven constitutification model, but actually it is not a very efficient model, cost-effective model, because we have to calculate every neural network computation every time and everywhere when we conduct a flow simulation. So it is very expensive. So we introduce some other model which do not use the neural network calculation. This model is inspired by this soft glass rheology model, which is a simple one-dimensional toy model describing the glassy material. And in the although it is a very simple toy model, it can describe yielding, viscoelasticity, and shear thinning, thixotropy, and so on at the same time. So we can determine the coefficient of the model to control the material property of the fluid. And I'm not going to tell the details of this equation, but what I should do is, what I had to do is that expanding this one-dimensional model to 3D and imposing some distributive properties to the coefficient of the model to allow it to describe various kinds of fluid. So we first introduced the concept of the bead spring in the 3 dimension. So this bead spring can be stretched by the flow, and the stretched bead spring can yield or reoriented by when the potential energy of the bead spring reaches the value of energy barrier E. So each spring can have the different value of spring constant and energy barrier E and relaxation template gamma naught. So by controlling the distribution of those 3 variables, we can control the material property. And the distribution of 3 variables can be described by multivariate Gaussian function, distribution function. And the 3-dimensional Gaussian distribution has 9 degree of freedom. And we additionally have one more degree of freedom, which is noise temperature X in the model. So we have a total 10 degree of freedom. And we trained the model by using Bayesian optimization. You can see that as the iteration goes on, the loss between the data and the prediction decays. And we can find the distribution of the spring constant and the relaxation time and the energy barrier value. So, and we can repeat this kind of training for Hookean solid and Newtonian fluid or Maxwell fluid, the viscoelastic fluid independently. So this model can be trained by very different types of the fluid or even a solid. So now we have the machine learning constituted model without computing the neural network calculation. And now I'm trying to develop a methodology of the flow simulation by using this kind of concept. So let me conclude my talk. I am working on applying the machine learning concept to the transport phenomena. And the first one was the early detection of the pore clogging in the microchannel flow. And it tells us that the convolutional neural network can be used, and the temporal information is very important. And in the second one, the battery slurry classification, we found that the structural information is hidden in the chaotic fluctuation of the flow signals, and we can find it. And the last one is the constitutification, the modeling. And we construct the model which can be adapted to very different kind of the fluid by using neural network or a probabilistic concept. So this is the end of my presentation, and thank you for your attention.
Thank you for the nice presentation, Dr. Jin. So any questions from the audiences about this research presentation? Yes, please.
I have a question about the pore clogging detection part. How many optimization loops did you run to update the parameters? How many loops did you run to update the parameters?
What does it mean, the loop?
Optimization loop in the pore clogging detection part.
The iteration or?
Optimization, yeah, hyperparameter tuning.
Hyperparameter tuning. Actually, that takes that much time. Actually, that can be done in a few tens of minutes. So I don't remember the exact iteration count, but yeah, that doesn't take too much time.
One more question I have. Why did you choose AUROC as the evaluation parameters? No, evaluation metric.
Oh, Because the threshold can be manually selected, so that is not very consistent for different models. So AURC can determine the performance independent of the value of the threshold.
Okay. Thank you.
Yes, please. There.
Hi, Dr. Jin. Thank you for the presentation. So I have a question on the Bayesian optimization of your SGR parameterization part, right? So you said in your Bayesian optimization, you're actually calculating the expected improvement in Bayesian optimization. Yes. So you test a random set of parameters, and then you recalculate and try again. So is it just any random sampling off the bat?
Actually, there is a heuristic boundary of the parameters. So we have field knowledge to define the range of the parameter.
Okay, so
that's all.
It's just a min to max.
Yeah, min max, and that's all.
Oh, okay.
And we randomly choose the parameters.
So you only do it one sample at a time. Like it's just one sample, one choice of parameters, evaluate, and then one choice of parameters, evaluate, and over again and again.
Yeah.
Okay, so why do you not consider like more advanced optimization? Like since you're already optimizing for the acquisition function itself, why do you not just do gradient descent onto the function? Is it very computationally expensive to optimize this?
Actually, the bottleneck of this process is the flow simulation. So defining the parameter is very small part. So we do not consider about the efficiency of the calculation.
Understand. Okay. Thank you very much.
And I think one last question will be available. Anyone from the audiences or maybe from the YouTube live streaming? If not, can I ask a single question? So it might be a bit vague or random question. So when I looked at your interpretation of the C constitutive equation, so seems like you are somewhat doing the dimension reduction and then retrieving to the high dimension. So you are trying to implement the machine learning technique to estimate the complexity or to retrieve the complexity based on the simple equation. So how do you think? I mean, sure, your model is anyway simple, but you try to make it to a higher degree of the complexity. Will that always be working, or can there be any limitations?
Yep, that's very difficult question. So what we have done is imposing a constraint, the basic common constraint of the complex fluid. So it looks simple, but the neural network computation will give us a freedom to mimic very different kind of the model. So I think that's the key concept. So I think this can be an answer for the question.
Okay, then let's thank our speaker once again. We are a bit ahead of time, but I'll try to introduce the next speaker, Professor Seung-Woo Han from Seoul National University. So actually, he had his PhD degree in the Department of Physics in the Seoul National University, and then ever since from 2004, he was working in the Ewha Women's University, starting his faculty position, and then he later moved to the Seoul National University. And since from 2013, he is a full professor in the Seoul National University. So today he will be presenting about his recent development of the 7net, a pre-trained universal machine learning force field. So let's give a speaker a big hand.
Okay, thank you, Professor Chang. Thank you for the warm introduction. So we have any? Okay, so good morning, everyone. Okay, so first of all, I thank the organizers for the kind invitation. It is my great pleasure to be here. And in fact, I also gave a presentation like 7 or 8 years ago in the Student Plaza. And at the time, I presented on the previous model, simple NN. And okay, so we did a lot of very good work using this, the simple NN, our first machine learning model. Today I'm happy to introduce our next flagship model, the 7net, which we are putting enormous amount of the efforts to developing it. It is a pre-trained model, so you can use it just right out of the box, okay, as pre-trained or with a little bit of the fine-tuning. And also it is universal machine learning force field, meaning that you can apply this potential model to any kind of the materials, including any element in the periodic table, even the actinide or lanthanides. Okay, so until the early this year, I did not believe such a model will be possible. But now I realize, as I will demonstrate in this presentation, I realize that the model now can achieve such a surprising capability from the deep learning. And using such a pre-trained model, I think it will greatly impact the material science in general, and in particular including the materials data, which is one of the main themes of this forum. Okay, so next talk. Oh, I can use it. Okay, so I can help but mention, this year the Nobel Prize is full of surprises, and in particular, I was surprised that Nobel Prize in Physics they recognized AI. Because in the physics department, I'm from the physics department, we never learned about the neural network, right? This is so simple and it's nothing deep there, but the Nobel Prize recognized it. Okay, and in this scientific background statement of this physics, this committee note that deep learning architecture are trained to reproduce the shape and strength of interacting forces with an accuracy comparable to ab initio quantum mechanical models. And with these models, we can considerably fast determine the phase stability and also dynamics of rigid materials. So they are recognized this machine learning force field and also its application in material science. And so I think that this now the machine learning force field became this one of the major pillars in the materials computational materials physics or computer science. Okay, so to begin with, in material science, it's very difficult to collect the data. Large amount of data, homogeneous and the well-curated data. The only exception might be the computational material database, and maybe that these materials projects they provide millions of the energy and the band structures of the inorganic crystals, and they are using the consistent DFT calculations. Okay, and so this is very useful. I mean, you can use it in everyday the material research, but at the same time, because they provide the big data, we can use them for the machine learning. And for example, you can make a model that predicts the energy band gap with a fraction of instantly using this big data, and it was quite good quality. And also, you can train a model using over the energy or force or stress, and that model will provide continuous potential energy surface with respect to the configuration. Okay, so for example, in this materials MP trajectory data set, the materials project team, they curated and also they extracted most of the data in the materials project as of the 2022 September. And, the data set is based on the PB functional and covers 89 elements, which is almost every element that is relevant in material science. And it also consists of the 146,000 crystal structures, and with the relaxation trajectory subsampled toward the equilibrium structure. Okay, so huge amount of the data. So we may want to train a model over this big data set. Okay, our first choice was using traditional or very popular descriptor-based machine learning model. For example, here. You represent the local environment of the local environment using a certain set of descriptor based on radial or the angular dependencies. Okay, and using some simple regression model, you can predict atomic energy. Okay, the problem of this descriptor model in training big data is that there are twofold at least. The first one. Since we need the descriptor of every combination of the elements, so if you are dealing with 89 elements, the number of the descriptors you need will be will increase combinatorially, which is uncontrollable. Okay, and the next, So suppose that this yellow atom is a silicon atom. Depending on this silicon atom is connected to another silicon or the oxygen, its influence on this central atom will be different, right? However, in this KRICT model, this is those environment outside the cutoff radius is simply neglected, and so you cannot reflect that on your energy model. So then alternative choice is graphene neural network. And here you represent whole this atomic structure using the node and edge features, and you assign the node and you also the communicate or geometry information is processed through this convolution or the message passing, and using those neighboring the environment or the information, you update your node feature. Okay, so and when you're dealing with this many multi-elements, then you can simply embed your atomic information into this node feature, and so you do not dramatically increase the size of your model. And also, by multiply applying this message passing, you can increase your perceptive receptive the field. Okay, so you can reflect, you can include those information far away from this central atom. Okay, so let me give a little bit more detail about the E3 equivalent graphene neural network. It's a NetCube model, which is our base model. And here, you first supply this atomic information, element information at 100 encoding, which is mapped into our certain, for example, 128 dimension of the scalar values. Okay. And in the interaction block, and here in the message passing, so we assign the node features, which is mathematically same as the Spraker harmonics. Okay, so L equals 0, L equals 1, or L equals 2, and also the multiple number of along this channel. Okay, and also we consider edge features in the form of the radial times Spraker harmonics. And in the message pathing in this equivalent model, we employ the tensor product. So simply this is a tensor product of Spraker harmonics, and usually the quantum mechanics in the physics, they state that you can represent this tensor product in terms of the classical coordinate coefficient as a sum of the different Spraker harmonics. So you have another set of the Spraker harmonics, which is transferred to the center atom. Okay, so this model is equivalent because you are considering not just a scalar value, but vector or the tensor values, and they are rotating or the reflecting, consistently with the E3 operation. All right, so so this is the main part of this message passing in this graph model, and also you can multiply apply this interaction, and at the final stage in the self-interaction part, you simply take out those invariant part and you put through this multi-layer perceptron to get the atomic energy, and by adding up all the atomic energy, you get the total energy of the system. Okay, and in obtaining these first order stress tensors, we use the analytic expression of the total differentiation of the total energy, which can be very easily handled by autodiff operation in the PyTorch or many library. Okay, so and there are also other types of the graphene neural network. For example, the one popular model is M3net or ChargeNet. They are based on the invariant graphene neural network. In this case, in the node and the atomic features, instead of those equivalent features, they use scalar features that depends on the angles or explicitly or by adding up all the information around this the certain center atom. And another popular model is equivalent graph attention model, and this equiformer V2, which is a favored model developed by the Meta. And here you use this graph attention, and because this graph attention usually it takes a really large resources to take a differentiation, and so instead of the back propagation, they directly infer or the predict the force and stress out of the using this multi-head output. Okay, so this model usually they don't take the differentiation to obtain the force or stress. That's the main difference. All right, so how about the 7net? The 7net is based on the native architecture, and we have a parallelize using this spatial decomposition method. And it is known that scrapper neuron is very difficult to parallelize. And our model is effectively only the one that supports the parallelization. For example, there is another model, the MACE, which also support the GPU and multi-GPU. If you compare this performance, as you increase the number of the GPUs, 1, 2, 4, 8, there's a little bit of the degradation, but it's reasonable, right? The performance does not degrade that much. However, in the case of the MACE, according to their statistics in this paper, as soon as you turn on the multi-GPU option, your performance drops dramatically, okay, and it's constant. So there's a huge gap between these two models. So our model is only one that effectively supports the parallelization. And our model interface with the LAMPS and ASC, and also we have developed a very fast D3. It's coded in CUDA, and the multi-GPU training, or it's fine-tunable as multi-threaded training, which I will introduce later. All right, so using the 7net, we trained the pre-trained model using the multi-MP trajectory data set that I mentioned before. It covers 89 elements and 146 crystals. So in total, there are about more than 1 million structures. About the hyperparameters, we adopted those values in the genome. This is the model. This also the same, based on the native architecture and developed by the Google. And so a 5 interaction layer and the different number of the channels for the spread harmonics. And okay, so in total, there's slightly less than 1 million parameters. It's quite big, the model. And in particular, we have removed the element-wise self-connection layers at the final output layer. And we did it just to save the memory, but we found that it actually helps to increase the performance in generalization. And that's one of the main reasons that you will see in the next slide, that our model performs better than other models. And so training such a big data takes a lot of the computational resources. And so it took us 90 GPU days on A100. We do not have one single A100 GPU card. And so we asked the Samsung, the counterpart in the Samsung, the SATE, and we have trained in that Samsung cluster, right? 90 GPU days. So they have, hundreds of the GPU cards, and so using the 10 GPU card is just 1 week work. All right, and about this training performance, well, I think it's quite good, considering that we are covering almost every crystal known to date. Okay, and the error level and also this parity plot in the test set is quite good. There are some of the outliers, but in some cases, this outlier, because of this, computational values that they are misconverged, or some of the cut-off radius issues, something like that, some technical, but there are not many outliers. And one interesting thing is that after training, if you analyze those atomic embedding vector 128 vector in the 3D map, and plot them from the hydrogen up to this bismuth, then it looks like a spiral, right? Spiral. So this is nothing but a 3-dimensional periodic table, right? Periodic table we see is 2-dimensional because, but if we apply this periodic condition, then it naturally becomes the spiral. And it is automatically learned through the dim net. We have nothing, no information, except that, this atom is different, right? Just purely from the learning this energy potential surface curve, then they have identified the chemical similarity among the different elements. It's quite, surprising, and yeah. Okay, and yes, pre-trained universal potential, even though it was trained solely on inorganic crystals, many groups, like the MACE, and we also, our group, we find that it can be used throughout diverse, almost every field in material science, not just crystal, but surface, and also the defects and the morph, and etc. Okay, so first of all, it has memorized, many of the key material structures and properties from the materials project, and also through the generalization from the deep learning, it can somehow generalize for the unknown structures or out of distribution. The downside is that it is computationally very expensive, might be at least 100 times slower than usual descriptor-based model, or from the classical potential, maybe 10,000 times slower than those simple model. And so this is very expensive, but this is valuable. It can replace the DFT calculations eventually. All right, so many groups have realized that this is really something new and it's something very useful. And so there are many of the models are actively developed until very recently. All right, and so there is one readerboard that benchmarking of these models. This is operated by the materials project. Okay, so there are many numbers, but before that I will explain what they measure. What is the performance metric here? Okay, so except for this SLME, these other data is just simply predicting the energy of the unknown crystal, so-called the WBM data set. Okay, so this WBM data set is made after this announcement of this MP trajectory, and so they replaced the atoms in the materials project to make another plausible crystals. Okay, and they evaluated energy using the energy and also structures using this DFT calculations with the same setting as the materials project. And so in terms of those models trained on the MP trajectory data set, this is out of distribution or extrapolation prediction. Okay, so it is really measures how much model can generalize. Okay, so they measure, so after you can computing this energy consistently with each model, then you measure its distance from those convex hole formed by the materials project data, and if it's negative, you say that you found a stable compound, and if it's positive, then it's unstable. All right, and so this is our data. So X is the DFT, the convex hole distance, and Y is the 7-net data. This the overall this R scale value is about 0.75, and so this is true positive and true negative, so unstable and stable and unstable, and first negative and first positive. And so you can also measure the classification, the performance using this confusion matrix. Like the precision means that how accurate your positive prediction. All this accuracy, or accuracy means how much you can get TP and TN, right? And so this F1 value is the harmonic average of this precision and accuracy, which is the main score that you delineate each model. All right? Okay, so you can see that our model, the 7-net, length is 7. So maybe we should have named this 1-net rather than 7-net, right? I regret it now. Anyway, so right, and so, but just one thing interesting is that above us, all these models are made a company, the big company or the startup. All right, and so if you look at this number of the model parameters, we are just slightly order of the 1 billion, but they are at least 10 or 100 times more model parameters, huge models, and so you need a lot of the research to train and also do the inference using that model. And also about the training set, so up to here we are using only the MP trajectory, but these high-ranking the models, they are all trained over the extra data set. They can make themselves over the open data set. And so this material projects, they assign and classify them as a non-compliant model because this test is about extrapolation with respect to MP trajectory. And so if you add up more data, eventually this becomes interpolation, or maybe somehow inadvertently you may include the training data or test data into the training data. Okay, so you can this is a little bit cautious data here. Anyway, so these are the facts, and Also, the one interesting thing is that the 7net is the top among those modules published from the open from the university, and we were surprised that this maze, which is very favored among the European communities, and we are scored higher than them, but we are using this even smaller number of the model parameters, right? We were surprised, right? And right, so these two models, the maze is slightly different. They are also the equivalent model, but a slightly different, more complicated architecture. So we think that, as I mentioned before, the elimination of the element-wise self-interaction operation helped us to improve this model performance. That's our understanding now. Okay, and about the model architecture, you can see that most of those high-ranking models are attention model. A means attention, and this orbital from the orbital materials, this I marked as A angstrom, meaning that they do not respect equivariance, right? It's a very, very bold assumption. So they explicitly state that we don't need equivariance, right? So in the case of the orb, if you calculate one atom in the vacuum, it is under force, right? It's moving, right? Because they do not respect those symmetry. All right, so yeah, so most of them are attention model, and this E means equivalence model, and I is invariant model. And so you can see that equivalent model is systematically or is performs better than invariant model. Right. Okay, so this Meta, right? Maybe so less than 1 month ago, they announced this is model, and Yulish sent me an email to look at their paper, and okay, so it's like, yeah. All right, so, but they also opened their own method 24 that I will mention later then, and so it is very helpful to train or improve the model. So anyway, so yeah, and so this is really competitive field, and the race is now begun. So every group is now, trying to put the resources and the data to improve the model. Right. But since with this Meta, almost all of this metric is fully saturated. So they did almost everything here, and so this MapBench discovery, they decide to add up another metric, the so-called SLME. This is nothing but measuring this thermal conductivity. So thermal conductivity is very sensitive to those harmonic and anharmonic the properties around the equilibrium, and it's very, very requires high accuracy in the potential energy surface. It's extremely stringent to measure. And you can see that now. So this SRM is basically some angle, the momentum resolved version of the symmetric relative error, which is simply measures the error with respect to the magnitude. So you can see that it's equivalent model based on 7 that performs significantly better than all other models, right? And it's a little bit disappointing that this orbital, those attention models are very high in this classification task on KRICT, but in terms of the this thermal conductivity, it has performed much badly, right? And if you look at those symmetric relative difference, the distribution in the Bayesian plot, and so you can see that the 7net and the maze is consistently close to 0 and almost the same performance, I think. And the charging, this is much better than this invariant model. And also, if you look at this orb data, it's not just this large error. Its distribution is extremely random, right? So this is because since they just simply directly. So here there's a subscript D. D means that they directly predict the force rather than backpropagation or analytic differentiation to conserve the energy, like C means that the conservative field, right? And so I think that that's so energy-wise it might be okay, but in doing the MD simulations or the Lexington structures or the very sensitive potential surface, the curve maybe I don't, it's not, I don't think this direct model is really helpful there. Okay, And also, if you look at the silicon phonon band by the EQV2 model, state-of-art model, then this black is the DFT data, and dashed line is the EQV2 equiformer data, and you can see that this is just random, right? Right. So using those attention models, you need to be careful about the MD trajectory. Okay. Right. And right. So enough about this crystal, the data. So how about other configuration? For example, here we have tested the surface reaction that is used in the area selective deposition in the semiconductor processing, and this is to estimating the energy, absorption and chemabsorption energy of the some of the inhibitors or precursors on the silicon nitride or SiO2 surface. And the absorption, this bonding is depends on the van der Waals plus hydrogen bonding, and this is quite good. This is Steve data, and this is as pre-trained, so 780 data. And this is a reaction energy, and also it correlates quite well. So a different data point means that you make a different neighboring environment, yet you have that good correlation, right? So in the surface reaction is quite usable without further fine-tuning. And since the the model was trained on the inorganic crystal, maybe the opposite material space would be organic liquid. Okay, so here we tested the binary solvent system, HDMC, and the lithium PF6, which is the commercial, the liquid electrolyte in the battery. First of all, this MD simulation works quite well. Okay, so quite stable. And also we measured one quantity, so-called the degree of the ion dissociation, with respect to the contents of the EC molecule. And so here, this is the 0 means that this lithium and the PF6, they are tightly bound, so they are not dissolved. And 1 means that they are perfectly dissolved and separated. Okay? And it is known that in experiment that as you increase the content of the EC molecule, then you have the higher the degree of dissociation. This is because simply each molecule has the higher dielectric constant in the liquid state, and so you can more easily solvate this lithium plus and PF6 minus. And surprisingly, the 780 model also produces a similar trend here. Okay, so our model does not explicitly include the Coulomb interaction, right? So it is implicitly included everything in the atomic feature. But it has a nice description of the solvation shell, and also it knows which one has the higher dielectric constant. It's really difficult to understand how the model can somehow extract those information from the organic crystal structures. Okay, so if you look at this database, training data set, there are part of the structures are similar in some of the structures in the training data, but there's no organic data. They they deliberately removed those organic data from the data set. Okay, so we do not have such an explicit description of the organic molecule, but yet you have the very good simulation of the liquid electrolyte. That's very surprising. All right, but there are still many problems, and one well-known problem, a systematic problem, is force softening. So if you look at this phonon spectrum, this is one just example, and then acoustic mode is okay, but optical mode is significantly softened, and also we can see a similar trend. Most of the crystal structures, and also surface energy is underestimated. And if you look at the region conductivity with respect to DFT, it is always overestimated, meaning that the diffusion barrier is underestimated. So these are related systematically to the data, because our training data was made of the mostly equilibrium structure of the crystals. Okay, so when the machine learning model predicts something, that it usually predicts the data mean, right? In this case, it's a 0. Okay. So that's why we have such a systematic the force softening. So, but however, the good news is that this is very systematic, and so you can somehow correct it. Also, very small amount of the fine-tuning data, And in fact, Jisoo and Jiho recently fine-tuned our the model, 7.0 model, using only one composition, azurite. Okay? And then it systematically improved all the other predictions, right? These are the lithium solid electrolyte that shares the same PS4 structural unit. And so knowledge is transferred to other configuration space through the structural similarity, right? So this is one very surprising or very promising the capability of the model. So the 7.0 is based on the PBE functional, right? How many time time? Plenty of time. All right. So yeah. Okay. So so 7.0 is based on the PBE functional, but we always want to go up the accuracy, right? Like from the GGA to scan to hybrid, or maybe eventually QMC or CSSD, right? But the computational cost to generate the data is rapidly increases as you the wrapping up the fidelity, right? And so usually there is a data scarcity in the high fidelity part. And for example, if you look at the matrix plot data, they are now supplementing also providing also the also scan data. But if you look at this, this is the energy, the count of the force of each atom. If you look at the volume and also distribution, is much smaller and narrower than the PBE data, right? So in this case, one strategy would be using this multi-fidelity training, right? So instead of the R2scan or pure R2scan or pure PBE data, since these two, the function is highly correlated, so energy surface is not completely different. So they are most of the part they are shared, but they are slightly different at a specific configuration, right? And so by training the data at the same time using both the PBE and the R2scan in the multi-fidelity framework, so this common energy surface might be learned from the large data set of the low fidelity data, while those small variations can be easily learned from the small the data of the high fidelity, the functional, right? And so we have implemented this multi-fidelity training into the 7net, and by using this one-hot encoding in this each layer, linear layers throughout the architecture, right? And so this is what we have tried. First, so this is the data from this project. Many of them are PBE, and there are some of the R2scan data. And you take some part as a test set, and we have gradually increased the training data. While we include all of this PBE data, we have slightly, increased the amount of the training data to see whether this, knowledge transfer effective can help increase the accuracy, right? So this actually is the number of the training data here, and this is a result on the error with respect to test data, and you can see that, and also when we subsample this R2scan data, we have various strategies like random or human intuition or the unsupervised learning, and any of the most of all of these methods produced a very promising result. That is to say, if you include just the 10% of the training data, then its performance is very close to those, ultimate those the model performance using the whole R2scan data. Okay, and on the other hand, if you train just R2scan data, its error is very large here. And also, if you look at the equilibrium volume, the error is much, much higher. So there is a knowledge transfer from the PBE side. Okay. And so, inspired by this observation, we trained one universal potential model, the so-called 7.MF0, using the whole set of the PBE and R2scan data of the matrix project. And we applied, for example, here, in constructing the phase diagram of the cesium, chromium, and chloride. And this is R2scan, the reference phase diagram. And this is PBE data, and you can see that many of the structures are missing, or they are classified as unstable in the PBE, while using the pre-trained multi-fidelity model, we have the right and correct this phase diagram. All right, so I heavily advertise our pre-trained model, but it is far from being perfect. It's far from being perfect. So when you use the 7net, be careful, always check with respect to the DFT calculation. So, don't trust me that much, okay? Yeah, this is just advertising. Right, so there's a lot of way to go from now. And so the current model is focused on the equilibrium structure and the crystal, and also the, from this, since it is constructed from the ICC data set, it is mostly focused on oxide materials. And so we needed to go beyond the equilibrium structures, harmonic, anharmonic, defect, and surface. And also in metal material-wise, we can also include non-oxide organic molecules. And also though we may need to increase the fidelity from the PB to scan to go upward. So how can we do that? The data, okay? So already the data was produced to improve the model performance, like OMET 24 by the Meta. They have intentionally made out of equilibrium configuration from this Alexandria database. Alexandria database was to supplement the materials project with some of the unsampled or rarely sampled elements, and also the open catalyst they provide the data on the surface. So yeah, enough data. So what's the problem? The problem is that these data sets are at least 10 to 100 times larger than materials project trajectory. So as I mentioned, MP trajectory, it takes 90 days, 90 GPU days. 100 times 9,000 GPU days. If you have a 100 GPU card, then no problem, right? So it is really, really painful to add up those data. And so, I don't know, yeah. So that's why, many of the models that they just directly to predict this force, because the force, it really takes a lot of, computation to reduce to get into loss function, right? So just training is the problem. That's what I am emphasizing here. All right, and about the perspective, and since this pre-trained model is very well already ready to be used, and I think it is very useful in industry in particular. And for example, in this semiconductor processing simulations, using this bespoke potential, then it took us almost 2 years to develop to find this training set, right? It's really painful. So industry, they cannot wait it, right? So their delivery time is like maybe 1 week or at most one month, right? And so the pre-trained model, will be very helpful for them. And this is the last slide. And I think using this, the pre-trained model, we can prepare next generation database. Like for example, so the current materials project data, they are focused on the equilibrium energy and also zero Kelvin data, and mostly metastable, not synthesizable, right? We can go beyond that using this pre-trained model. So for one thing, so using this pre-trained model, it takes just 2 days to have this energy and those data in the materials project, A100. If you have the gaming GPU card, maybe 1 week. That's enough time to get the whole materials project data. So it's really fast. So for example, we can also try to have, instead of just equilibrium structures, we can have the transport properties and defect. For example, here, this is the data of the bespoke potential, thermal conductivity versus the Bell panel and neural network, the data. And if you use this, the DFT calculations, it takes about a couple of days to have one thermal conductivity. And using this bespoke potential, maybe a couple of hours, right? And most of the time is spent on constructing the DFT training data. Using the pre-trained model, you have some of the accuracy is compromised, but it can be done a couple of minutes, right? And so you can now construct a huge thermal conductivity data set. And also final temperature, thermodynamic integration, and all these kind of things can be done very efficiently. And so you can look at this final temperature properties like a melting point. And also you can directly find those equilibrium structures from the crystal structure prediction which requires large amount of the structure generation and also the energy evaluation. Now, I think they can be done quite efficiently using this pre-trained model. Okay, so I think so maybe we can go from the materials project to the next generation material database, and it will be very helpful in material science. So with that, I conclude my talk, and I would be happy to answer your question. Thank you very much.
Thank you for the great presentation, Professor Han. So, any questions from the audiences?
Too much advertisement.
Yeah, it's a great introduction. So being a very more old-fashioned guy in the just DFT, so normally we have a good sense of accuracy, for example, in DFT. So I'm just curious, like for example, we showed the table of like, competing ranking. So I'm just wondering, is it ranking just amongst themselves, or is there some more systematic, detection of accuracy for example, I think it was like 2 years or 3 years ago, people tend to compare, like tensor or, kernel based with, let's say, gap. In DFT, you have like the flap code, for instance, right? So I was just wondering whether is there something that is, so for you get some sense of accuracy if you use something like out of the box or,
That's a really good point. So the difference is that in the case of those bespoke model, you have the training data, the same training data, but different model, and also you have the same task, right? And so you have very clear connection from the training, the model to performance, right? But this is a universal potential model, so it does not necessarily confined into the training data. So this is just crystal data, but you can test it against like the surface or or any kind of the properties that you can do with the DFT calculations. So this WBM data set, since it is reasonably close to those training data, so I think it is a basic the test of the model performance, but it does not necessarily mean that the same performance in downstream task. The thermal conductivity is one good example. It's completely, this is reversed, this order is reversed. So yeah, and maybe also the surface and those things might be different. So once there's some of the model was open at the math bench, I have 20 students, and each of them test their own application, like liquid simulation of the surface or etc. And so yeah, students have a different opinion about the performance, right? So it is really painful to get really good, consistent the feature. Yeah.
If I may just ask a very quick question, I think that's all great. I mean, that's for the accuracy, but I think the cost. So it's not clear to me now. Like in the sense you put equivariant, invariant, and this. So I'm just wondering what is the ballpark figure for the cost of calculation? Definitely, these will definitely outwin DFT, and also the scale of calculation. In terms of calculation cost.
That's a good point. So one thing is that except for the invariant model, you can use both CPU and GPU. But those other models, like equivariant model and also the attention model, you definitely need the GPU. GPU is just, you can just, throw it, right? And so first you need the GPU. And well, I think, so in terms of the A100 GPU card, if you have it, and it's a 7-net model or the base model, maybe other models as well, you can run like a 1,000 atom system and 1 nanosecond a day. So yeah, it's much faster, of course, than the DFT. However, compared to other bespoke potential or other classical potential, is much expensive. And so yeah, so computation cost is definitely, and it is about Maze and our model, and other models might be, or they claim that since they just directly predict the force, and so the cost of the backpropagation is eliminated there, and so it is faster a couple of times than maybe equivalent models, but then you have this compromise in the force, and yeah, and so, but anyway, so the computation cost is definitely very high, and one problem is that it's not really about this architecture. It's about this architecture. This tensor product is is, of course, matrix and the vector multiplication. However, matrix is so small, and it does not saturate the GPU, right? And so one example is that when we test our code again with H100, like this is another much faster than A100. So nominally, H100 is faster than A100, like 2 to 5 times. However, our 780 only faster 1.5 times, and so it does not fully, utilize those GPU cores. And it's very difficult. So it's inherent problem of this equivalent operation, and so we are collaborating with the computer science engineer, the professors there, to make some of the kernel, optimized for those tensor products. But there's a long way to go. Yeah.
Maybe a last question. Yep.
Thank you for a wonderful talk. So I have a question regarding this fine-tuning method.
Yes.
So my original intuition was when I put some fine-tuning trainings, then that might give us some kind of like a bias on the training data. So that might worsen, deteriorate the accuracy of the other part of the material space. But it seems that the one material training can give us some more accuracies on the similar materials. So my intuition was incorrect, or do you have any other opinion on comments on the accuracy of this fine-tuning method?
Oh yeah, that's perfectly correct. And this is our textbook, the knowledge that if you fine-tune a model, then for the given downstream task you have the better performance, but in other areas performance is degraded. That's why we are doing the fine-tuning. Like you can optimize your model parameters for a specific task that are more interesting to you. So that's the what fine-tuning is. But what I want to emphasize is that and so first, but in our case, we are interested in making a potential that can be used in a broad spectrum of the materials, not just the azurite, right? Like it's a doped azurite, or maybe some of the replaced, other compositions, high entropy azurite, etc. So making a model for that material space, you may need to fine-tune a huge number of the data set, and so this one obvious straightforward strategy. But we trying to by conserving some part of your the architecture or the part of your model space. We can do that using so-called EWC elastic weight consolidation and so replay to reduce the forgetting problems. And you can maintain your accuracy for the material space that are interesting to you. So in our case, in replaying this, we included those from the training data. We take replay with the same types of the elements or the structures, right? So by doing that, you can suppress this forgetting problem. And then you suppress the forgetting and you fine-tune a specific the materials. Then we found that this knowledge transfers to other areas, and accuracy is also going on. Of course, if we do that, then the other material space, like I can say the organic molecule, it will degrade substantially, right? But that's not our interest. So here we are trying to make a fine-tune, global, large area of the material space, and I think it works.
I see. Thank you so much.
Okay, then let's thank our last speaker of the first session.
Thank you very much.
So we will end our first session of today, and we'll be resuming after lunch. So we'll be starting the second session at 1:20 afternoon. And then, for those participants in place here, so we'll be taking a group photo before we going for lunch. So try to get together at the front.
And also there's additional information for the lunch. So for those who registered for joining lunch, except for the speakers, we prepare the lunch boxes on the 3rd floor. You can get a lunch boxes and then coming back to this hall. For the speakers and chairs, we prepare the same lunch boxes on the 2nd floor. So we will have there, and then okay, thank you.
I want all the lovey-dovey sex. Rent out with the lovey-dovey sex. With you, I want it all.
앞으로 나와주세요. 그룹 단체 사진 찍고 이제 점심 먹으러 이동할게요.
I wanna drive all night, wanna take your private jet to the sunny mountains, wanna make you smile with you, I want it all. You got it, got it, got it all. Your body to your smile, want you to my own. And
to maximum 2 minutes for our guests or audience from outside to come in. Yeah. So I've spoken to a couple of our international guests. Some have been here before. Some have been here the first time. If you're here first time, welcome to Korea. Yeah, and leading on to this, today we have 3 speakers in the second session. One from the Nanyang Technological University in Singapore, so that got me really excited. So by the way, I'm actually Singaporean. And so we will look forward to listen from Dr. I need to say this really, really correctly. Jose Rakatala Gomes, right? So Dr. Gomes is actually, so I'll just introduce him, by the way. Okay, so he did his bachelor's in chemistry and also his master's in advanced materials in Spain. And then he continued to do his PhD in chemistry at University of Southampton. And now he's actually a postdoctoral fellow at the School of Material Science and Engineering at Nanyang Technological University. So today, he's going to tell us a bit more about the work that he's doing on combining AI and high-throughput experiments towards inorganic materials by design. The stage is all yours. Let's give him a round of applause to encourage him.
Hello. Okay, shall I crack on? Sure. Wonderful. Thank you so much for the introduction. I didn't know you were Singaporean. This is very appropriate. Thank you. Hi, everybody. My name is Jose Recatala Gomez, but everybody calls me Pepe, so just Pepe is okay. Today I will be talking about combining AI and high-throughput experiments to design new inorganic materials. I am an experimentalist by training. I have a degree in chemistry. I don't know if that means that if I'm a chemist or not. And I come from NTU, from the School of Material Science and Engineering, and I am very happy to be here representing the group of my advisor, Professor Kedar Hipargaonkar, who is an associate professor in the department. And so let's crack on. So why do we want to do this materials discovery? Honestly, it's because it takes a very long time to discover a new useful material. I have a couple of examples here. I did not know that Teflon took 25 years, by the way. That was surprising. Why is this attributed to? Is to a mix of mismatched time constants. So governments provide funding for 4 or 5 years, perhaps. PhDs, graduate students, remain in the university for 3 to 4 years, 3 to 5 years. Residency time of postdocs is between 2 and 3 years, perhaps. And then time to actually build up a startup and develop a product that may take 10 years. So all these time constants are not aligned, which makes the discovery process really, really slow. And I really like this slide because it also serves as a very good summary of what Kedar does in Singapore. The promise is that convergence enables acceleration. So by mix and matching some AI, machine learning, high throughput, high performance simulations and automation, we can achieve close to a 10% acceleration factor. And Kedar does all of this in his lab in NTU. I highly, highly encourage you to visit his website and learn about it. It's really interesting. So one of the flavors of AI and automation sorry, that I will be talking about today is for inorganic materials, which is what I'm also interested in. We call this the MATGDT framework. So the materials generative design and testing encompasses generative design, experimental validation, and rapid functional property testing. We not only want to make new materials, we want them to be useful as possible. And this is actually quite an old idea. It was formulated for the first time in 1988 by John Maddox, the so-called Maddox Challenge. And he thought, well, if we had a large enough computer, a large enough data set, it would be possible for us to input a chemical space, say elements A, B, C, and D, and actually predict the structure from that. So how can we do that? So if you actually look, first of all, is it worth doing it? Like, have we discovered everything that there is to discover? No, not really. If you look at the inorganic material space, first of all, it goes exponentially as you go from binary, ternary, quaternary. And if you look at the possible missing compositions, there is still a lot for us to find out. And maybe, hopefully, some of these materials result useful for some sort of application and help resolve some grand challenge. Okay. So say you like elements A, B, C, and D. Given that composition, can you find the lowest energy structure, so a stable structure? And there are many ways to do that. You can use Calypso, USPEX. They all rely in sampling a potential energy landscape and finding the valleys, so the low energy structures. Some of them are higher in energy, so they may be considered as metastable. But at the end of the day, they all rely on that. So how do we do this? How do we do this in Kedar's lab, right? And I really want to advertise the work of my colleague, Dr. Raymond Zhu. He developed something called a property-directed generative design of materials. It really relies on creating a continuous representation of materials and sampling from that space to extract new materials. And we rely on databases of existing materials. I think Professor Han has mentioned Materials Project. We use it all the time. We also would like to find ground state properties, stability, free energy, and also go all the way to the end towards the applications, and hopefully go backwards. So not only you get a material and you use it, but you have an application in mind. I want something that has a band gap of 1.1 and also is cheap, so not made of expensive elements like gold. And then you go back, you sample these, and you get it. So that's what we try to do, and we try to experimentally validate this. So we try to make the materials that we predict. And very quickly, I want to talk about KRICT, which is the crystal structure prediction that we use in the group. It was published, so please go to the paper and check all the details, because I don't think I'll make it enough justice. But essentially, KRICT relies on a representation that encompasses atomic features, space group, but most importantly, Wyckoff positions. And this is a symmetry-aware method. So essentially, when you minimize, the loss function punishes very severely materials that do not get assigned the space group that you want. So that's how we, at the end of the decoder, we get actually structures with the desired like crystal structure or crystal system that we input. And we also have a rapid DFT validation. A colleague of mine developed it, so please go ahead and check the paper. So essentially, all starts here. We are domain experts, hopefully. So I did my PhD on thermoelectrics, so I kind of understand thermoelectrics a little bit. I know what materials can be good thermoelectrics, and I can see what structure it is. I like rock salt materials, for instance, right? So we fix that space group. We give a possible list of elements. We encode, and we sample the latent space to decode certain materials that are of interest for us, and then we go ahead and try and make it. And this is the results. This is how it looks like. The first question would be, are these materials stable? So we obviously check for phonon stability. And the high-ranking materials tend to be phonon stable. There is a little bit of an error, but I'm told that there's a numerical error that can be fixed with a higher level of theory. After this, we go ahead and try to make this, try to realize it in the lab and see how accurate the model is. But first of all, I'm actually very happy because Professor Han mentioned the Nobel Prize in physics, right? We get asked a lot, like, how far are we from AlphaFold for materials discovery? And my personal opinion, I'm happy to have conversations if anybody disagrees, is that we're almost there. We're really almost there, right? Like, we have genome, 2.2 million new crystals, open materials, another. There is an abundance of data here, right? I do think, and by the way, this was prized with the Nobel Prize in Chemistry of 2024 for the Hassabis and Jumper, right? So there is a lot of value in this. So we're almost there. And this is one of my conclusions, but I'll tell you now what we think in Kedar's group the problem is closing the gap between simulations and experiments. So this is what we are actively working on, and I would like to show you two examples that we have done in our lab of AI-generated materials, crystal structures and compositions, and then the experimental validation that we have tried to do, and what we have learned from it. So hopefully it's useful. So yeah, let's test it. The first example I would like to show you is the curious case of copper tin selenide. There is a cloud, and it's black. It's an omen. You will see at the end. But essentially, we utilized KRICT, and we got this material. We tested whether it was phonon stable. Yes, it is. It is a metal because the Fermi level is in the valence band. So, okay. When we looked into the possible oxidation states, we thought, oh, but this may not be possible. And then we thought about it from a very purely chemical perspective, which is like, okay, so perhaps in the presence of selenium, this oxidation state preferentially forms because selenium is more reducing environment than oxygen. This has been observed in tin halide perovskites. So we thought, let's try and make it, see what happens. So we looked at the energetics, and this is the Hall. So what we found that at a certain level of DFT theory, it was thermodynamically stable. But it had two competing phases very close in energy, 30 MeV. The thermal energy at room temperature is 26 MeV. So we thought, okay, 30 MeV is fairly accessible for us. We'll try and do it. And when we checked the literature, we immediately found that these two phases have been experimentally realized. Wonderful. One of them is a semiconductor, one of them is a metal. So we thought maybe we can access these. And I actually need to show you this because we have invented this technique in the lab, me and another PhD student. We call it 6S, and it basically results in self-sinter material. So you have a powder mixture, you pass current, it relies on Joule heating. At the interface between a heating element and your powder, you actually have a contact resistance, so heat propagates this way. And this is real time, by the way, it's not accelerated. At the end of the day, you will get a pellet of a almost fully densified material. Since we like functional materials and we are interested in electronic properties, this is very handy because you don't need to press this material. It's already ready for you to measure the electrical conductivity or the resistivity, whatever you want. It has fairly high throughput. We can make 10 grams of pure single-phase material in about 39 seconds. So we use this a lot because a lot of our materials are either semiconductors or metals. That's what we do in the lab. So we can rapidly make it and test it. And that's a pretty good advantage for us, to be honest. So I tried to make this. It took 24 seconds. And I found out that when you look at the EDS composition mapping, I had formed a ternary phase. It was fairly well distributed. It had no clustering. When I conducted some structural validation, I found that this was the majority phase, and I was missing some tin because it happened to be oxidized. That will happen sometimes, especially in Singapore, where it's rather humid. So this was encouraging, but not enough to prove that we had made it. So we looked into transmission electron microscopy. We found some grains, and we had found two different phases. But when we tried to match them, we got no preferential matching. Like everything matched equally well, both our target phase and the competing phases, both of them. So again, we did not get an answer for this. So we looked into transmission electron microscopy composition, and we mapped some grains. The first one, we got a fairly good agreement with our target composition. The second one was perhaps a selenium deficient competing phase. And the third one honestly made no sense. We didn't know what to do with it. So we had a broad mixture of phases, but they did not appear during structural refinement. So we didn't understand what have we made. So we also did some electron backscattering diffraction. We got the Kikuchi bands, and we matched them to our phases, and we got a preferential matching for the target phase, but it was not such a preferred match. So still, we didn't quite understand what we had made. So we did electronic transport. Remember, like we got a pellet directly, we just cut it and measure it. So it was metal because the conductivity decreased as a function of temperature. Wonderful, so one of the competing phases is a semiconductor. This is not a semiconductor, so that's out. So now we had our target phase and the other competing phase that was much, much higher in energy, 30 MeVs above the convex hull, right? So, okay, this means that we had made either the target phase or the competing phase. What's more odd about this is that the competing phase had been only observed at high temperature. So as I was saying, there was a black cloud. That's because I don't think we have succeeded. I think the composition is fine within error bar. The structure matching is also okay. The electronic measurements indicate our target phase, but it did not discriminate against this one. So interestingly, either we have made our target phase or we have stabilized a high temperature phase at room temperature. And we are still working on this to validate what have we actually made. So that's pretty tough. And then I want to introduce a second approach, which I like to call this is the work of my colleague Haiwen. He's been working on this for a very long time, and the paper may come out soon. He calls it the design, test, make, and analyze paradigm. So he also utilizes some AI to design and to filter different target candidates. Then there is a testing, so whether they are DFT stable, whether they are phonon stable. Then we rapidly make them in the lab. And then we spend most of our time actually figuring out what we have made. So I'm going to introduce this paradigm on his behalf. We go through a few evaluation layers. So the first one is synthesizability. I encourage you to check out the publication of my colleague Raymond on synthesizability score. Basically, from a group of elements, the synthesizability score evaluates the possibility for them to be experimentally validated by using the ICSD label in materials project as a classifier. So the way this works very briefly is you sample the different materials from the materials project, then you use a property generated autoencoder to convert them into crystal structures. Then you will check whether they are synthesizable or not by matching this. And then you get their synthesizability score, which goes from 0 to 1. So 0 means like not synthesizable, 1 means highly synthesizable, highly probable to be synthesized rather. So he was looking at the space of ABO3 perovskites because they have been widely investigated, so they are technologically very interesting materials. My colleague wanted to discover a new one. So when we parsed this, we went to the second evaluation layer, which we call the oxidation state probability. This hasn't been published yet, but you can please check out the preprint. My colleague put it up a while ago. So this evaluates the probability of a material to appear with a preferred oxidation state. And we use it as a filter to further classify most probable elements. And then the third layer was actually not conducted by us, but by Matt, who was a postdoc in LBNL in the group of Christine Persson. And he developed something called reaction network synthesis planning. So this takes into account thermochemical data and approximates transition states using transition state theory. So it basically results in different pathways for you to synthesize a material and ranks them by probability of happening. So we not only got a candidate material, we also got possible ways to make it. So it's a very integrated approach. So I'm going to present the case study of yttrium molybdenum oxide, which was the perovskite oxide that my colleague was interested in making. When we evaluated its DFT stability, it turned out to be 30 MeV above the convex hull as well. It was phonon stable, so in principle there were no indications that it could not be made, so we went ahead and, So he utilizes another flavor of ultra-fast powder synthesis, which was adapted from Professor Julian Bing's paper in Science in 2020, which essentially also relies on Joule heating. And he can, by carefully controlling the current, he can access different temperatures pretty fast. So this has a high ramping and cooling rate. So there are chances for you to stabilize different materials. The throughput is 0.3 grams per minute. So it's a bit lower than the previous one, but still, like, it's enough for you to test the structural and compositional properties. So do XRD, do TEM, do that stuff. So the first step in this, and honestly the hardest, is identifying what we've made. Most of our time is not actually spent making stuff, it's finding out what have we made. So by accessing different conditions, different sintering conditions, the XRD pattern showed several differences. And at some point, by using different reactions given by the reaction condition network, we find that some unidentified peaks appeared for 2 of them. So we decided to investigate these further. Generally speaking, new peaks in the diffraction pattern means different compound. So we conducted some what we like to call high fidelity analysis. This is quite slow, and it's not possible to be automated at the moment. But essentially, we found out doing TEM that some rods seen here corresponded to YMO3. They were phase pure, and they sort of matched the target composition of 113. The unit cell turned out to be orthorhombic, so this was very, very encouraging for us. The XPS also showed the possible oxidation state that we expected, so we decided to evaluate this further. And so we resorted to do something called micro-ED, so microelectron diffraction. And the way to do this was we used EDS stem to separate single crystallites made in the sample that had no other contamination from different crystals. And then we actually did this in collaboration with Bruker in Germany. We actually sent them samples for them to measure and help us analyze. So the way it works is like they collected data from -70 to 70 degrees. It's quite well known in single crystal, actually. And they try and get the solution, which for us was a unit cell. Because if you remember, yes, the composition matched, but the unit cell did not. So that was, this disagreement led us to do further work. And then once you get that, we got all these possibilities. And there's a lot going on here, and I'll do my best to explain it. This is the solution that we found, that our collaborators in Germany found. So this matched a 4411 PBA2 solution. Ours was definitely not the same. So we said, okay, it is not the same. And looking into the ICSD, we found a very similar structure with a different space group. So is this a novel material? Is this a new material? Well, when we had actually refined the unit cells and looked into the validation errors, we did find that, the fitting for PBA2 and the fitting for PBAM was marginally better. There was no better matching for them. They were almost exactly the same. So we decided that, well, sadly, this must be the preferred solution, and we just mismatched the previous experiment. So when we went back and looked into the energetics and all the sample compositions that we made, we find out that if we actually recalculated the whole with a different level of DFT theory, we found that no, maybe this material is not as low as we thought, maybe it's higher in energy. So in all honesty, did we succeed? Well, also no. But what have we learned? Have we learned something? Did we actually, are we any close to succeed? Honestly, I will leave this here, but I would like to stress out this. I think that the gap between generative models and experimental validations need to be closed for us to be able to actually realize new materials. And I would agree perfectly with Professor Han in what he said before. The data is very critical, so building actual databases for functional properties needs to be done. And hopefully the rapid experimental techniques that we develop can help with this. And honestly, all I have learned so far can be encapsulated in this quote here from Professor Christine Persson: making materials is not for the faint of heart. It really isn't. After a year and a half of trying, I wouldn't say we succeeded much, but I believe that the framework is appropriate. I also think that it's a matter of time that we succeed. So hopefully, in the future, I can come back and show you a material that has actually been made and realized in our lab. And with that, how am I doing time-wise? All good? Wonderful. With that, I would like to thank Kedar for the opportunity to come here, the speakers, for inviting me as well, and all the people that have actually contributed to this work. My colleague Raymond, who developed YCRIS, my colleague Nongwei, who does the DFT, Cheng Wang, who helped me develop the high-throughput synthesis technique, and on our collaborators both in Berkeley and in Rigaku that helped us solve the data, and of course, the funders who generously helped do this work. And please, here's Kedar's email, his LinkedIn. I'm also happy to answer any questions for you or direct you to the people that can. I highly encourage you to visit the page and look into our work because you may find it very interesting. And with that, I would just like to thank all of you for your attention.
Thank you very much. Let's give him a round of applause. All right, this presentation is open for discussion. Any brave guy person to actually have a couple of questions? Well, I will encourage, yes, please. So maybe you can use the mic, yeah.
So I would like to ask, when you did the convex hull construction and stuff, and you find that a material, let's say, is 30 milliV away from the convex hull. Of course, this is the solution for zero temperature, right? So this means that there are a lot of entropy contributions that take into place. And the easiest one of them, for example, is the structure entropy. Did you try to come up with some sort of number how much this can be for the specific material? Because, for example, you can add this entropy and go, like, let's say, to 10 milliV, which is synthesizable more or less, like if you increase the temperature a little bit.
Good question. The answer is no, we did not. Perhaps we should have. Also, very important is to consider the disorder in these materials. Honestly, we can only predict like perfect crystals, right? Predicting a disordered material is quite complex. You have to build a supercell and so forth. So we did not do it at the time. We did it a posteriori. So we're trying to like get some numbers right now. So we did not do it. We should have done it before, but we thought, okay, this is a good enough solution for us to kickstart. And because our experimental validation is so fast, we can actually afford to do it before running the numbers. But yes, I completely agree with you.
Great. Any other further questions from somebody's hand is up yet? Christina? Or maybe it's faster for me.
Thank you. Thank you so much. A couple of questions, if that's all right. First one, have you been able to put back your results into your models and sort of bias your models in a different way?
Yes, but the problem is that we only have very little points. We need a lot more data. We need to fail a lot more for this. It's not single shot, right? Like, so it would be wonderful, but the results haven't changed that much.
Sure.
So we need to,
keep doing it. So my next question is kind of linked to that. Have you been assembling your data in accessible databases?
Of course, yeah.
Great.
We are curating it in-house at the moment. We plan to publish it, of course, so other people can benefit from our work. So yeah, we put a lot of emphasis in structured data, because honestly speaking, a lot of the time that we spend doing this is like making the data machine readable and making it useful, like getting meaningful results out of it. So yeah, we dedicate an enormous amount of time to that, yes.
That's great, thank you.
Thank you. Any more further questions? Maybe one from Joshua?
Great, wonderful talk, and really very careful work, on tracking this down and trying to confirm your predictions. I wonder if you could speculate. What do you think is the weakest part of the prediction pipeline? In other words, like where should this community be trying to focus their efforts to bolster the prediction strength?
First of all, thanks for the compliment. I appreciate it a lot. It's very kind of you. I don't normally like to speculate, but since you asked me, I will. I think the main problem is the synthesizability score. Having a better, along the lines of the previous question, right? Like, how much of this reflects actual synthesis conditions? There are entropic properties that are not included in the prediction. There are defects that are not included in the prediction. Disorder, really hard to tackle in real materials, right? So for instance, like I highly believe that the copper tin selenide that I have shown you is simply an ordered version of a disordered material. Whether this is a new material or not, it's not for me to say. I don't think so, but I don't know. But definitely the synthesizability needs to be improved. That's where we should hammer down the hardest. Yeah.
Great. Any further questions from the audience? No? maybe I'll just run a very quick question. So I think our group is actually also very much interested in surveying the potential energy surface and yada yada yada. And I think you actually mentioned the point briefly on matter stability. That also links to the prediction of synthesizability, right? So I think these are also very new and exciting areas that are being sought after by other researchers as well. So is it always the case that we are searching for the global truth? Or sometimes metastable structures are by themselves a class of their own, and they have their own functionalities as well. So what do you think? I mean, from a synthetic or from a synthesis point of view.
So it's a really good question. I'm not sure if I can fully answer it, but I'll try. From my perspective, I'm really interested because metastable compounds can be completely different from thermodynamically stable compounds. So different may mean different properties, which can be interesting. So I don't really know whether they are a class of their own, but it definitely should be treated as a class of their own. I don't know if that answers the question.
All right. If there are no further questions, please join me to thank the speaker again. Thank you very much. Great. Shall we, Katerina, maybe we can start to come on stage. So let me first introduce, it gives me great pleasure to introduce Professor Katerina, and I would like to pronounce the name correctly, Christofidu. Great. Okay, so she comes from the University of Sheffield, and now there's a slight twist. We'll be coming into modern digital metallurgy. All right, so before she starts, let me just give a brief run through of her her career. So she actually came from Imperial for her bachelor's, a PhD at the University of Cambridge, and then she started her lectureship in 2019, maybe quite challenging times, at the University of Sheffield, and now she is a professor in digital and sustainable metallurgy. And also, I was just looking through her CV, and she actually is a great advocate for women in STEM as well. Good for you. So without much further ado, the stage is all yours. Please welcome her.
Thank you. All right. Thanks, everybody. Hopefully everybody's still awake and had some coffee after lunch. That was wonderful. I couldn't have done a better job introducing my talk than Pepper did earlier. So thank you. I'm going to use a little bit of what you said to kind of cue us up a little bit. But before I do that, just a few shout outs to the people that made this possible. This is very much not just my own work. A lot of people put a lot of time and effort into this. I particularly want to shout out Alan Thomas and Shanyuan Liu from the Sheffield AI Research Engineering team that have been doing a lot of the background work on this. And we've got this great initiative in Sheffield where we actively encourage computer scientists to get in touch with domain experts in different fields. So we've been working very closely with that to kind of teach each other, which has been going really well. So I'll highlight that. And then at the bottom there, a little bit of funding. The Henry Royce Institute is the UK's national research institute for advanced materials research. So a lot of the work that we do comes under that umbrella. And then a couple more shout outs to other people that have been doing a lot of this work. Professor Nicola Morley and Professor Haiping Liu have also been involved in this work. Josh Berry, who's here as well, has been doing a lot of the machine learning in the background, applying these databases to what we're trying to do. So kind of queuing up, how do we end up kind of extracting properties and databases from scientific literature using large language models? My group looks into the intelligent design of engineering alloys. Basically, everything that we do is understanding how we can create new materials for industrial applications, right? As Pepper showed us, it can take 25, 30 years from inception to actually getting a material into service. And that's not a timescale that we can actually tolerate for much longer, right? When we're talking about engineering alloys in the aerospace industry, the qualification process itself can take a decade. From the time you've agreed on a material to certifying it for flying, it's an impossible time frame, right? So when we start talking about new materials for aerospace, for hydrogen jet engines, for electric cars, for fusion energy or new fission reactors. All of that we can't really wait 25 years for. So AI and machine learning are incredible tools to help us design new materials, and that's how we ended up into this. Biggest problem we have, we don't have enough data. Right? So we've been working with steel, we've been working with aluminium alloys, titanium alloys, all of that. We've been concentrating in a tiny, tiny little area of the periodic table and kind of just going around in tiny little circles in it. And we don't have enough data to kind of innovate beyond that. We're kind of interpolating within a very small space. So a class of materials that's kind of allowed us to think a little bit outside the box is high entropy alloys, complex concentrated alloys, multi-principal element alloys, whatever term we decide to use at this moment in time. Basically materials that don't rely on a single element as their base. Right? So we use multiple different elements in equal-ish compositions, or many kind of, there is no element that takes precedence over the rest. So this field kind of came about in the early 2000s, 2004, 2006 or so. They were the first kind of reported documentation about these types of materials. They're very much alloys, but because we have so many different elements in such high concentrations, we have an entropic stabilization of simpler phases. And we can use that principle to help us design and target specific properties. For example, we can use much higher chromium concentrations to improve corrosion resistance, whereas normally we would be limited in the chromium concentration because it creates deleterious phases that will be problematic for mechanical properties. That sort of idea. So this field has been growing and growing and growing exponentially. So this is just a graph of the literature just from 2016, right? So from 2016 to now, and we plotted this back in July, I think, when we did the last count, you can see the number of papers is just growing massively. And all of these papers are reporting new materials, new compositions that they've made, new manufacturing methodologies, which can also be very important for us on how we can control the microstructure. But we're not using them, right? We've got thousands and thousands of papers. All of them have usually more than just a single composition, more than just a single alloy. And we're just leaving them be. Maybe we survey 10, 20, 30, 100, 200 in a year. Nowhere near the thousands that we see there. So how can we use these materials and these papers, how can we use the literature in a much more profitable way for us to construct the databases? That's basically where we kind of ended up in this field. The databases that we do have to play with are very small, and they're very biased towards specific kind of regions of the periodic table as well. So what we end up with is basically applying really fancy techniques to things that are just going to give us the same answers that we already have. So we went about using large language models effectively to extract information from the literature to help us build up the databases so that we could do some deep learning or some more meaningful machine learning, applying more meaningful machine learning to the design of materials. Some of this was motivated by our existing projects. So we've been working with the automotive industry to design corrosion-resistant coatings, for example, or working with tooling companies to create new tooling materials for metal cutting, right? So very practical applications, which then gives us a very strict set of materials properties that we're looking for. So this is the methodology that we've been following, and the first thing that we wanted to do was to take a couple of the existing databases that we've been using and use our methodology to basically recreate those databases from the exact same papers to see how well we're doing compared to a human person that spent hours and hours creating a database. So we took two databases that we've used previously. The Machaca database was published in 2021, and it includes about 1,300 data points from 670 different materials. So still quite small, but that's actually one of the largest databases that we have, right, for this materials. And then we have the GHOST database, which has 380 or so unique materials from 75 papers. The reason we picked those two was because the first one gives us a lot of information about the different phases, the different crystal structures that we see within each material. And the second one gives us a little bit of hardness information as well. So it has a little bit more than just the phases. So we wanted to just have a play and see how well we can recreate them. So the main thing was, how do we apply large language models to extract data from this growing literature field, and how can we rapidly assemble these new data sets? So we have this sort of framework. I'm going to go through it sort of bit by bit and see where we are. So our first kind of step is to collate the PDFs from these databases, make sure that we have all of the original papers so that we can apply the large language models too. The next step, which proved to be a little trickier than initially we thought it would be, is converting the PDFs to raw text, right, so that we can run the large language models on. We had a little bit of cleaning. We followed a couple of different strategies. That actually matters a little less now, and I'll come to that later, because we've seen newer and much larger models that are able to handle text without needing as much cleaning. Then we worked on prompting, and I'm going to show just the prompting strategies today. We're currently working on fine-tuning as well. And then we did the comparisons just to understand how well is this working and how well can we recreate the original databases. So first step then, converting the PDF to raw text. Right? So this is just one example from the papers that we had in there. Looks nice and lovely from the typesetting. We're all very familiar with these. Well, this isn't very useful for a model in itself, right? So we need to convert this into raw text as a first step to what we're doing. And there's a few tools out there that we can use. PyPDF is actually a very common one, and this is what that exact page I just showed you looks like once we pass it through PyPDF. There's a lot of information we don't need. There's a lot of random information, a lot of putting in things like that from the bottom of the page, and all sorts that are going to just confuse the model, right? And this doesn't work at all. So we played around with a few different tools, and thankfully our friends at Meta have actually trained a specific PDF to raw text model called NuGAT. They've trained it on archive papers, right? So they've trained it on scientific papers, and as a result, what we get is a very nicely structured raw text format. It looks a little bit like if you write in tech, so that gives you basically your tech distribution back, which can also be fun if you're trying to convert something from that perspective. So this is now much more useful for us to use in the LLM models. The other really useful thing about NuGAT, it converts tables back to something that's actually very readable, right? And a lot of, I mean, I'm sure everybody knows this, we hide a lot of information, or make it a lot easier to read in tables and in figures. We're trying to handle the figures currently, and there's a lot of new tools that are coming our way to help us with that, but this is already very valuable, taking the tables and converting them back into text that we can use as well. So super helpful as well. There we go. So the next part that we were looking into, and we started this work about this time last year, the LLM development in this time has been enormous, right? So when we started this, we couldn't put a full paper through the LLM and use it effectively. So we had to come up with some good techniques to clean the text. That's by no means wasted effort, because it taught us quite a lot of things on how we can split the text in different ways to improve our accuracy as well. But we tried to clean the text, removing the abstracts, for example, or removing the introductions, where you might get a little bit of confusion by referencing data in other literature, so confusing exactly where information came from, that sort of thing. So we tried some cleaning as well to see how that would affect our accuracy scores. and how effective it could be in helping us be much more precise. So from then, we went into the main bit, which was how do we use the LLM and how do we design our prompting to then give us back the information that we need. In this case, we were trying to recreate existing databases rather than extract new information, just to make sure that we knew what we were doing and we were happy with the results. So the first step in all of this is splitting the paper, depending on the tokenization ability of the model. This we can now handle a lot easier, right? There's models that can take the whole paper and we don't need to worry about splitting. But there's still reasons why we might want to split to improve accuracy. So we started out of necessity, but there's a lot of attention that we can provide if we split the paper into specific parts, right? So we tried some splitting to understand what that would do. Then for each part of the paper, we could start our prompting, kind of engineering from there. So prompting the LLM to extract the information that we were interested. So as a first step for us is, what is the alloy composition? And that in itself is not straightforward, because as a metallurgist, we have 50 different million ways of writing out what a composition is. It might sound simple, but it actually isn't, right? There is no standardization, and we often end up in a mess of how we present it, particularly in the high entropy alloys, complex concentrated alloys field. So extracting the alloy composition, and then extracting the relevant phase information for those alloys. So what phases were formed in the material crystal structures and the like within that. And then we did some prompt validation from there. So we had a couple of different methods to do that. We had just a hard-coded validation check, which is much faster, and it avoids repeated processing through the LLM. But that doesn't necessarily teach the model, right? So that can be nice and fast for time, but it can be a little bit less accurate again. And then the next one, follow-up prompting, which gives us slightly better performance. And I'll show you some of the results in a bit. And then concatenating all of the model responses, removing duplicates, all of that, so that we can then compare to the original databases. So extraction prompts then, they're very easy, right? We were very specific. We weren't looking for anything too specific, but when you think about the properties that we will be interested in general, things like conductivity or resistivity or all of that, you can very easily prompt the model to do that. And if anything, the phase information and the alloy composition are two of the most complicated ones we could ask. Maybe moving into oxidation and corrosion can complicate things a bit more, but these are quite complicated by most accounts. So we're just telling it to extract the alloy, phase, and hardness information from the paper, and then it's very helpful to give it a JSON schema to do that with, just because it's going to help kind of concatenating your results at the end as well. So the alloy, you can give it some examples. You can tell it, you want to always have the hardness as a value, and in many cases when we're looking for more difficult properties or less popular properties, we'll often have a null value there. So making sure that it's able to return that is a useful exercise. And then in this case, we wanted to simplify a little bit the phase extraction to match what the original databases had in them as well. So again, we can give it possible values that it has. So that's what we had based on the databases that we were working with. So you can give it that and ask it to compare effectively. So if you're not, then having a value that looks like that, then it can go back and revalidate itself. So this is the validation prompt then. So we say, hey, you just returned some results. They don't quite look like the results that we're expecting, so can you go back and double check that you adhere to what we told you? So if, for example, you have an intermetallic phase, that can have lots of different names, but we didn't allow it to differentiate between all the different types of intermetallics. We just classify it all as one, again, because it was, we were trying to compare to existing databases. So you can go back to that and ask it to make sure that it's giving you values that adhere to your scheme. So from there, it will return the updated JSON objects from your structure. So quite easy validation, right? You were not doing anything. It's just a normal question that you would ask. If you were extracting the data manually, you would ask these questions to yourself. So that's exactly what we're doing. So just as an example, this is a paper we were working on, and we were just trying to see how well does it do it if we try a few random examples and see what's going on. So here's our alloy, right? You'll see that it doesn't have any amounts, right? So that's already one of the problems. In this case, it's an artifact of the field. If it doesn't give you the amounts, you assume that they're the same. So you would take the number of elements, and 100 divided by the number of elements will give you your amount. So all of that you have to kind of hard code in somehow. But it returns the alloy, which you can then get it to give you the composition. And then it finds all the key information within the text and tells you, hey, this alloy is a single phase FCC solid solution. So that's your phase information as well. And it returns FCC. So great, we're doing a good job already. LLM model choice. We dwelled over this for a long time. We tried a few different open access ones. We wanted to make sure that whatever we built will be available open access to use, because that was one of our key kind of objectives. So we ended up going with Llama 3.1, which came out in July or so. And we started testing on 3.0, which had the 1 billion and 3 billion, which are much smaller, and we had lots of issues with the tokenization there. But the 8 and 70 billion Llama 3.1s, were much, much better. So we could go all the way through this and see what was going on. So some of our results then. So I'm gonna start with showing you the comparison results between the two databases. So this is our first larger database, right? Looking at phase and alloy composition. So we want to be up here. So we've got a precision score on the y-axis, and we've got a recall score on the x-axis, and the color coding is the F1 score, right? Basically, we want to be 111 on everything. That would be ideal, because that would mean that we're extracting the exact same composition, the exact same phase as there is in the original database. So a lot of our results are kind of concentrated in this upper right-hand corner. A lot of our results aren't, right? There's almost a straight line dependency there. But very positively, a lot of it is up there. And if we look at the accuracy in F1 score specifically, so this is for recalling the alloy composition, and that's the alloy and the phases correctly, we've got about 70% or so, both accuracy and F1 scores. And then that comes down when you combine the two things, as you might expect, right? So in some cases, we might have the phase correctly and the alloy incorrectly. In other cases, the other way around. But very positive results, right? This wasn't any extreme level of coding or anything like that. If we look at the Gorse database as well, we've got similar results, slightly worse for this database, right? And this concentration up here is a little bit lower compared to what's going on at 000. But the accuracy in F1 scores, very similar overall when we average it out. 70% or so, we're dropping down to 50%. So across the board, very similar results. What was really interesting, looking at this manually, the majority of our issues aren't actually to do with the model. The majority of our issues come back down to the human that assembled the database. So we picked out quite a few of the results that were off, and were giving us 000 scores to check them against the original papers, and those results were actually written out wrong in the database that we were using. So although that actually gave us a lot of confidence, not so much in the data that we've been using for a long time and taking as gospel, but much more confidence in this is actually working pretty well, right? If we're able to get to 70% accuracies already and not struggle too much, we could be getting somewhere quite quickly with this. We also tried to see what the different models, the different sizes of models would do to the data. None of this is surprising, I don't think. So 8 billion versus the 70 billion. What you can see there, maybe if we take just the green ones on the right-hand side, which is the alloy end phase information together, you'll see a bigger concentration on one, on the 70 billion, and then we've got a slightly bigger concentration lower down for the 8 billion one. Right, so larger model, better results. Hooray! If you've got the time to do it in, this didn't actually take very long for us. We've got fairly small data sets in this case, but it took us a couple of days to do this one, for example. Prompting strategies, then. The hard coding versus the prompt validation. I mentioned that earlier. Basically, prompt validation is a lot better for cross-checking your results compared to hard encoding it. Yeah, we get the 70% or so and the 50% or so for the alloy plus phase compared to slightly lower results for the hard encoding. But if you're short on time and you have a huge number of papers that you can get through and are happy to sacrifice some data, the hard encoding will be a lot faster, right? And you won't need the prompt validation as much. Split sizes. Now, this was quite interesting in some results. And it's going to be even more interesting when you start expanding to more difficult properties that you're interested in. So the split sizes, here we use 2048, 4096, and then the full paper where we could, right? In the 8 and 70 billion models, the full paper is very, very doable, right? You don't need to worry about it. But it's interesting to see that in accuracy, the full paper is always less accurate than anything else, right? So the model starts to get a little confused with some of the things that you might see in the introduction in particular, where you have some more information that might be pertaining to your results, but you're confusing it a little bit because it doesn't know it's an introduction. It doesn't know that some of that data is coming from literature. F1 scores, other way around, right? And that's interesting. And again, that will be a lot more valuable when we start thinking about the more difficult properties like corrosion, the more classification-based tasks as well. Cleaning strategies. This, again, is coming back down to how do you split the paper in some respects and how do you focus on specific aspects of the paper. But the basic cleaning is just as good as the detailed cleaning, basically. The hit that we get is not enormous, and we're able to handle it. So if you're, again, keen for time, basic cleaning, way better. So what are we doing with all of this going forward? So we did a lot of the work based on prompt validation. The next obvious step is to fine-tune the models themselves, right? And that can be very useful when we are thinking about giving that extra boost in the scores and getting models that can run much more independently from that perspective. So we now have a couple of different things that we're trying to do. Llama also released their mobile models in 3.2, the 1 billion and 3 billion lightweight models that you can run in theory on mobile devices. The initial results aren't great for these, right? We might expect that. They might be okay for 1 or 2 papers that you're able to cross-validate yourself, but they're not great if you're running through full databases. But the really exciting thing, we've got some vision models that have come out now. 11 and 90 billion vision models that can also use image reasoning and captioning. All right, so that becomes a game changer for extracting information also from figures, which a lot of us know that's where a lot of the useful information is gathered. So we're expanding all of that prompt validation work into some of these larger models. The next step is the fine-tuning, right? So fine-tuning the actual models. It's way more computationally expensive than the prompt validation, right? But the biggest issue that we're having with the fine-tuning is that we can't fine-tune on the databases that we've been using because they're too small. right? So the next big thing is, how do we do this and still be able to compare against something tangible before we can expand it into much larger things? So we've been gathering all the open access databases that we're aware of, and that's given us about 2,311 entries for phase information, about 900 entries or so for hardness, which is doable. We would have liked a little more, but actually we can probably fine-tune based on that. So far for the fine-tuning, the training is the most time-consuming bit, right? We've heard about that already. It's currently training. We left and it was still training, so it's going to take a little while. It requires a lot of post-processing, right? So whereas in the prompt validation, you can do a lot of things in the prompt lines, in the validation itself. In the fine-tuning, you have to kind of harden code a lot of that, and you have to kind of anticipate all the different things that might happen with the alloy compositions, the way that you present phase information, all the different ways that we describe exactly the same phase, right? We can say FCC, we can say A1, we can give it the exact ICSD entry. There's so many different ways that we can provide the same information. So all of that, we kind of need to anticipate in the fine-tuning. The other key issue, and I think we've got to talk about this later as well, is standardization of the data, right? All of this is coming down to a very, very key issue in standardization of how we present data, how we talk about data, and how we then tabulate or put in figures and all of that. And the fine-tuning is going to highlight a lot of issues that we're having with that. But we want to still do it just to demonstrate how the comparisons work and what we can do with just the prompt validation. So, I've already covered the future work, but just a few conclusions. Overall, this started as a bit of a side project and it's ended up being a very valuable thing that we're doing and we're going to expand a lot too. The results are very positive. One of the things I didn't really talk about that we were very excited when we saw, the model also starts to extract information about the manufacturing without even being asked. So if in the same paper, for example, we had two compositions, the same exact composition of alloy, manufactured in different ways, the model returned the manufacturing method as well, which is a huge win for us. Because often when we design metals, we need to think about the manufacturing as well, and that affects the performance. So if we're able to extract information about the manufacturing, we can make the databases useful not just for materials chemical design, but also for manufacturing design, which would be remarkable. There's a huge potential to expand to additional properties, which is what we're doing. Basically, we're going to target, in particular, oxidation and corrosion resistance for some of the things that we're actively working on, and also magnetism. There are challenges, standardization being the key one, but it is positive, so we're excited. And with that, I think I'm about on time, and I'll stop there. Thank you.
Great, thank you very much. Presentation is open for discussion. Any questions? Maybe Professor Han?
Yeah, thank you for the very nice talk. I have two questions. The first one is that you mentioned that the vision model might be promising, but I think that vision and the language model are quite different. So why do you think it is promising?
They are. We've tried a couple of small things just to see what it could do. It seems like it's going to help us with extracting some information from some of the figures in more detail, which we haven't really been doing very much. And a lot of the information in the databases that we've seen is extracted from figures.
The second question is that, did you try ChatGPT?
We did at the very beginning, and we found that it wasn't as good as the Llama models in this case. It might be that in different properties that it will do better, and we haven't tried, obviously. There's been a couple of new releases since July that might be doing better with the 4 models, but yeah.
Yes, I see another question here.
Really nice talk. Like, it's impressive, especially the manufacturing bit. That was
We were really surprised because we didn't ask it at all.
A little bit scary, you know?
Very scary. When you see it come out and it goes powder metallurgy and then it goes ingot metallurgy, I was like, oh, okay. Now we're talking.
It's really impressive. So I have two questions. The first one related to the prompting strategy.
Yeah.
The validation prompt specifically is very clever. How did you converge upon that specific prompt?
A lot of it was actually thinking about what we were trying to get to compare to the database, right? So some of it was already kind of instructed for us because we were trying to compare like for like. But I think when you're thinking about the materials design kind of framework and what properties you're specifically looking for, it becomes a little bit easier to write the prompts to that, what exactly it is that you're looking for, if that makes sense. In this case, it was easier, but I think as we start expanding to specific properties and how you validate that, conversations with undergraduate students, often very helpful, actually, because that's a really easy way of kind of going back and forth and getting to the actual question that you're after.
And my second question, if I can, is at the end you had a fine-tuning versus prompting engineering. Are you going to add a versus, say, like retrieval augmented generation? Are you keen on trying that as well, or?
We haven't spoken about it yet, just because the fine-tuning is taking way longer than we ever thought it would. And also because the prompt validation is looking really good, or better than we expected. But yeah, it is probably a conversation we need to have at some point.
Thank you.
Pleasure.
Great. We'll just have a short question before we welcome the next speaker. Yeah, go ahead.
So, at some point in the slide before the last one, you talked that we need to actually learn how to report the data and stuff like that. So, if you go back to, let's say, the extraction of the database, the first and the second one, when you remove the ones that are mislabeled, do you see the difference in the writing text between the ones that the model is doing well and the ones that does wrong? And what are, let's say, one or two examples that you find that are written differently, which leads the model to misguide?
Usual one is actually coming back down to composition descriptions and how we write out the compositions. That can confuse the model a lot. It can confuse us quite a lot, to be honest, a lot of the time, because everybody has a different way of writing it. So we've seen some correlation with that, the composition. And then with the phase information, a lot of the times is when we're using structobaric notation rather than describing the phase in a different way. So when you say, I don't know, the A1 phase instead of FCC, that can confuse it, that combination of letter and number. But we've not done a huge amount on it just because we know we've got a very small data set, so we probably need to expand it and train it a bit better first.
All right, great. Please join me to thank Katrina again. Thank you very much. Just before we invite Josh, I'd just like to maybe make a very, very quick note. You know, I think Katrina was mentioned that she's joined today by also Josh from Sheffield, is that right? And I'd just like to shout out to the younger researchers that are coming all the way from overseas as well, including Andre from NTU. So please, if you can see them around, please make them feel welcome. Well, now we have a senior guy. Okay, so now let's welcome Professor Josh Schreiber. So I'll just give I've got lots of good stuff about Joshua, but I'm just going to run through briefly. Joshua actually graduated from Berkeley, and he then moved on to Lawrence Berkeley National Lab for his postdoc. And then he actually moved to Haverford College as a professor, and he then moved on to Fordham University. I think that was in 2018. Yep. And I think to show his authority in this field, he is actually also the associate editor for digital discovery by RSC. So without much further ado, please welcome Joshua.
Great. Well, thank you for that introduction. and it's really an honor to be here and to tell you about some of the work that we've been doing. In a sense, actually, this talk will combine some of the threads that we heard in the first talk of this session, particularly on focusing on synthesizability and how can we predict whether a material can be made or not. But using the tools that we've heard about in the last session, namely large language models. And so this is a study that was conducted actually just last spring in collaboration with Professor Yu-Sung Jung and his graduate student Sungmin Kim at Seoul National University. So I think after the last talk, and for an audience like this, we don't really need to introduce large language models. How many of you have already used ChatGPT or Llama or Gemini? Pretty much everybody, right? So, you know, one way that I find it useful to think about these types of tools is as a way of doing approximate search and retrieval. So that is to say, we might think about a large language model as being sort of like a compressed database. The weights, in some sense, store the information. And so when we perform training, we're really doing a form of lossy compression of the training corpus. When we make a prompt or a query into the database, you know, well, that's sort of like a natural language query into our approximate database. And the generated results are an approximate retrieval from that result. And why I think that this is useful is maybe it gives us some intuitions about how we might think about using this for chemical and material science problems and where it might go wrong. Because if you fill your database with random text collected from the internet, it is probably not going to retrieve the types of chemical knowledge that you are going to be interested in. So what can you do to improve this? Well, our last speaker alluded to the idea of fine-tuning of large language models. And I wanted to just go into that in a little bit more depth. Essentially what we're going to do is modify the weights in the large language model such that the tokens that get produced have different probabilities than in the pre-trained model. And this is going to allow us to match the input and output relationships in our data. So just to introduce a little bit of the terminology and methods that are used, people often refer to a full fine-tuning. This is where we're going to essentially backpropagate through the entire large language model. And this is almost never done in practice because it is prohibitively expensive to do. And so instead, what is often done is to use what are called low-rank adapters, or LoRa. We assume that there's just some small delta, some small deviation in the weights, and so we'll assume that that has a low-rank structure. It can be computed through the outer product of some smaller rank matrices. And so this greatly reduces the number of parameters that we need to backpropagate through. It's also, I guess, just helpful as you're thinking about fitting all of these into memory that, you know, any parameter that you want to optimize basically costs you 4x in terms of memory if you think about having to store the gradients and the Hessian information. And another trick that is done is referred to as quantization. This is not to be confused with what all of you have learned in your quantum mechanics courses, but it just means that we replace the full floating point representation with a smaller number of bits. This makes the weights a little bit more coarse, so sort of like a pixelated image rather than a smooth continuous image, but, you know, again, reduces the memory and therefore is of value. So just to kind of show you where this fits in here, so when you're doing the weight updates with full fine-tuning, you know, essentially you have inputs, you know, they propagate through your pre-trained weights, you've got some weight update model over here, and ultimately, like, it's the final weights that will predict your next token. When we use this low-rank adapter, you know, we've essentially just, you know, instead of having the full n by n matrix here, it has many fewer model parameters. And of course, these low-rank adapters, you know, can often be placed, you know, sort of at the end of the process, but there are also places to include it, to include low rank adapters in the query key and values in your attention architecture. So a lot of tricks and technical terminology. Why talk about this, right? Why is it relevant to chemical information? Well, something really surprising that was only really kind of exposed last year was that you can use this type of technology of fine-tuning large language models to make predictions about chemical systems. And to my knowledge, the first paper on this was one by Kevin Jablanka and Bernd Schmidt and co. That came out in 2024, but was actually a preprint from spring 2023. And so what they did is that they showed that you could look at various types of tasks where you would feed in a smile string for a molecule and then fine-tune your large language model to perform classification or certain types of discretized regression, or even do inverse design type problems. And other researchers have also found the same thing. Some researchers in Liverpool and Andy Cooper's group found the same kind of general properties for organic semiconductors. And there was a group in China as well that looked at environmental contaminants and doing quantitative structure-activity relationships with these. They also introduced some interesting masking techniques to try to find out what parts of the molecule that these fine-tuned large language models were doing. So just to make something completely clear here, the thing that we are not doing is just putting the molecular structures into ChatGPT. That absolutely does not work. So I want to make that perfectly clear. What we are doing is we're getting a collection of molecular structures and the corresponding outputs, using that training set of perhaps 50, 100, 500, or 1,000 examples to fine-tune a custom version of ChatGPT or Llama or whatnot, right? And it's only with that fine-tuning that this actually behaves correctly. Okay, so that's the previous work. Where do I come into this picture? So about 6 months ago or so, I thought, gee, we've seen all of these examples about applying this fine-tuned large language models to organic chemistry. Maybe it should work for inorganic chemistry as well. And so what we wanted to do was look at really two types of problems. So given a target compound, just represented as a chemical formula, like the one up here, can we actually predict whether this compound is synthesizable or not, right? We've heard many different approaches to this, in the first talk in the session. There are thermodynamic approaches to doing this, and there are pros and cons associated with that, right? Maybe it doesn't capture metastability. So what we would like to do is just to be able to feed in a chemical formula and make a prediction. This is something that can be synthesized. And so that's our synthesizability problem. Now, of course, this is very challenging because we certainly know what has been made, right? Those are our positive labels. But everything else might be makeable or it might not be makeable, right? So it is a problem of positive and unlabeled learning. The other problem that we wanted to address was how do you synthesize it? So what are the ingredients that I need to buy and put into my reactor in order to perform this synthesis? And so ideally what we'd like to get out is just a list of what those precursors should be. And if you think about the type of machine learning problem that this is essentially a multi-label classifier problem, right? We say, this is our shelf of 311 possible ingredients. Put a 1 with any one that you want to use for this recipe. Okay, so those are our two problems. So let's talk about synthesizability. One of the things that is really tremendously powerful about the LLM approach is just how simple it is. So what we did is just simply prepare a text prompt. This is the entire text prompt, right? You are an expert inorganic chemist. Determine if the following compound is likely to be synthesizable, right? And return only P or U, right? Positive or unknown. And then we provide just the chemical formula for the compound. We used our fine-tuned model, but just in case you were suspecting that ChatGPT knew the answer already, we also evaluated the pre-trained models. What are we going to compare to? So we're going to compare against exactly the same set of training data and test data with a state-of-the-art convolutional graph neural network method that takes in the stoichiometry and then generates the results, right? So we kind of retrained this bespoke machine learning model that was developed specifically for this task and had only just come out very, very recently. How does the fine-tuning process work? Well, actually, it can be really quite simple. All you need to do is assemble your input and output pairs. So we have a set of input pairs with the prompt and our compound just written out as a chemical formula, and then the desired output that we want the model to have. And in this case, we just want the model to say P for positive or U for unknown. And if you're using one of the commercial services, then it's just as easy as uploading a file containing all of these examples to the OpenAI server. You give them your credit card, and you go away and have a nice lunch or drink a coffee. And so, for about the price of your very nice lunch and coffee, you then get out a API endpoint that you can use to make queries. So this is a very simple way to do this. In fact, we did not modify any of the hyperparameters. We just used the default hyperparameters. And we really didn't do any prompt engineering. This was really just kind of the first reasonable thing that came to our mind. How are the results? Well, what's surprising is that this fine-tuned LLM model is just as good, maybe even a little bit better than the bespoke machine learning model that had been developed specifically for this task. And so that's really quite amazing. Now, in comparison, if you just use the off-the-shelf GPT 3.5 or GPT 4, the results are terrible, right? So clearly this is information that is outside of the training domain. ChatGPT is not interested in predicting synthesizabilities, but by doing this simple fine-tuning process, we can get really, sort of state-of-the-art results. Another little trick, and we talk about this in more detail in the paper, is that if you're just returning these single token completions, you can actually pull out the model's probabilities for returning positive or unlabeled. And so we sort of make use of that. You can kind of adapt the thresholds and so on. And so these plots over here are actually the model's probability associated with returning a positive, not just a specific instance. Okay, so that's good. What about the precursor selection problem? Well, again, it's really quite simple with the fine-tuned LLM. We provide a system prompt. You are an expert solid-state chemist, and here's what we want you to do, right? We want you to return results in the following format. So I'm going to give you a target. Just say the name of the target again, a little arrow, right, indicating that this is a retrosynthesis, and then what are the precursors that go in there. And we could ask it for one synthesis, or we could ask it for 5 syntheses, right? And so we sort of generalized on that. Again, we're going to fine-tune a model on this data, and we'll kind of compare to the baseline models. Here, too, we compared against a state-of-the-art, just recently released earlier this year, bespoke machine learning model that had been developed for this task, which sort of breaks down the target composition into a set of elements and then recommends precursors based on that. Same training data and so on. And I should say that all of the training data in both of these problems is experimental data, so we're not making anything up. All right, again, very simple. The training data just consists of inputs, right, which are the text, provide 3 synthesis targets, and here are the 3 examples that we had in the training data. If we only have one example, then we just say synthesize this one thing and have the output. And so again, you upload this to OpenAI, you give them $10, and you walk away, and you've got a result. So how well does it do? So the light bars here indicate the top 1 accuracy. This is getting every single precursor correct and not predicting any precursors that aren't present for the synthesis. And the dark bars in each case are top 5 predictions. We did this as a 5-fold cross-validation, so you can see some set of errors. And so what you see is that the pre-trained GPT models, GPT-3.5, GPT-4, are not much better than just guessing based on the statistical weight of the precursors. But what's really surprising is that our fine-tuned LLM model actually outperforms this bespoke model. In fact, actually, it does even better than that. These dashed lines indicate the hypothetical maximum given the assumptions of our bespoke machine learning model. It assumes that every element can come from only one type of precursor. So if I have copper, for instance, in my product, I have only one copper precursor. And so we can actually go beyond that based on the generality of this fine-tuned LLM model. So that's really kind of surprising and shocking, right? Why work hard on developing special purpose machine learning models when all you need is actually encoded in the chemical composition and the sort of underlying rules can be extracted just based on analyzing the text. Well, we wanted to go one step further, right? And so to go one step further, we don't just want to predict a particular composition governed by a chemical formula. We want to actually be able to make predictions about the synthesizability of individual crystal phases, right? So individual structures, right? There are many different polymorphs that could be made, as we heard in the first talk, right? And we want to get one specific one. And so the question then is, how do you represent the structure for your large language model? Well, we did something that is relatively simple. For the structure-based prediction of synthesizability, we start out with the CIF files, and we can get candidates of many different things from the materials project. The ones that have an ICSD tag have been made, so those are our positive labeled examples. We can, of course, then just feed this into a convolutional graph neural network that has been developed specifically for this type of positive unlabeled synthesizability task. All right, so that's our baseline of the bespoke model. To make this work with the LLM, what we're going to do is feed the CIF into a program called RoboCrystallographer, right? It takes the CIF file and generates text like the text that a crystallographer would write. Now, there's no large language model or machine learning involved in this. It's just purely a deterministic program that goes through and looks at bond angles and geometries and produces text that looks like this one in the center. Then, with that text, we can do a few different things. One is, the beginning of this actually just describes the stoichiometry. So we're going to call that the stoichiometric GPT, right? So in other words, that's just like what I told you about a few slides ago. The other thing that we'll do is we could just feed in all of this text description of our structure, right? And then use that as the input. But there's one other thing that we can do, right? Under the hood, the large language models take in this block of text and generate an internal representation in the form of a high-dimensional vector. And so what we can do is actually generate that embedding vector that captures the semantic meaning of the text. It captures it in the form of a 3096 dimensioned real number vector, right? So maybe it's not very human interpretable, but it's at least capturing the internal sense of this text as the LLM sees it. And so based on that semantic vector, we can then feed that in as an input just to a simple feed-forward neural network, right? That we will train for a positive unlabeled learning task like this. All right? And so we'll call that one PU-GPT embedding. All right. So it's the moment of truth. How well do these different methods work? Well, the fine-tuned LLMs are pretty good, right? That predicting things based on just the composition is in some sense an easier problem, right? Because any of our polymorphs would work. And so the gray bars are, of course, higher. If you don't fine-tune your LLM, the results are poor, right? Not surprising. And in general, including the structure information, right, helps, quite a lot. And we can get pretty reasonable accuracies on this, both recalls or precisions. What's interesting is that certainly fine-tuning helps, right, as mentioned before. But in fact, we can do even a little bit better than the fine-tuned LLM or these bespoke graph neural network models by using the embedding vector method. And this is also really promising because it's very inexpensive and very fast to compute these vector embeddings and then evaluate them with this relatively simple feed-forward network that we trained. So kind of neat, right? Now, okay, so we can make these predictions about is something synthesizable or not, but we wanted to go even one step further and generate explanations. And so, what we've done in sort of our recent work is to take the predictions that come out of these models, right, where we say, here is a new compound, right, here's a new crystal structure that all of these models agree should be synthesizable, but yet, has not been made. Why is that the case, right? Help me to understand this. So the way that we do this is actually a multi-step process using the LLM. We first feed in the structure description and ask, explain why is an inorganic compound with the following structural information synthesizable, right? We've actually looked at what the types of responses are over thousands of examples, right? And in general, it seems to be very reasonable things, right? The types of things that a human chemist would also draw upon, right? And this is an example of the type of reasons that get generated. What we then wanted to do was actually check for the internal consistency of these rules. And so this is a really neat trick from the large language learning model community on essentially what we're going to do is split this up into a series of rules, right? And we'll use the LLM to break up this explanation into individual if-then rules that invoke an underlying principle, right? Thermodynamics or structure and bonding and so on, right? So we're going to feed this reasoning into here. And this is an example of the type of rule that gets extracted. Again, something that is very reasonable to a human chemist. Now, this is just the output of an LLM. So should we believe it? Is this just a confabulation, right? Or a hallucination, as some people say. So one thing that is really powerful is that people have found that large language models actually have this sort of self-calibrating property. That is to say that if you provide a statement and ask your LLM, is the statement true or false, you can read off the log probabilities on the true or false and get a calibrated uncertainty on the statement. So we're essentially using the LLM to self-verify. So what we'll do is, again, kind of feed in this extracted rule as the input to this statement, right? You are provided with a statement of unknown veracity. It's going to be this statement. Return only true or false, depending on whether this is true or not. And then we can read off the probabilities on this. And those, in fact, actually in other studies have been found to be well calibrated. So it's really neat, right? So we can actually then rank which of these rules are very reliable and extract information. We can discard the rules that are unreliable and throw them away. And in this way, actually learn something new about the materials that we're trying to synthesize. Okay, so I think I'm probably running low on time, so I'll wrap things up here. The take-home message here, something that is tremendously surprising to me is that these fine-tuned LLMs are comparable in their performance to the state-of-the-art bespoke machine learning models that people have developed for these tasks, both for synthesizability and for precursor selection, right? It's so simple, and one of the things that makes it really powerful is that we have a lot of flexibility on the inputs and outputs. So if I want my inputs to be a list of precursors, I just need to write out the chemical formulas for those precursors separated by a plus sign, right? And the model is able to interpret that. And certainly, I think there are many areas where we could extend this to other problems, right? This type of positive unlabeled learning problems occur in lots of other tasks. We just happen to be interested in solid state synthesis. And so my recommendation for all of you, since we are a community of materials modelers, is certainly do work on your own state-of-the-art model, right? Your own bespoke model. But consider using an LLM just as a baseline, right? Because if your task is completely described by information that is present in the text string description of your work, maybe the added value of that other types of information might be less than what you think it would be. Okay. Now, there are a lot of provocative statements that I made in this talk, so I wanted to preemptively answer some of them. Yes, it's true. We use the commercial model from OpenAI. We've actually tried the open source models. The performance is not as good. So for us, we just want the best performance. I'm sure if we come back a year from now, the open weight models will be just as good. So one of the problems, though, is that we don't know what's in the training data. Is there leakage? Well, the poor performance of the pre-trained models suggests that that's not really a relevant issue. All of our fine-tuning has been trained on experimental data so far, right? And so to the extent that we know that there are biases in these inorganic syntheses data sets, the model is just going to reproduce those. But that's the same as any other machine learning model. So I'm not sure that we're any worse there. There's certainly lots of things that could be done better. We didn't do any prompt engineering. We didn't even fiddle with the hyperparameter tuning. So this is in some sense, just doing things in the simplest possible way. There are probably also, in fact, there are a few things that we've demonstrated, and if you're interested, we can talk about it in the coffee break. You can also do things where you combine predictions from different models, and in fact, use your LLM to re-evaluate and re-rank. And this can actually boost your performance by a few percentage points. It's kind of neat, right? Maybe something that's useful. Now, I've told you about what we did. What if you want to start doing some fine-tuning? Well, it turns out that it's really easy. When we did this study back in February and March of last year, March and April of last year, all we had access to was fine-tuning GPT 3.5. Over the past summer, GPT 4.0 Mini and GPT 4 are now fine-tunable. And in fact, actually, they cost less than what we did before, right? Both for inference and for training. And in fact, actually, I would just encourage you to use this most recent model. Our experience has been that it actually fine-tunes much more easily than the previous models and then the open source models. There's some other tricks that you can use to drive down the cost, but we'll blast past that. Another thing that I think is really neat, there's a whole series of startup companies that are providing LLM fine-tuning as a service. And one that I particularly like, just as a user, is a service called OpenPipe. So this provides a common API that you can use to fine-tune OpenAI models, but also to fine-tune Llama, Mistral, and other models. They provide all the hosting, right? So you don't need to bring your own GPU. You just need to provide your credit card. And this makes it really easy to do side-by-side comparisons of the different models and so on. Okay. There are, of course, also lots of open source libraries if you do have a big bank of GPUs that you can do this locally on. And so if you're interested in this, actually I've written up a blog post about my discoveries and findings and how to get started in LLM fine-tuning, which may be a useful resource for all of you. Okay, so just to wrap things up, right? Don't use pre-trained GPT models, right? They're not going to help you with your chemical data. But fine-tuning LLMs is really easy and it's fast. It doesn't cost a lot of money. You don't need a big bank of GPUs. And it gives surprisingly good results for these really challenging problems, right? We heard from our first speaker that the most important thing that we need to do is improve our synthesizability predictions, right? And maybe this is one way towards doing that. I demonstrated today, this application to inorganic synthesis, but also I think extracting explanations and reasoning are really powerful. So I would recommend that you use fine-tuned LLMs as a baseline for your studies. And there's a lot of interest now in developing LLM foundation models specifically for science. And so if any of you are involved in those efforts, I would encourage you to make it easy for users to fine-tune, because I think that will be kind of a very common usage pattern in systems like these. All right? If you want to read more about what we did, The paper on composition-based fine-tuning came out in JAX over the summer. The work on structure-based predictions and explanations is on the Chem archive, and so you can read all about that. Here's the fine-tuning blog, and I'd like to thank the sponsors, and thank you for your time.
Thank you very much. All right, so this presentation is open for discussion. Questions from the audience? All right.
Hi, Prof. Thank you so much for the presentation. So, if I may, I just have two questions. So, the first question is regarding the synthesizability that you talked about, right? So, have you done composition based validation? That means, let's say for a given composition of copper indium telluride, do you remove all compositions related to that and then test whether does it still predict synthesizability for that well?
Okay. Yes. So for the synthesizability, we did not say, for example, I think what you're saying, right, just to repeat the question, is if our test case is some copper telluride, say CuTe3, making sure that our training data does not contain any copper telluride containing phases. And the answer is no, we did not. So for the composition-based synthesizability, it was just a random training and test split. Yeah.
Understood. Thanks. Thank you for answering that. So my second question is then on the how to synthesize the model, right? So similar in the same vein as this, right? Would you be interested in say cross-validating whether the precursors are being picked have certain commonalities, will they, let's say it's an oxygen-containing compound, would it purposely pick the most stable oxides or so on?
Yes. Yeah. So that's a really interesting question. What we did as the sort of baseline statistical model was to just look at the frequency with which individual precursors occur in the training corpus, and then to select those, by the weight with which they occur in the training corpus. So that may capture some of the effect that you're describing, right? Like the propensity of people to use, a specific, I'm always going to use copper oxide, right? Rather than, copper sulfate or something like this. But that was the only, that was, sort of the only way in which that entered into the work.
Thank you very much.
Great, thank you for the questions. Any more from the audience? Oh, yeah, okay.
Great talk. Maybe I should have checked with you before going into synthesis, honestly. I see that you synthesizability, you say either 1 or 0, right? So it's either synthesizable or not, right?
Okay,
So,
yes. Well, to be fair, what we say is it is synthesizable or unknown, right? But, we'll take the ones that are closer to positive, yeah.
My question is, oftentimes you can't fully make a compound, so it has impurities.
Yes.
Right? So perhaps it's not 1 or 0, it's like 0.7. So how do you deal with that kind of problem?
Excellent question. So actually, if the AV people can turn back on the presentation for a moment, I can show you a slide that might help answer that. Let's go back. So one of the things that we can do by extracting the probabilities of the output tokens is we actually get a score about what the model, what the fine-tuned model thinks about what the output should be. And so that is plotted here. For example, we get a number of compounds that are plotted as, probability 1, right? Like it only reports that this should be made. But there is actually a range, right, going down below. And a fine point that I did not mention in the talk is that there are some schemes that we've learned from the positive unlabeled learning community where you essentially pick a correct threshold for that, right? So that would be analogous to your like 0.7, or whatever the value is. Is presented in your question. So yes, so we do actually get a score, even though we're predicting only, one text token, right? We can actually extract out a probability, and then by calibrating that against our training set, we can figure out what is the sort of the best trade-off for that. And so it's not purely just a yes or no, but it does have that bit of a shade of gray.
Can I ask another question? Sorry.
Yes.
Sure. Thanks. So, and I guess that you also face this, but like when you go to the literature, synthesis recipes tend to be very not heterogeneous, so to say.
Yes.
How do you envision bypassing this problem?
Robots, clearly, right? This is something that I've worried about for many years, right, and studied. I don't see a simple way past that, right? It could be that many of the times we use these because they work well, or just because it's convenient, it's on the shelf, or we have some literature precedent. For our purposes, one thing that we did do was that we did trim down the data set. So any duplicate sets of precursors, we just only have one entry for those. And we also allow for the fact that there are multiple choices that could be present. So actually, another way to spin that is that I also think that makes some of our accuracy on precursor selection a pessimistic bound on the actual performance. Because I suspect that many of the things that our model predicts could work would potentially actually work. It's just that the one example in the literature that we had for them, wasn't that particular choice of reagents. But beyond that, trying to understand this, I think certainly more comprehensive data collection, right, will help. The other thing that I think is perhaps a really useful technology is there's a recent preprint from a group at MIT that has been building upon our composition-based prediction method. What they do is they fine-tune a large language model that, given the left-hand side of the equation, predicts the right-hand side of the solid-state equation, given the right-hand side of the equation, predicts the left-hand side, or they have a third model which, given a target, predicts both the left-hand side and the right-hand side. And so I think that perhaps there's an opportunity for using the data that we have and combining that with self-play type technologies to sort of explore things, perhaps with a few select cases brought into the laboratory for ground truth. But that is purely science fiction and speculation on my part.
Thank you.
Okay, so any other questions from the audience? So may I just end this session with one question? So basically, as associate editor for the journal, I think it's still, just my personal opinion, I think it's still not very common for people to report or publish wrong or failed experiments.
Tell me about it. Preach it, brother.
Yeah, right. So there are many young researchers and scholars here. I think they're also worried that maybe journals are definitely not accepting or not interested in failed experiments. From a data point of view, how do you think, or could you share with us what importance do you think it stands or it holds in this whole ball game?
Sure. Thank you for that question, right? I suppose in 2016, I wrote a paper in Nature about the importance of failed reactions in inorganic chemistry. So certainly this is something that is very important. I think that certainly one thing that we can do, first of all, there are many different types of failure, right? There are kind of trivial forms of failure, technical errors. We probably don't need that type of data in the literature. But more practically speaking, to date, efforts to try to build databases of failed reactions have really not taken off, right? I know we tried to do something with that, It was hard to get momentum and traction. Other people have tried doing things, and those have really gone nowhere. I believe that these types of large language model tools, like we heard about in our second talk, might be really helpful because it might be a way to go through electronic laboratory notebooks, right, and extract out examples of these failed things, right? Because certainly laboratory notebooks do have these failed examples. But I also think that new emerging software tools like the ChemDX software that many of you are coming for the hackathon over the next few days might be a way to help. And I think that the integration with these automated labs will really help drive this systematic data collection. Once your experiment is described in an electronic form, it's much easier to just kind of retain that information regardless of what the output is. As far as publication goes, it's really tough. I don't think, well, I mean, I guess I would say that there are some promising examples of this. The Chemical Sciences, just earlier this year, published a paper by researchers from Toyota Research Institute where they had used a combination of high throughput DFT and some machine learning tools to try to predict new faces. They predicted 11 faces. They went into the laboratory to make them. They made none of the faces. And Chemical Sciences did publish that paper of containing exactly 0 successes. So perhaps the Royal Society is leading the way in publishing failed results.
Good to know. Yeah.
I think the challenge for you as a researcher is how to frame that failure as being insightful. And that's up to you. But it can be done, right?
Yeah.
And I think there's much more appetite for that these days.
Right. So do not be afraid of good failure, let's say.
Yes.
All right, with that, thank you. Thanks, Josh, again. Thank you very much. And that ends the second session. So I'm just wondering, are there any admin? So we have a coffee break, but please come back for the third session. All right, see you in a bit.
It was my fault. All right, it's time for the session 3. I'm Byung-Young Kim from Hanyang University. I'm your chair for the session 3, and we have 4 invited speakers. So I will introduce the first speaker. The first speaker is Dr. Mihail Minotakis from the Paul Schroeder Institute, Switzerland. So let me introduce briefly about his career. He graduated from University of KRICT for the bachelor and master degrees, and he got his PhD in Trinity College of Dublin, and now he's a postdoc fellow at Paul Schroeder Institute. So if you're ready, you can start, or floor is yours.
Yeah. So let me first start the time, so I have an idea of where am I. So, I need to stand here so as well. Okay. So first of all, I would like to take a moment to actually thank everyone who is working here to make this event possible. I would like to also thank the organizers who gave me the chance to come over from Switzerland to present this work here. And the title of this work is MC3D, the Materials Cloud Fair and Full Provenance Materials Database. And this is the work that we are doing on the group of Giovanni Pizzi and Nicola Marzari on PSI. So the outline of the presentation is shown here, where all the work was orchestrated with AIDA. So firstly, we need to introduce the tools that we use. So what is AIDA and why you should care? We are going to talk about what is a workflow, what is a provenance track, workflows combined with robust simulation protocols, and then we're going to move on to, if we combine all of them, to create this database that it's called MC3D database, which is an acronym for Materials Cloud 3-dimensional database. What is the origin of this database? What error relaxation workflow we used? What are the error handlers that we implemented in this work? Then we are going to show some application on run on exascale, and what is the current state of the database, and a short demo. And then, in the end, because we want this database to be used, we will showcase some of the applications that MC3D is actually already used, and some summary. And here on the right side of this slide, I show the nice front end that Christian made for us. So first of all, what is a workflow? So according to Oxford Learner's Dictionary, a workflow is a series of stages that a particular piece or type of work passes through from the beginning until it's finished. For example, what I like to have in mind is a cooking recipe, right? You have the ingredients, you follow some stages, and in the end, you have a final product. Sometimes a workflow is simple, right? So for example, you have the division of 2 numbers, 5/2, you have this, the division, and then you have 2 + 1. But then on the other side, it can be very complex. So for example, we can calculate the band structure of materials. And if we want to, let's say, make the same schematic for that, we get this one. So starting from the crystal structure of the material that we are interested, let's say we feed the relaxation protocol with the structure, the pseudopotentials, the parameters that we are using. We perform the calculation there, and then we get a number of outputs. Then from this number of outputs, again, we use some of them, some we want to keep them in our mind, or keep them on the database until we recall them, and so on and so forth, until we found this nice plot here that tells us a lot of nice things for this material. And then, of course, this has become very complex very quickly. So this is where AIDA is used. So AIDA is a computational science infrastructure for high throughput workflows with full data provenance. And what does that mean? AIDA is a software that is used to actually orchestrate these recipes and then retrieve all the data and manages them in a specific database. It has a scalable workflow engine that it ensures the robustness. It has a built-in support for HPC, which give us performance. It also gives us full data provenance, which ensures reproducibility, and a flexible plugin system, which ensures interoperability. So, for example, if one of you uses a very specific ab initio code, or even you do science away from material science, you can use AIDA to create a workflow and create a database with that. And before I show you this, how the schematic looks for a single band structure, imagine we are doing a high throughput study of, let's say, 30, 40,000 materials, how the database looks like. And this is actually how the database looks like for the database that I'm going to present today, for MC3D. And we can see that it is quite complex. All these pixels that you see encode some information, where you can go to the database and check exactly how this specific data was produced and what it does in our workflow. Of course, if you have the machinery, let's say, the AIDA on its own, it's not doing much. You also need to have an idea of what are the parameters that you are going to use to do these high throughput calculations. And this is the work that was done by Gabriel, Marnik, and the rest, that it is now under review. So they used this machinery to do high throughput experimentation to come up with specific parameters, for example, K points or smearing, that gives you the best high fidelity calculations that you get. Everything was done with Quantum Espresso here. And not only that, we have implemented all these protocols in this Quantum Espresso input generator that you can go there, upload your structure, select what type of calculation you want to do, select also if you want precision or accuracy, and this will print you a specific input that you want after, that you will take it and run your calculation. And here I have the QR of this site. So around my presentation, you're going to see a lot of these QR codes. So feel free to scan them and go and check these tools. So now that we have the protocols that we want to run our calculations, it's time to see what data we're going to use. So this is what we are going to refer to as MC3D source. So it's the source database of crystal structures that are curated for us to believe that they are only made from experimentally synthesized materials. So how we did that? We extracted all the data, the C files from crystallographic open database, inorganic crystal structure database, and MPDS or polling file, which then we came up with almost 800,000 different materials. Then we wanted to see, and we choose the ones that are consistent. So we remove the ones that, for example, have different composition between the title and what it is reported on the C file, missing hydrogens, etc., etc. This reduced our database by around 150,000. Then, for this consistent SIF, we went onto the stoichiometric and the non-stoichiometric materials. As Pepe said, like three talks before, if you are using non-stoichiometric, it's quite difficult to handle. You need to use SPS, you need to do a lot of stuff. So we are not going to use them. So here, we keep only the stoichiometric. Of course, there are a lot of duplicates on that. So we are doing a duplicate analysis, and we end up with almost 73,000 of materials. And these are the unique materials that we believe that they have been synthesized so far. And here is the Venn diagram of what is the distribution of the number of materials by its database, where we can see that actually 1/3 is shared among the 3 databases, but there is also quite a lot that is exclusive to a single database. So then, now we have the data, we have the machinery, we have the protocols, let's see what we're going to do. And the first thing that we wanted to do is structure relaxation. And to do that, we want to ensure that what we have is actually relaxed. And this is the workflow that we used. So we took each one of these structures that we have on the MC3D source, and we implemented this workflow that is freely available on the AIDA Quantum Espresso repository, so you can go there, clone the repository and play with that. So we have 2 relaxation loops, where the first one is a bit more rough relaxation that we want to push the material towards the minimum, and then here we have the main relaxation loop, where we have very high accurate parameters. And each one of these relaxation loops, actually we implemented this logic where it says we check if we want to run a relaxation. We run the relaxation, we check the results. In case there is a problem, we try to fix it. Of course, we cannot do it internally. If it passes a cut of calculations, we stop the calculation and we say that it failed. But a lot of the times, what we implement so far is fixing the problem. And this is what we are going to see on this slide. So here we run 50,000 calculations almost with these different error handlers. These error handlers can handle simple errors. Let's say, for example, the wall time, when you just need to do a simple restart, or more demanding ones. So, for example, the electronic convergence, where you have to check, for example, the bands that you used, the smearing that you used, and all these parameters. And we found out that for materials that do not contain rare elements, rare earths, almost 80% of them was actually converged straight away. Whereas 20% of them, it needed these error handlers. Of course, you might think 20% is not a lot. We could even run them without. But if you run, let's say, 100,000 materials, 20% is 20,000 materials that you wouldn't relax without these error handlers. Of course, when we now go to the rare earths, it's a bit more difficult because they are strongly correlated materials. There are ways to converge them by using, let's say, DFT plus U. And we are working actually with the developers of Quantum Espresso to actually increase their success. It's not that it is super bad, right? It's I haven't put it here. It's around 80%, but still we need to increase it. So now this slide is might make the people who were talking about resources a little bit mad. So like around 4 months ago, we ran what is known in the HPC community as a hero run. And what is a hero run? So here we have the Alps newly inaugurated supercomputer in Switzerland, which is this one, which contains almost 10,000 Grace Hopper GPU chips. And we use it to run, to orchestrate with AIDA to fill the machine and keep it filled until the end of the allocated slot. So this is a graph that shows us how we were able to fill the whole machine for these 16 hours. So we used AIDA to orchestrate the run and Sirius enabled Quantum Espresso software to run the calculations. So Sirius is actually a suite of codes that enables GPUs to be used by Quantum Espresso. And we were able to actually relax almost 20,000 of materials in these 16 hours. We burned almost 1 million GPU hours on this slot. And yeah, as you see here, around 2.5, we were already filling the machine of 2,048 nodes. And there was a small Slurm problem here, but it was fixed. And actually around 4, we even took a nap and we let the software does its magic. So, okay, so now we have the data. Of course, this is not only the 20,000 materials that we have. We have almost 50,000 now. We have 3 versions of the database. We have a PBE version that was calculated by Sebastian. We have a PBE Sol version 1 that it is calculated by Marnik. And we have a PBE version 2 that was calculated by Timo and me. And here is the QR code, so you can go there, see the data. And what actually comes with this data is the full provenance. So you can see what is happening from the initial structure up to the end. So you can actually track if the calculation was done correctly or not. If it was done incorrectly, please tell us. But I'm sure it's going to be fine. Of course, this is a bigger overview of the database where we have the structural properties of 50,000 materials, where we have the highest concentration of materials is on the ternary compounds. The next one is on the quaternary, and here is the number of elements, the distribution of the number of elements. Also, soon we are going to publish also the electronic structure properties as well. And also you can find the X-ray diffraction patterns. Of course, as I said before, you will be able to find the provenance graph that explains the origin of the database uploaded there. So this data allow us to do some comparisons and draw some insights from these databases. So for example, here we have a comparison between different functionals for PBE and PBE Sol. So let's say the initial, the ancient, let's say, version of the database versus the newest one, where we see that actually the relative volume changes actually fluctuates as we change to different functional, exchange correlation functional. But also we can take a look at the metadata that accompanies the structures that we have, which also sees that the data that we have also contains some structures that are flagged as high pressure structures. Whereas for which they shrink if we start doing the relaxation. Whereas also for the blue ones, we don't have any information that accompanies them. And then now I'm going to show you a little demo of how the Materials Cloud front end looks like that was developed by Christian. If our technicians can play the demo, I would be very pleased. Thank you so much. So it's me here that is pressing mc3d.materialscloud. I go there and I check the different methodology that I want to use, PBE Sol V1. And I go and check 3 magnetic materials, which is manganese, iron, cobalt, and I see that we have 2 elements, one that contains silicon and one that contains germanium. I choose the first one. Here I can play with the structure. Here I can see some info and where does this structure comes from. So it comes from polling file. Here we see some information regarding the structure, the XRD pattern. And the nice thing is I can go now and check the provenance. So for example, I go to the optimization calculation and I go here and I see this flag where I can go and press on each one of them, which I don't do here because it's gonna be super boring for you, and check the input parameters for this calculation. So yeah, that was it. Thank you. So now that we have the database, let's move on to some of the applications that were actually this was used. So the first one is the library of Vannier functions. So what are maximally localized Vannier functions is a method to actually accelerate the calculations by exchanging the problem of, with a different kind of, with a tight binding model by fitting this maximalized localized Vannier function. This has the same accuracy or as DFT or beyond a fraction of the cost. And they are very useful to calculate properties like Berry's curvature, electron phonon transport, superconductivity, etc. But also it's super difficult to fit them. So you need expert knowledge on that, which for example, me, I don't have. You need to use Vannier 90 tools to actually fit these functions. But once you have them, you can actually calculate a lot of things. So the challenge was, can it be made fully automated? And this was done by, it was the work of Yunfeng's PhD thesis, where he actually created an automated Vannierization workflow and a library of Vannier functions for almost 22K of structures. And here we can see how well these Vannier functions fit if we calculate the band structure from them, where here we have the difference between the DFT calculated bands and the ones that are calculated when we have the Vannier functions. And we can see that almost 90% of them are below 3 milliV of error. Then once we have the Vannier functions, we can do, let's say, we can do a library of Fermi surfaces. Fermi surfaces are as a key property to understand the electronic structure of materials. But it is very difficult to do it with experiment. It's very expensive and time consuming, but also very difficult to do with classical DFT because you need to sample the Brillouin zone very finely. But when you have the Vannier functions, you can go and calculate it, and this was done by Natalia, where he calculated a library of Fermi surfaces based on the MC3D. So now this will be published by the end of the year. So when this data will be published, you can go there and try to search for, let's say, interesting topologies. Then another nice topic is the calculation of formation energies. We know that the distance from the convex hull provides a metric for the thermodynamic stability of a material at 0 temperature. But how this, let's say, formation enthalpy changes if we change the functional, for example. And this is what is done here, where we calculate the difference between PBE and PB sol. We see a difference. And this work was done by Timo, Marnik, and Giovanni. And then, of course, we can go and try to find materials that they are with some specific interesting properties. So here, the first application was about the electrides, where electrides are materials where the electrons can be found between the atoms. And these materials have very low work functions, so they are excellent electron emitters with high catalytic activity. So they scanned MC3D, and they identified almost 352 novel electrolytes from this database. And the good thing with that is if you have a database that it is based on experimentally synthesized materials, you can go to the experimentalist and say, I calculate this property, you should be able to make this material, and they go in the lab and do it. So we have non-metallic candidates, electrolytes under doping, and electrolytes with predominance of one spin channel, which can be used for spintronics applications, so for example, spin filters. And the last one is the discovery of superconductors. So, of course, if you have a material, you can use quantum espresso, the brute force approach, and calculate the TC and the Eliasberg spectral function to identify materials with the need TC. But of course, this is a very difficult calculation to do. So if any one of you tried before, like it's a super heavy calculation where you produce a lot of outputs, and you cannot do it in a throughput, with a high throughput fashion. But then if you have the automatic linearization workflow, you can combine it with the EPW, which stands, it's an open source code that stands for electron phonon linearization. So you can calculate the TC based on that. So what you do, you have this, let's say, workflow, and this is what they're doing here. We have some candidates, and these candidates were taken from the MC3D by imposing some, let's say, rules that people from the superconductor community know. For example, superconductor properties do not go well with magnetism, for example. And they take these materials and they press a button and they do the calculation. And in the end, you come up with a TC. So they created this CPW workflow to calculate the critical temperature for these materials and identify any possible superconductors. And the good thing about that is that a large number of known superconductors are top candidates. And this is a big collaboration between people from EPFL, people from UC Leuven, and people from Politecnico di Torino. So the summary of my talk. So we have the AIDA, which is a materials informatics platform that it is robust enough to run on exascale machines. In combination with appropriate protocol leads to high fidelity, high throughput simulations. We have MC3D that is a findable, accessible, interoperable, and reusable database featuring experimentally validated 3D materials, and that it has been already used for a variety of applications. So I call everyone here to try to use it, both MC3D and AIDA, and explore the features today. So I would like to thank everyone that is a part of AIDA and AIDA Lab and all the developers that are doing this work, and of course the funding. And I would like to thank you for hearing me out.
Thank you for the very nice talk. It's time for the discussion and the questions. If you have any questions on the audience. Yes, Professor Han, please.
Yeah, thank you for the interesting talk. So I have two questions. The first one is that, so this MC3D supports API, so can you extract
Yeah,
for
there
the
is
machine
an
learning?
API that you can go and get the data from the database.
Okay.
And I can give you access. If you go to the MC3D cloud, materials cloud, you will find API and you can download the database if you want to use it.
Yeah. So the materials in the MC3D are all from the experimental database.
Yeah.
Is it correct?
Yeah.
Yeah. So then is it identical to the ICSD or is more than ICSD? So maybe you include the COD and other databases as well.
Yeah, it's more than ICSD. Yeah.
Yeah.
So Yeah, that's the short answer. So we
Yeah.
took also the ICSD. So in principle, everything from ICSD is already scanned and see what we could add to this. So we add also the polling file, which is quite difficult database to get access to, and also the crystallographic open database. And we get this MC3D source that we have here. Yeah, so it's more than ICSD, yeah. Of course, there are also high pressure structures, and we are working to, because that doesn't mean that in ambient conditions this can be synthesized, meaning that there are less materials actually synthesized in the reality than this. So we are working to actually flag them, so the people can go there and say, I don't want any high pressure materials. So I go there and take only the ones that are known to be synthesized under ambient conditions. But this is work that we are doing right now.
Can I make one more
Sure.
question? Okay. So we are trying to combine. Maybe we can try to to combine this matrix project data and also the MC3D data.
Yeah.
And in that case, this is BASP and the quantum espresso. But ideally, since they are using the same function like a PBE, but different shutter potentials, and so you may in the optimal situation, maybe you have just reached the shift of the data. But is that true? Have you checked that data correlation with the matrix project for the same structures?
Yeah. So we went over different databases, and we want to see how different are the results by using quantum espresso and VASP. Well, to be fair, like almost 98%, they are more or less the same. There are some differences, like for example, we have differences in magnetic moment for some materials that probably has to do with how they treat the charge, how they treat the simulation on the software side. But yeah, there are not many, let's say, and they are very identifiable. So you can, because there is this ICSD, for example, if you want to combine all the ICSD, or there is this ICSD tag, and you can see how they differ between different databases. Yeah.
Okay, thank you.
Are there any questions or comments, please?
Great talk. First of all, thanks for the effort of developing databases, because they are really useful to you and to everybody that does it. I have two questions. Yeah. So how do you keep up with updates from all the databases that you have utilized?
Well, on the backend, each one of them have a different, goes to a different MongoDB database anyway. So, and yeah, so it's a different database in the end of the day, each one of them. But then our vision, let's say, is if we update the materials, if there are, let's say, now on ICSD they come and say we have 20,000 more materials, we want to press a button. This is why we do these automated workflows. So we want to press a button and extend the new database. So it does the calculations, of course, if you have the resources, right? And then you update the database. So it's actually extendable. And if in the end of the day, it's going to accept, at some point, it's going to accept contributions from other people. So if you have, let's say, calculated a new compound, that it is experimentally synthesized, and it obeys some, let's say, standards, it's going to be extendable. So people from the community can also contribute.
Yeah. And my second question, if I can, when you say electronic properties, you mean like electrical conductivity, things like this, or what do you mean?
I mean, we're saying something more like band structure density of states for now. And yeah, we're also planning to add spin orbit coupling. For example, we are going to run the whole database with the use of spin orbit coupling, which is...
Okay, thanks.
Yeah.
No more questions? Then before we move on, please give a big hand to our speaker again. The second speaker of this session is Professor Dongwari from Postech. What he's going to talk about is natural language processing for building a literature-based materials database and research applications. Before we start, I would like to briefly introduce his career. He graduated from Korea University as a bachelor, and then he moved to the United States. He got the master and PhD degrees at University of Florida, and then he spent some time in the National Institutes in the US, and then he came back to Korea, and then he got the job at Jeonnam National University, and he moved to the Pohang University of Science and Technology from 2017, and now he's an associate professor. So please, let's give a big hand to our speaker.
Thank you very much for the instruction. Today, first of all, thank you very much for giving me an opportunity to present my work. And today, title of my work is Natural Language Processing for Building a Literature-Based Material Database and Research Applications. So I will mainly talking about how we have been using natural language processing to build material database. So first, let me give you a little bit of introduction why we have done this kind of study. So if we need to study the material discovery or finding new materials, and then traditionally, people has been using experimental discovery. So the people has been done the experiment and then try to find the new material. So basically, they do experiment and then they theoretically analyzed the property, and then finally they found the new material for specific application. And then there are 20,000 of data available from the ICSD. However, this kind of study is very limited for using as a database. As the computer has been improved a lot, and then people has been using the simulational study to discover new materials. So in simulation discovery study, and then they perform the lots of computational study, and then perform the material screening, and then try to find the new material for the candidate. That has been like, there are many different databases. For example, OQMD has around 50,000 of the database. So it is still, compared to experiment, it is very a lot. But if you really want to do some kind of material discovery from the machine learning point of view, and then that's not enough. And then now, what people are starting to interesting is, can we discover the new materials by using data? So data-driven discovery, is that possible? So what we are trying to do is, we're trying to build a database from the literature. So basically, there are lots of literature available, and then we take the data from the literature, and then we can, if we can make a database from the literature, that can be a lot more, much more than those compared to the simulation or the experimental database. So what we want is that we want to build the experimental database from the literature so that we can use for material discovery. That's the idea. So if we're thinking about what the material discovery is, we always thinking about the material science study as the relationship of the processing, structure, property, and performance. So if we're thinking about the processing, that's the how we make the material And then structure is what kind of structure does the materials have. So that can be either electronic or atomic structure or even microscopic or macroscopic structure. And also we are thinking about the property. That property could be the material's intrinsic property. So if we know the structure and then composition of the material, that property can be determined. But material science, as a material scientist, this property is not important. Depending on what kind of processing, what kind of method to synthesize or making the material, that property can be always changing, and then we call it as the performance. That performance is the more likely when we put it into the device, put a material into the device, what kind of performance does the material shows, or whether it is a good performance or bad performance, that's the performance. So if we're talking about studying materials, that means we are always studying about this processing, structure, and property performance relationship. And if we understanding this relationship, we can build a new material or we can find a new material for specific application. That's what the material science normally do. And if we can thinking about the simulation database, there are lots of simulation database available nowadays, and then people has been studying a lot or using computation power to build the simulation database. The main problem of simulation database is they do have the structure information, and then they do have intrinsic property information, so they do have millions of the structure property relationship database. However, the problem is that as we want to build the new material, then this structure property relationship or structure property database are not enough to find a new material for specific application or finding new material discovery. So we need the processing and then performance database, but simulation data does not have this kind of enough process and then performance database. So if we can look at this structure PSPP relationship, then we do have lots of structure and then property relationship, but this processing and then performance data are completely missing from the simulation data, so that it's kind of difficult to find or discover new material from the simulation. That's the main problem. Instead of that, not sure. Yes, something stuck. Sorry about that. Oh, yeah, now it works. Okay, so simulation database, they are pretty limited for the processing and then performance data. Compared to that, and then this literature database, from the literature, we can have all this processing, structure, performance, and then structure data. They do have in the paper. If we look at the method section, we do have how they really made it, so we can have the processing data, and then in the main paragraph, we can have the whole structure and then property and performance database. So basically, if you look at the literature database, and then we can build all different PSPP relationship from the literature database. So the good news is, if we use the literature database, basically we can build the entire PSPP database so that we can use those database to build new material or find new material. But point is, how we can build this database from the literature. That's the problem. And if we thinking about the easiest way of the building database from the literature is some people who has a domain knowledge a lot, they do go to the paper and then they read the paper, whatever they need, necessary paper, they search those papers, and then from the papers, and then they read it, and then they found out whatever the important data or data which they can use it, and then extracting those data, and then they can make it as the database. That's what we can easily think of. But problem is, we are talking about the tons of the literature, like not only like 100 or 1,000 literature. We are more talking about like billions of literatures. And if people, whoever has a domain knowledge, goes to those paper and then read and then extracting whatever the data, then it could be almost impossible to build the entire database. Then the easiest way is the way using some processing. So what we are trying to suggest is this is what we are trying to do. The main idea is machine go into the literature, and then they read the paper, and then they found out each different section of the paper, and then figure, and then whatever it is, and then they found out what kind of data inside the literature, and then they figure it out, and then if they can extract the data by itself, so without human being, and if they can read the papers and then they extract the paper data, and then that will be the great. And then after that, they taking out that, and then they build the relationship, and then with those relationship, and then whatever the different number of papers, and then they take out the database, and then they build it as the database, as what we can see here. That this is what we are trying to do currently. So what we want is the machine goes to the paper, and then they read the paper, and then they found out whatever the useful data inside the paper, and then taking out the data, and then finally they make it as the database. That's what we are trying to do at this moment. So in order to do that, and we have built the four-step process, and we essentially build the NLP pipeline for the literature-based material database. So what we do is in the first step, we search the bibliographic data search. That's the KBSE. And then second step, and then we essentially crawling the scientific article and data. And then third step, and we call it as STPC, and then that's the pre-processing and classification. So classify all the data inside the paper. Then the last step is MNIC, and then in that step, and we take out essentially PSPP relationship data from the paper. So that's through this four-step process which we developed, we have successfully build this material database, what we can see here, and then we will, step by step, we will explain how we have been done in this process. So in the first step is the keyword-based bibliographic data search engine. We call it as KBSE. And in this step, what we really do is from the all different type of search engine, if we put some of the keyword which we want to find out, and then after that, and then if we use the all different API, and then using the API, and then we using this keyword and then API, and we find the all possible the papers in the literature paper, and then after that, and then we pre-processing the title so that we remove some of the non-necessary some of the non-necessary word or some useless things, and then after that, and then we classify the title. As a result, and then we can set up the bibliographic data, including the DOI through the whole title and all different things, and as well as we also have some bibliographic classification. So what kind of paper or title, what kind of title does this paper has, so that we can use for the next step. After that, so this is the result of the KBSE, and then as we can see, that we have all the bibliographic data by using this KBSE searching engine, and then we can also classify what is the title of this paper, so that based on using the unsupervised learning, or just using the title, and then we can classify the whole title, keyword of the title, so that we can classify, okay, this paper will be classified into the certain different topic or different range of topic. So that after this classification, what we do is the next step is we do KSAC is a keyword-based scientific article crawler. So in this step, we actually taking out the papers from the literature. So what we do is going into by using all the bibliographic data, DOI and then publisher and all these data, and then also bibliographic data, and then we go to the website, and then we actually taking out the paper. If the paper is in PDF form, and then we can use the converting the PDF to the XML type, or if it is the HTML type paper, then we can just taking the paper directly. Then after that, and then we use it depends on what kind of publisher, and it depends on how we can extract the data. It will be depending on what kind of publisher. So we have to look at what publisher it is, and also what journal it is. It is not only depending on the publisher, but also depending on journal itself. They do have all different types. So we have classified all different type of the publishers and then journals and then the type of the papers, and then we essentially taking out either text or image or table data. So we through this step-by-step process, and we essentially taking out the text, image, and then table, all of the data in the paper, so that we can build the metadata of the literature data. So after that, and then, okay, so this is the result of what we have been done using the KSAC. And then, as we can see, we can have the title, abstract. So we just cut those kind of each text as the sentence by sentence. We just keep saving those kind of the text as a sentence, so that we can, for next step, we want to make it easy to process in the next step. But we saved all those kind of literature data as what we can see, and then also the image data, we also save those kind of image, and then table as well. So what our crawler, the successful rate of our crawler is from about 1900 articles, and then we have been successfully taking out the PDF or the HTML data, and then after that, and then we took out the data as a pretty high rate, and also the image, for the image case, we have among the 13,000 of the the paper including the image, and then we have like 70% of the image papers. We have been successfully taking out all the image in the paper, and then also among the more than 4,000 of papers which has at least one table inside the paper, we have been about more than 80% of the paper we have successfully taken out the data from those papers. Then after that, and then what we do is by using the STPC, so structure-based text processing and classification engine, and then we essentially pre-processing and then do the classification to taking out the actual data from the paper. So in this step, what we do is we pre-processing the text, so we just remove some of the data which does not really need to use for taking out the data. We just pre-processing, and then we classify the text so that we, depending on what kind of each different section, and whether it is the title or introduction, or it is abstract or main or method, we classify the text of the paper into 6 different categories. And then after that, and then we use the PSP NER recognition identification, so that what we do is whether those kind of word is depending on which either processing, structure, property, or performance. What kind of category does the word is essentially going into, so that we classify all those words, and then after that, and then we post-processing, so that some of the words in the paper, if those words are different depending on the section or depending on the paper, we want to make it as consistent as possible. So we use the post-processing step, so that we make all those kind of words as consistent as possible. So through this process, and what we have is like this, so that we have all different paper, that those kind of word meaning same meaning word, then those words will have exactly identical words. That's what it is. So that we have all these identical words through the STPC step. So this is all the identified PSPP NER wording. We have showing some of the example of the word, depending on whether it is the device performance or material structure. We identify all different type of word in the category and subcategory, using subcategory, and then all different each word as a NER tagging, and then we identify all different words. If it is the same word, and then we put it into the same category, and then after that, and then by using the post-processing, and then we make the paper as consistent as possible. And then after that, and then these are the result of the classification result for our each different section of the PSPP. And as we can see, we devise, and then we can successfully classify the device and material. But compared to that, and then still we have to work on this performance and structure type things. But we are getting improving at this moment. So it is getting improving, and we try to work on it more. The last step, and then we developed the M-link. That's the context-based material data linking. So what we use is using the large language model prompt, LLM prompt, and then we build the sum of the relationship, depending on if it is whether depending on the property structure relationship, process structure relationship or property performance relationship, and all we build the all different relationship depending on the word, and then we finally build the PSPP relationship, and then after that, and then from that relationship, and then we build the PSPP database. So that's what we do using this process. So what we do is that so each device and then performance and then the process type of things, and then we build the relationship, and then from using this large language, different large language model, we take out the data from the papers, and then essentially what we do, we use the two different model. One is the Llama, and then the other one is the GPT, and then we try to take out try to build this PSPP database, and as we can see, and then our it shows the pretty high performance, and for both of the method. If we look at the record, and then it is very high, but precision, if you look at the precision, it is relatively low. So this means the large language model is guessing the right things pretty right. But problem is, even though it is wrong, it is still, in many cases, large language model guessing it as right. And then as a result, then the F4 score is around 80%, and then GPT is a little bit better than the Llama model. So we have been using, so this is our model MLink, and then we have been trying to compare with the all different different the building engine, and how well our model works. So if we compare to the MLink to the other model, then but first of all, we use the rule-based and the human knowledge using the NER for the NER, and then after that, and we use the large language model to build the PSPP database. Compared to the CAM data extractor, you use the language model, and then use the rule to the building the data, and then CAM extract use and then NER early, and then CAM prompt, all they use the large language model to build. And then I will show how much difference each model shows. So first, if we compare to our MLink model to the CAM data extractor, and then the CAM data extractor, you use the small data, and then it gives a pretty low NER accuracy as the identifying the word. As a result, and then they show the pretty low accuracy relation, and then they only have some structured data only. So they do have a very limited the database building ability compared to our model. And then if we look at the second chat extract model, and then they directly use the large language model to build the database, and then they have difficult to the prompt optimization, so that they are very limited the building the relationship, so that they only build the partial PSPP database, and then their low accuracy was relatively lower compared to our model, so that our model essentially give the better result. And then the main difference of the chat extract model is that they use the Q&A method, and we have initially used the Q&A method, but we realized that large language model is better than the Q&A model. So anyway, our result was better than the chat extract model. And then if we compare to the NER early model, they are likely use the pre-training initially, and then by using the pre-training large language model, and so that they do the fine-tuning, and then build the PSPP data, and then the NER-RLE model was the main problem of the NER-RLE model is they do have a generation error. I will explain a little more later on, but the problem is the limitation of large language model. This large language model, they do generate some of the word which has not been even in the paper. So because since large language model is sometimes they just build some word regardless of whether the database include the data. So they do build some, it does, even though there was a wording like the lithium solid solution, but they do some of the wording they generate like a lithium-ion battery or electrolyte kind of word, which does not include in the data source. And then our model does not have that kind of problem. And then finally, and if we look at a little more, then this kind of generation data, so is as a formula section, this the NER-RLE model is like sometimes some useless word is coming out like PTEs, or like sometimes they do show the classification error, which shouldn't be this number should not be in this category, but it goes to that. So if we compare to the NER-RLE model, and then our model was the accuracy of our model was much higher than the NER-RLE model. Sometimes the NER-RLE model does not have the word inside, but they do generate those words. So even though it is not inside, because of the large language model guessing some of the words, then they do just the generating. So it wasn't really successful as a building database point. But our model does not have those kind of problem. And then if we compare to the CAM prompt. CAM prompt also has a similar problem as well. And then some of the word has a classification error, and then some of them has low NER accuracy, and then also some of the data is some generation error. All those kind of problem is exist in this CAM prompt model as well, but in our MLink does not really have those kind of problem, and then each PSPP section has exactly correct data in our MLink model. How much time do you have? It's okay. It's done? Oh, still have time? Oh, okay. Oh, okay. And then the one different section I want to discussing about is after building this data, we want try to use this data to things. First thing is that we have tried to do the research trend analysis using this keyword from the bibliographic text data. And then what we did is the trend analysis. So we analyzed from the all different the papers, and then we taking out the title of the paper, so that we have trying to see what is the different research trend is going on in this research trend. So that what we have been done is from the previous section, we have the collect article, and then we extract the keyword, and then we research structuring. We done the research structuring, and then after that, and then we done the research trend analysis. So these are not like what human being did. What we did is we did using the machine learning by using the taking out the data which we taking out. So that we collect the article, and then we extract the keyword from the title, and then after that, and then we structure the each keyword as if those kind of keyword is mentioned more, then it is more related to the searching field. And then we by using the data, and then we look at the distribution of the data of the or keyword, and then we have classify the keyword, and we try to look at which keyword is the which section. So this is what we have been done. So we have to classify the keyword, and then as a result we can classify the all different keywords as a 3 different sections as what you see. And then this is the unclassified classification, unsupervised classification. So as a result, and then we have classified into the 3 different sections. After that, and then we have been looking at what kind of word is in each different section, and we are trying to classify the data, and then we want to look at the research trend analysis. As a result, what we see is that this is our result from the paper we analyze, and then we can categorize it into the 3 different, as what you can say, and then each category is in structure-informed performance, and then material-informed performance, and then neuromorphic application. We can categorize it into 3 different applications. So depending on the keywords, but this the naming is what we have been done afterward. What the machine did is that they essentially categorize all the paper into 3 different sections. That's the thing. So we can use this method to categorize all different paper into the different section, and then after that, and then as we can see, we can clearly listed all the papers into the year, and then from 2006 to the recent, and then structure-informed performance research has been significantly decreasing. And while the material-informed performance research is still continuously going on, and then recently the neuromorphic application research is increasing a lot, and we can definitely see that this kind of trend from the analyzing these papers or what we have been downloading downloading, and then we can classify what kind of words are included in each different section, and then as a result, and then we can see which kind of the research has been published to all different type of papers, and we have been identified all different research, as we can see. So this is what the turnover of our work.
Thanks for the very energetic presentation. Even though we are a little bit behind, we're going to have a few questions, please.
Thank you for a nice talk. And I do think this work is very valuable to collect all the data from the materials to the device performances. And I would think the completeness of the data is the most important thing. And you mentioned that your model M-Link does not hallucinate new words. And how did you make sure that your model does not hallucinate these things?
Okay, that's a good question. So after we building the database, and then we try to compare. So basically, our model. The first question is how we can make sure that our model does not hallucinating the data. So since we use the NER and then human-based NER tagging, so that it is essentially it is not possible to hallucinating data. So we are not really directly using the large language model. Large language model is just used to build the PSPP relationship. Not taking, but before that, and we identified all the words by word by the NER tagging, so that it does not cause that problem. So let me just go back and then explain. Okay. Sorry. Yep. So if you look at the differences, our model only used the large language model to build the relationship. So we only use the large language model to build the PSPP relationship. But before that, and then we all used for the NER or identifying the all words in the paper, we used the rule-based and then human-based, human NER tagging. So that since if those kind of words should be in the paper, and then we identify those words as a certain, whether it is categorized into the either PSPP. So we use the all different rule and then human-based identification, and then this large language model is only used for the building the relationship, so that it is not essentially hallucinating. And compared to the other model is using the large language model, and then those kind of hallucination issue coming from the large language model, but we prevented those problems by using this initial step of the NER tagging and then rule-based and then human-based NER tagging method.
Thank you.
Okay. Any more questions? If not, I have a very one quick question. So regarding your PSPP database, when you say the process data, how much detailed information do you collect? For example, if for a given paper, CVD is used, then do you collect the CVD and all the information regarding CVD, like the temperature or the precursor, something like that?
Yes. So that's the what it works at this moment, and then that the performance rate what we shows is this is the like whether how much we have in is entire data, not only the processing data, but this is the successful rate of it's like around more than 80% of the data was successfully taken out from the paper and then building to the database.
Then there must be some discrepancy. There must be discrepancy between the papers and paper by paper, because the full article can contain all the information, but like a letter type paper.
Yes.
Do you discard those data, or do you, what? How can you
I mean, that's really good question. That's why some of the paper shows the pretty high rate of taking out all the data inside the paper. Some of the paper has shown pretty low successful rate, and then this is the kind of average value. So it depends on the literature or papers, or what kind of paper. Yep.
Okay, no more questions? Then let's thank the speaker again. All right, we have two more the presentations, and third presentation will be given by Dr. Chio Kim from Georgia Institute of Technology. And while he is preparing his presentation, I briefly introduce about himself. He obtained bachelor, master, and PhD in the Hanyang University, and he had a working experience in Samsung Electronics. Then he moved to the United States, and he is the now research engineer at Georgia Institute of Technology, and he is also co-founder of Mathemalize. And please give a warm greeting to our speaker.
Hi everyone, my name is Chio Kim. Thank you so much for the introduction and having me here. Actually, I felt a little bit loneliness because no one have been speaking about the polymers today, but my major focal point is developing some tools and the methodologies for the developing the polymers for the better performance. And the first part of presentation is the introductory part for the what have been done in the Georgia Tech side, and the second half will be focusing on the how we utilize the findings in the academic setting to some commercialization pathways. So, all right, let me start. So yeah, as we all know, the development of the materials takes time, and it's amazing that the Teflon was already mentioned in one of the presentation today. Teflon have been invented way back to the 1933 and took more than 2 decades for successfully the introduced in the market, and it is still the people are still focusing on making the variations of the base Teflon structures, and yeah, Kevlar, another examples. But why does this take some time? Why is it so time-taking jobs? Because that is we usually use the intuitions and the experience for making the other materials, and also we fails for the experimental procedures. So that's main reason why it takes. And also the polymers has the more complex structures, and its morphology can be varied in many different types of the processing conditions, and the resulting properties and the performance varies a lot. So with that background, a lot of effort have been focused on in developing the polymers in many application areas. And in the Georgia Tech, where I am working as a researcher, we are working on the energy materials, and slightly moving to our focal point to the recyclable polymers, because it's everybody's interest, right? And also the membranes for the separation. Actually, those are all related, but I wanted to make some separations for the easily introducing some use case that I will show in the next slides. And additive manufacturing, which will really accelerate all the processes used in the lab, from the intuition to the actual lab test, and some generative AI. The many speakers have been talking about AI, generative AI, and I will add some more about that. So basically all the examples I will show is detailed in those 2 papers. One of them is recently published, and actually this the multi-organizational collaborative works within the General Electrics and the TRI, Toyota Research Institute, Georgia Tech, and the company I am working on, the Metmorize. So the first example is the energy materials. So the no emission vehicle, actually it is happening these days, right? So before that, the electric vehicles, there was a hybrid vehicles that has a capacitor and the fuel cell inside. So the reason why we are using the hybrid in this type of the vehicle is it is using the electricity and also the fuels as well. And how do we use the electricity? That is interesting part. So usually when we are driving, we hit the brake pad for the slowing down the vehicles, but that the friction force is just the loss of the energies, and we wanted to utilize that kind of loss and minimize the energy. Maximize the energy efficiencies. So the capacitor is a great tool to store the energies very quickly, but the capacity, even though the name is capacitor, the capacity is very low, so that the rapid speed of the charging and discharging can do a role for rapidly accepting the powers, and it can be transported to the batteries in the vehicle. So the keyword for such application, all the polymers are incorporated in the capacitor, fuel cells, and the battery. why the polymers are used is actually it is safer and the cost is low and the weight is very light, and all those three can be can bring a big merit for using the polymers in the many part of this capacitor fuel cells and batteries. But there is some the point that we have to overcome. So the next slide, actually the BOPP, biaxially oriented polypropylene is the standard materials that used in the dielectric capacitor in the hybrid vehicles. But as you can see the curves, the temperature is rising, the efficiency, the discharging energy density is also degraded. Actually, these temperature ranges are usually the vehicles are experiencing while we are driving. So the constant the performance is required. And what if we have this type of this performance by some materials, even in very high temperature, the energy density is still very high. That is very desirable and where we want to go. So using the data-driven approaches and the machine learning, the models for the predicting some basic properties of the polymers, we can do like this. So we can start from some known polymers, known monomers to generate a huge number of candidates, like 1 billion. This is possible because we can do, for example, the known polymers are there. It's very easily accessible. So the list of polymers can be analyzed, and we can learn from that baseline, and we can populate more polymers based on the knowledge learned from the known polymers. So for example, we have 1B hypothetical polymers that can be applied to that can be supplied to the machine learning models, which can make rapid predictions for the properties. And we can do some screening. For example, here we want to have high dielectric constant for higher the energy density, and it have to be resistance to the large electric field. Maybe we can use the electric band gap that can raise the breakdown field in the high electric field. So maybe dielectric constant and the band gap can be two objectives we want to optimize. And if it's processable, then that's where we want to try to in the lab. And we can select some promising candidate from there. So yeah, this is the result. So 1 billion polymers and in very high electrical band gap higher than 4.5 electron volt, and glass transition temperature larger than 450, because we want to make the polymer that is not degradable in the higher temperature. So this section is where we want to go. And one of the polymer, for example, this one, this backbone and the benzene rings, and second carbon has the methyl and chlorine in the fifths. This is the one of the polymer we could find, and there are more actually. And this polymer is actually under validation in the University of Connecticut by Dr. Searching and Yang Kao. So yeah, this is one example that we established in the zero vehicle application, zero emission vehicle application. And yeah, in 2014, I have been participating in this project, the DFT, and that was kind of the outstanding outcome, because before this era, there was very, very small amount of the effort for doing DFT on the polymers. And actually at the time, what I did was making the nice 3D model that we can use the DFT, 3D models for the polymers, very, very simple polymers like polyethylene. In single supercell, the polyethylene only need 2 carbon atoms and 4 hydrogen atoms. That was the beginning. And these team members have been working for populating more polymers in just a simple single chain structures in the supercell. So, but that was meaningful actually. That was good because the DFT was very well performing for making the dielectric constant calculations and band gap calculations. But the people I introduced in the previous slide, Dr. Yang and Dr. Searching, is keep knocking the door and brings the new polymers again and again and ask us the calculation result in one day to make a go or no go decision for the high dielectric capacitance polymers. So that's the motivation for the applying the machine learning approaches using our data set. And now 2020, the machine learning, instead of the DFT, shipped the millions of the polymers that can be utilized for the many applications. And the another application is the recyclability, sustainability, and the green solutions. So we cannot avoid using polymers in the daily life, right? But instead, because the polymers are everywhere in our daily life, we at least want to put some effort to minimizing the harmful effect on the environment. So, for example, what if we can make the polymers easily recyclable, mechanically or chemically, and also these days the organizations or the countries, European countries, are very, very seriously regulating to avoid the use of fluoropolymers. PFAS-free polymer design is one of the major the challenges in the polymer community. So such things have to be considered, and what we have done is, again, apply some typical design procedure, like finding some huge number of candidates and set up some objectives. In this case, in previous example, we just used the two dielectric constant and the band gap. But in this example, we have 6 properties, like some mechanical properties and thermal properties, TG and TD, and ring opening enthalpies as well. So based on those, the target properties and the target range of each property, we can screen the polymers populated in this initial stage. And the last one is green options. For example, polymer does not have should avoid to have the fluorine atoms in the smiles, the structures. And after that, it can be ideal properties. So this is one of the way to finding some recyclable polymers. But there are some more, like we can combine the PHA-based polymer plus commercial polymers and do the population of the possible structures and apply same approaches for the filtrations. So yeah. And another one is the membrane, the filtration. So the gas mixture of the crude oil or crude oils have to be distillated to filter out the required the type of the fuels or the molecules. And the conventional and the traditional distillation had to produce a lot of the harmful effect of the environment. And it takes a large amount of the energies for the operating such facilities. But what if we have some nice filtration, the membranes, and it is easy to create. So this schematics has a mixture of the gas or the crude oils, and this filter is made of the polymers, and it can be split into the different types of the molecules. So this is an example. This is the machine learning model. The parity plot shows how the model is performing by comparing the experimental and the predicted. And this one is showing the very nice agreement between the experimental and the predictions. So actually this machine learning model is predicting just the base property of this membrane, and the prediction result can also be transferred to the next simulation or next some numerical approaches, like this one we call the multi-scale approach to integrating the machine learning and the transport modeling. This is continuum scale modeling. Actually, the machine learning, the prediction result is used as an input parameters in the more advanced the secondary the models to predicting the filtering effect. So yep. And the last one is about the how the machine learning is used in the autonomous autonomous additive or the sequential manufacturing the lab. Actually, this is collaborate with the Dr. Shi in the Georgia Tech, and the main purpose of this the project was making some polymers that can be used in the 3D printing technology, and the application was making this glove that has some different sections in the glove itself. Some parts have to be very strong and thermal resistive, and some parts have to be flexible because it should be flexible and to grab some the other stuffs. So starting from the very small amount of the property data set, we can train the machine learning model, initial training model that may not be very the accurate or the high performance the machine learning model, but that can be the beginning, starting point of this active learning loop. So initial model and predict the properties of the candidate materials and select some materials, do some lab test. Test result can be augmented into the original data set, and model performance can be increased. And by looping these cycles, the new type polymers they are delivered to the Professor Shi's lab, and that can be used for making this glove. Right, so the last one I want to introduce is some generative models, how those generative AI technologies are used in the generating some new polymers. So we can think of the different methods like the polymer genome. Actually, this is the list of the polymer fingerprinting schemes, and these fingerprinting schemes and the model algorithm can populate some new polymers, and these new polymers can be again act as the candidate polymers, and because we already have the machine learning the predictive models, that models can be used for the rapid prediction of the generated models. So, and next one in this is again the language models. We really want to have more data, as the the presenters are already emphasized. We wanna have the pipelines that can be utilized for the rapid extraction of the data from the polymer specific or material specific corpora. So the Polybird or GPT Llama can be used as a large language model, the pipelines, and that can be used for the extracting of the 1 million polymer the properties. Actually, the extracting the data and the knowledge or relationship between the materials and the properties can be covered by large language models, but the challenging part is having the computer vision models or tabular data extraction models. So I believe you or the experienced some difficulties for the reading the chemical structures shown in the papers. If it's 2D, then it's easy, but the 3D crystalline structures are represented in the 2D in the paper. Even human cannot understand that structures many times. So that is very the big challenging part. The next step is mainly focusing on the computer vision models for extracting the knowledges from the chemical structures and the technical drawings. All right, so yeah, all those the inventions and the knowledges developed for about 1 decade have been integrated in this polymer informatics ecosystems, and the main philosophy in our research group is providing our inventions or the findings available to the public. So we are running some polymer genome and some GitHub repository and Polymer Scholar. So Polymer Genome is the academic version of the polymer property prediction platform. So you all can come and make an account and do some basic property predictions for any given polymers. And here we are sharing some data related to the polymers. and some source code that integrated in these ecosystems. And the Polymer Scholar is about this, the language model-based data extraction. So we already extracted a lot of data about the polymers from the literatures, and this Polymer Scholar platform is providing as a public service. So how do we do better? In fact, all the finding or in academic setting is we are publishing our findings in the papers or do some patent filing, but how do we better to share the findings to the people, or how do we make such technologies applicable to the industry? They are accelerating the R&D. That is actually a very important question. So the 2021, I and the group leader, the Professor Rampiram Prasad, have founded Metmorize, which is the startup company in the Georgia base. So our goal is to help all the industry or the academic people accelerate their R&D based on the polymer informatics technology that we invented in the Georgia Tech. So it's funny that all the findings, data, and some the algorithms or pipelines have to be registered as an IP to the institution, Georgia Tech. And this company I found also invented such technologies, have to purchase that IP, and I'm running this company. So our main solution is Polymerize. Actually, this is the commercial version of the polymer genome, and it is providing more advanced features like the training the custom models using your data. And basically, it provides nice predictors and stock models of the property predictions and screening features. So from the data, even if it's small or big, it can used for the training and utilized for making the property predictions and screening using the populated candidates and making the decision. So all the pipelines described in this figure can be done in our service Polymerize. So yeah, this is kind of what type of the materials or polymers can be handled in our platform. So yeah, let's skip this slide. And very recently we have applied some advanced the algorithms. So usually we are using the data and build the model based on the data. But there is no reason to just avoid using the non-physics. So the physics is the trademark name that has the conventional neural net and one last layer that we can incorporate the non-physics. So for example, if some phenomenon, if we have a small number of the data in the data set, and but data set size is small, but we know that property is well following some known physics like Arrhenius equation that is strongly depending on the temperature, then the known physics can be incorporated in this architecture. And of course, we are providing the fingerprinting schemes like handcrafted fingerprint called polymer genome or machine-crafted fingerprint like PolyGNN or PolyBird. So if we compare the polymer genome and those two others, then the performance of the fingerprinting is similar. Accuracy of the fingerprinting is very similar, but the speed is the way faster if we use the PolyBird. So imagine that we have 1 billion or million of the polymers. If we use the polymer genome fingerprint, then fingerprinting itself will take a few months. But because we have machine-crafted fingerprint called PolyBird, it can be done very quickly, maybe 2 or 3 orders of the magnitude faster than the handcrafted one. All right, and this is the Ask Poly is the large language model based the chatbot, and the Poly is the large language model's name. So this is very, very baby, and the first version, even version number is smaller than the 0.1. So the version 0.07 is the version number. So it is just doing some basic interaction using the human language for making the predictions for the given polymers. So we can ask what is the TG, TM of the PVDF, then it gives us the answer. This prediction result is the large language model-based prediction. But if we ask something like what is the temperature, melting temperature of a PVDF using polymerized stock model, then it uses the stock model, which is explicitly trained using just the tabular the stock data. And also it can give you some design features as well. For example, could you provide 3 the fluoropolymers with higher melting temperature than this one? Then it gives some the new polymers. And also, if the version is improved in the future, we are planning to have some customizable, meaning the fine-tunable capability using your data. So you can use our the base large language model as a baseline, and you can provide your data to train the next version of the predictive models. All right, some series of the applications with the client will be introduced. So the Kimberly-Clark is our long-term client, and basically we are doing some work for them. For example, making the predictive models for some mechanical properties of the non-oven materials, and because that the Kimberly-Clark is buying some raw materials from the other vendor, and the vendor is not opening their raw materials information. So we cannot have a full descriptor for making the model. So model performance is kind of poor, but still we can build a model. And this model can be used for the designing and the filtering some required properties. So for example, this blue histogram is original experimental result provided by Kimberly-Clark, but by using the data-driven approach and the automated candidate population and screening features, we can populate way more large number of the cases. And yeah, this is one example. And some other example is the making some materials that can be used for the semiconductor application and electronics applications. And the Asahi Kasei is a Japanese company, a global company, but based in Japan. And they are putting huge effort for making the new polymers, which is the carbon neutral, actually. That is the big agenda in these days, right? So they just simply use the dielectric constant for making some predictions of their new polymers. We don't know because they don't tell us, but they are using the platform and they are doing work for predicting the dielectric constant and the proton conductivity. So based on those two properties, I can imagine that their application is something in the electronics, and some transport property is making the important roles in their application. And the Resonec, another company working on the 6G technology, the polymers for the application in the 6G technologies, and they are using the stock models like these, and some benchmark result made by themselves is they're showing that the polymerize is outperforming compared to the other the method for the fingerprinting. All right, so I think this is the last slide, or last application. The PFAS-free the polymer design is also important topic these days. So the polymers that used for the many applications, like the cosmetic containers, like a shampoo that has the fluorine PFAS polymers, and it is required to remove, the finding some replacement polymers that can do the same role, but without PFAS. So we can set up some design goals for that application. For example, shampoo container, then melting temperature. Oh no, shampoo container is not a good example, but some example. So melting temperature have to be very high, band gap have to be a certain amount, and these tangent rows have to be smaller. But starting from the candidate generation step, like 1,000 PVDF-like polymers, but PFAS-free, we can use the stock models for these properties, predict rapidly and screen screen based on our target objectives. And finally, we can remove all the polymers that has a fluorine and bring those the candidate to the lab for the testing. And this is finding. So yeah, for example, here some mechanical properties and solubility parameters and the melting point. We want to be here, and there are some candidates. And here are the reference polymer PVDF, and we found a lot of polymers, but unfortunately most of those has fluorine. But here we find one, so that can be one of the candidate material. Okay, so yeah, this is what I have, and questions. I would say some credit to the Ram Prasad group members here and the Metmorized families, and some funding agencies like Georgia Tech, Georgia Research Institute, Georgia Tech, and ONR, NSF, CJ Bio, or our client, valued client. Thank you.
Thank you for the very nice presentation. We are open for the discussion and questions. Okay, please.
Thank you for a nice talk. I'm interested in polymer in general, and I think I saw some like single chain polymers examples, but there are many heterogeneous polymers and branched polymers. Have you handled like some heterogeneous polymer like black copolymers or random copolymers? And if so, how did you represent for the machine learning inputs?
Yeah, okay, that's a good question. Actually, single chain polymer, we call that as, no, it's different, but the homopolymers, right? Homopolymer consists of single monomers, and copolymers is combination of different monomers. And it can be alternating or random or blocks, right? So it's kind of easy task to representing that as a numerical vector, because we can fingerprint each monomers. For example, in the copolymer, for example, there are two monomers. Then we can fingerprint them separately and combine those fingerprint vector based on the composition of each the monomers occurrence. And if we want to add more details, like whether it's random or block alternating, then that feature can be additional descriptor, right? So it's simple. And we may be wondering about, what is that? I don't remember. Sorry.
And I have one more additional question. So if I remember correctly, the properties of polymer can be tuned by additive. So did you consider some additives as well?
Oh yes, of course. That is actually in the industrial background. Industrial sector, additives are very, very important. None of the industrial people are interested in homopolymers or copolymers. So the additives, what type of additives have used, and how, what is the amount of the additives, flame retardant or reinforcement, right? And what type of the processing conditions have been passed through, that also will affect on the final performance of the polymers. So all those information have to be, sometimes type of the additives have to be included as a categorical descriptors in the data set, and amount of that additive have to be added as a numerical descriptors. And those information can be encoded like one-hot encoding, right? The magic method, one-hot encoding. Yeah.
Thank you.
Any other questions? Can I give you one question?
Yeah.
I happen to see a keyword on your slide about the polymerize, which I pretty much interested in, which was the polymer with hybrid materials. So can you provide some kind of properties of the interaction between the polymer and hybrid materials?
Actually, that depends on what type of the other the materials are combined with polymers. And
like solid materials, let's say.
Well, for example, the perovskite, for example. The hybrid perovskite contains some molecules inside,
I see.
right? A, B, C, one of A, B, or C can be the. That's not the polymer, but maybe combination of the soft matter and the solid backbone is one example.
It's possible.
And maybe we can represent such structures using coordination of the backbone structures. What is it? The framework structures and the monomers or polymers included can be, the translated using just the polymer genome fingerprinting or polyglot fingerprinting separately.
Okay, thank you. Any more questions? Then let's give a big hand to the speaker again. Finally, we are gonna have a last talk by Dr. Kwang-yeol Lee. He's from Korea Institute of Science and Technology. I will briefly introduce about Dr. Kwang-yeol Lee. He graduated from the Seoul National University in the Department of Metallurgy, and he got a PhD in the Department of Material Science and Engineering, KRICT, a long time ago. And then he is now principal research scientist in KIST, and he's a kind of founder of Computational Science Research Center at KIST. And he's going to talk about how we can curate data, materials data. Please give a warm greeting to our speaker.
Thank you for kind introduction, and I'm very pleased to come here and very pleased to introduce our effort to build a kind of standard data schema and standard data vocabularies for the future of our material science. So I came from Korea Institute of Science and Technology, and I'm also in charge of the Material R&D Data Standard Expert Committee. So I'm very happy to introduce the present progress to make some kind of a harmonized material data schema and vocabularies. And before starting my presentation, I'd like to acknowledge all the contributors to build this kind of standard, and all these people are very much devoting to this effort. And thank you very much for all this effort. And this is a famous diagram about the paradigm of material science, and the time spans whole human history. And I used to say that we are in the stage of third and transition stage from third to fourth paradigms, like here. But in this symposium, I recognize that we are in the middle of the fourth paradigm. I was surprised. I was really surprised of the speed of the transitions. So all the people is now involved in the machine learning, and and I also enjoyed the excellent presentation about the very successful story, and also successful and promising, some kind of promising future about the data collections and the data management. But I also feel that there is some kind of course, there is a very positive atmosphere about our future. But also, I feel some kind of negative shadow in this atmosphere. Frankly speaking, we all worry about the data. So everybody say about we do not have enough data, and we do not have an appropriate form of data, and we need more integrated form of the data. So I'd like to suggest that don't be overexcited. Just sit back and take a big breath, and then think more fundamental aspect about the data. So I'd like to ask this thing: what kind of data do we really need for the machine learning, for the material design by using the data? So that is the basic theme that I want to discuss in this presentation. So I'd like to talk about what is the AI-ready data for materials design. So I think it should have two properties. First one is, of course, all the data should have properties. It should be explicitly defined data, which means that when you see this data, we all have to understand what is the hardness. We should understand that one. And then if it has a number, like a 30 in this example, so we should also have some the common rule about the unit of this value. So we have to define everything. So this definition of the keyword and definition of the data form, and also in the case of numeric data, the unit is a kind of a standardization of a vocabulary. But this is not enough for our machine learning. So it should be associated with certain materials. So until recently, these kind of data appears in the various handbook. Materials handbook always has this kind of data. And as Professor Lee criticized that simulation data also has this kind of information. But this is, of course, not enough. We should have an understandable context of the data. Data should have a story. So because of this story, we can do machine learning. We can predict something. We can optimize something. So in order to do that, we have to have information on how to synthesize these materials. And what is the structure? What is the composition? What is the defect? What is the surface? What is the interface? And all this information should be integrated into the data structures to report these hardness values, so that then we can understand this hardness has a story. Or this hardness is the material which is synthesized like this method, and also this structure, something like that. Then by learning this relationship, we can design the materials. We can optimize the process. So I think this is an AI-ready materials data set. So in our committee, we try to make a standard for the vocabularies, as I mentioned, and also we try to standardize the data structures which can have a context of the data. So that is our mission of this committee. So once we build that kind of standard, I think this is a very important rock base for the future of material science, because this is some schematic diagram of data flow in our future. If we are doing the data-driven material design, somebody should collect the data from experiment, calculation, or publications, and then we will build a kind of a data lake, very, very large data lake. And the users of the data should collect the data from this lake, and that data should be well structured, should be AI-ready data. Then we can analyze that data, and we can learn from that data to find some materials, some novel materials, and optimize the data. So I think the standard data schema and vocabulary is a kind of a language for our future material research. So I think this is a very important aspect of our future. But the problem is, material is actually has a wide spectrum. As you can see here, from steel to the biosensors, all these are in the discipline of material science. We have a huge amount of apparently very, very different sub-disciplines. So the question is, our main challenge is how to collect the data into one harmonized data structures. So that once we build that kind of harmonized data structures, we can it can increase the potential of data-driven research. For example, we have data over some battery materials, but that data can be used to build some kind of fuel cell materials, or some photovoltaic materials or something like that. That we called it has an interoperability. So we want to build the interoperable data. In order to do that, we should make some kind of harmonized data schema, standard data schemas, so that we can play around in that schemas. It looks very different, but if we see this one into a kind of the workflow of material research, then I think we can find some common factors in all these kind of materials. So let me explain details. This one is This one is famous. I'm sorry. This one is famous material data science tetrahedron, PSPP. So many times mentioned by Professor Lee. And in this case, this is a kind of a static model. But if we decompose this into the workflow, we can draw like this process. By using the process, we can build the materials of a certain composition and structures. Then material should have properties. The properties should be characterized by a certain method. And then in diagram, there is a performance. But in this diagram, we think that there is one thing missed. So we should add the concept of material systems into this one. Because in order to characterize the performance of certain materials for a specific application, we should build a material system. So let me show the details in later. And in order to build the material systems, we need additional materials. So let me explain using these examples. So in the case of of course, let's imagine that we are working on the heterogeneous catalyst. So in this case, first thing we have to do is to synthesize the catalytic particle. So during this process, we have information about the synthesis. Or if we are working on the theoretical work, we should have a model of these catalytic materials. And we also have to characterize the particles, for example, size, composition, and the surface orientation or something like that. And then that property have information how to analyze, how to calculate all of these things. These are a kind of a metadata of the property of these catalytic materials. But in order to characterize the performance of these catalytic materials, we have to build a catalytic system. So in this catalytic system, we have a supporter, we need a supporter, and we need the promoters if required. And by assembling these materials, we can build the catalytic systems. Then we can now characterize the performance of this system. So we have to include the material system. Then by including this concept of material system, many apparently different material research have some common aspect. As you can see here, this is a case of perovskite solar cell. It also have a same the workflow data structures. And also in the case of fiber reinforced materials, it should also have the same structures. So by introducing the material systems, we can build a kind of a harmonized data structures that can cover a whole kind of sub-disciplines of materials. This is a kind of a definition of material systems. The material system is defined as an object that is composed of one or more materials to characterize the performance of materials. So this is the examples. So our approach to build a harmonized data schema is we build a schema based on the workflow of material scientists. And we also build a schema to cover whole sub-disciplines in material science by introducing the concept of material system. So that is our basic approach to overcome these problems in material science. So what the outcome of this committee is to build a structured data keyword dictionary, as you can see here. So we regularly publish the dictionaries using this one. And we also publish the dictionary both in document and also in JSON form, so that you can apply that dictionary to your data management platform or your future nationwide very huge scale of database system. So our suggestion based on this idea, this is our recommended data structures for material research data. So of course there is 3 sections: metadata, material section, and system sections. And metadata is simple. It's that this is to explain the data set. So in the material sections, we have a number of material data in material sections. And each material information should have a chemical information, and also it should have a process information to synthesize the material. And it also have a property, inherent property of that materials, like physical and chemical properties, which is quite independent of application of them materials. And then there is a system sections. In the system sections, the unique point is configuration. Configuration means that in this configuration, it defines which material is used in this material system. For example, in the case of catalytic systems, so we can define material 1 as active materials, material 2 is a support material, material 3 is the additive materials. Then we can completely figure out what kind of a material system we are using to measure this performance. So this, of course, there is also need the information of synthesis, a kind of assembly process to build the system, and also it has a performance data. This performance data is a very system-specific information. So in the case of catalyst and photovoltaic and the composite material should have very different value of kind of performance. So this system is the vocabulary here is very system-specific, but in the case of material section is quite general. So if we see some examples, this is a real data set, some kind of example data set. This is the metadata section, and here is the 2 materials information in the green box. And here is the chemical information and process and property information is included in these material sections, and this also have that one. And then there is a system information. So in the configuration, we define what is the active material, what is the amount of active material, what is the support in the case of a catalyst. And then we have information of the performance, as you can see here. So then if we have this kind of structures, then now we can understand the context of this data. And then by combining the relationship, I hope we can optimize many things about the materials. So now I'll talk about some boring part of my presentation. This is about the dictionary. And in the dictionary, depending on this idea, in the dictionary we have 3 vocabulary group of metadata, material, and system-specific vocabulary. And analysis and material process is commonly used in the material section and in the system sections in many areas. So we make a separate group of analysis method vocabulary and the material process vocabulary. And additionally, we also defined how to express the numerical data in these databases. So we have 3 vocabulary group, 2 common vocabulary group, 1 numeric data group. And if you are interested in this, please visit the github.com and type this keyword, then you can find our all information about our effort. And each keyword has certain these structures, like for example, the keyword name has an English definition, an alias, and we define the data type associated with this keyword, and we also provide some data examples in the dictionary. And real data appears like this. So name, some string values. So the numeric values always have a value and uncertainty should be provided. We are recommended to provide. Of course, in some cases there is no uncertainty, but we recommend to provide uncertainty and also provide how to measure these values. So that is also very important to compare the measured data and compare the calculated data. So in the case of calculation, in this part, you can include all kinds of computation conditions in this one. So that the array numeric data also provided. So, okay, we are 10 minutes behind, right? Yes. But I will try to keep this time. Right, so 7 basic SI units of all these things can be found in the GitHub. So don't be stressed too much about too many fonts, too many characters in the paper. And we have chemical information. We prepare these keywords and these property keywords. So many keywords are actually prepared at present. And also system-specific vocabulary. This is now we published the version 2024-01, and it has a 10 material system. The keyword is included in these systems. So this memlistive is the contribution from Professor Lee and something like that. And photodetectors from Chris. Chris. And And this is a process. In the case of process, we define the keyword of the unit processes so that when you build your template, data template, you can plug in these values into the required place in your platform. So you can simply pick this one into your system. So for example, in the case of making a catalytic particles, some people using the solver thermal process and then heat treatment and then centrifugation is doing, then you can consecutively add that keyword into your data template so that you can make your own template quite relatively easily. So here DFT, in the case of DFT is also we are treating DFT calculation as an analysis method, and here is the list of the major parameters for DFT calculations or something like that. So all this information, as I mentioned, the GitHub is provided by Met Research Data Standard Committee in GitHub. So please visit their work there. And so we maintain the versions using the branch function in the GitHub. So we also publish the data in the form. And as a summary, we have been building harmonized data schema and vocabularies for whole sub-disciplines of material science. I'd like to emphasize we try to cover whole sub-disciplines of the material science, and based on the workflow and the concept of material systems. And we welcome your participation for building and extending vocabularies in this dictionary. We are fully open. So any suggestion, any recommendation, any requirement for your own purpose, so we are happy to include your requirement into our systems. And when you did that one, you should be proud of that you are making language for our future. Thank you very much.
Thank you very much. We are open for the questions and comments. No comments or no questions, please? Yes.
Oh, I really like the talk, Dr. Lee. Really, really nice. Yeah, I was just a little bit, I wouldn't say confused, but just curious. So, for example, when we look at any regular paper, you report on the performance you mentioned, and you actually classify groups of materials into the system. I think that's a very good idea. But how can we distinguish this between a material system and the performance of the device?
Device is a material system is actually include the devices. For example, we can say that So in the example, you can see the photovoltaic device. That is, we consider that as a material system.
I see.
Because that includes not only perovskite layer, it also have a whole transport, electron transport layer, and the electrode. So many materials is combined in to build that device. That is the concept.
So maybe my point is more, would you have a system within a system? So a device is a really complex.
Right,
yeah,
right.
That's my point. So, I think a system, maybe you have a max, I'm not sure there's a maximum number of components of materials, right?
That is a very, very good question. And we are still discussing about that issues. So how much, where is the boundary between the material system and the materials, or something like that? That is a very, very difficult questions. And in that case, I'd like to accept the opinion from community. So photovoltaic research group I think they should have their own some idea how to deal with their data. So in our standard, our basic attitude is to accept the community opinions, whatever it is, so that there is a precedent. But you are correct. That is a very, very difficult questions. We are still discussing about that one.
So other questions, Dr. Chio Kim?
Dr. Lee, so many times the material scientists are handling, for example, two-dimensional plots like the stress and strain curve and some frequency-dependent dielectric constant. So do you have some visions for the making those easily?
To include that data.
Yes.
So that is the reason why we provide the standard for numeric array data. So graph is actually, in the viewpoint of data, some graph is a kind of numeric array value. So that, can I see my view graph? I will show you. Could you show me the slide? Oh, sorry. Okay. Oh, okay. This is the numeric array. So graph is one. If you draw this graph into table, it's the same as this graph. So that they should be included as an array data. So that is also very, very difficult part for us to make a standard for these things. Right? That's true. Thank you.
Any other questions? I have one quick question.
You always ask one question. We are behind the schedule.
Okay, one quick question. Okay, like you said, it's gonna be recommendation for the researchers, but somehow, anyhow, we need to encourage the researchers to use those kind of vocabularies. But I believe that the people's, personal, the instinct is kind of the laziness, not for you, but how would you attract people?
I think there is a very common and serious questions for collecting the data. So no one actually don't want to spend their time to just collecting and managing the data to deposit the database. So that autonomous lab is very important. And we should build some kind of automatic data collection systems. So I think that is the only solutions. Once in my institute, once I build the laboratory notebook, electronic laboratory notebook, the idea is that if researchers is doing research into laboratory, then the data should be automatically collected from that electronic note directly to the database. I think that is the only promising way to collect the data from the laboratory. So in order to do that, we need a very high level of natural language process, because everybody should write their notes on their own way. So we should find a way how to systematically collect the data, how to understand their handwriting, how to machine to understand the handwriting values or something like that. So there is so many challenges. That is what I say, a kind of shadow of our future. But eventually, I believe that we can solve it. We can solve it, and the future should be bright. Thank you very much.
Okay, let's give a big hand to the last speaker. And this is the end of the last session. And I deeply appreciate all the speakers and participants. And is there any announcement from the KRICT? Okay, thank you. Thank you very much.